Welcome to the course for Uniswap V3. This course is for Solidity developers who have experience working with Foundry. To fully understand this course, you should also have a basic understanding of a constant product AMM, such as Uniswap V2. What will you learn in this course? You'll learn the algorithms of Uniswap V3. Some of the topics that we'll cover are math for liquidity, algorithm for swaps, and the algorithm to calculate the fees for liquidity providers. I will also explain the math and the code for time-weighted average pricing, TWAP. And finally, there will be several exercises in Foundry. In this course, we won't cover the advanced math library used in Uniswap V3. We'll work a little bit with the periphery contracts, position manager, and the router contract. However, we will not go into the details of how they work. Why should you take the course? Many of the core math used in Uniswap V4 to calculate liquidity and to calculate the swap amount is basically copied over from Uniswap V3. So by taking this course, you'll have a foundational understanding of some parts of Uniswap V4. Another reason to take this course is that you might have ideas for a new AMM. Uniswap V3 is an influential contract, so I'm sure that when you're doing audit contests and bug bounties, knowing the core mechanics of Uniswap V3 will help. This course has some exercises in Foundry. So here I'm going to explain how to set up Foundry to do the exercises and then where to look for the exercises and the solutions. So the first step is to navigate to the GitHub repo Advanced DeFi 2024 and then git clone this repo. You can do that by clicking on this button called code and then copying this git URL and then inside your terminal type git clone followed by this URL. So once you clone this repo, head over to the README. And then scroll down, and we're looking for a link called Uniswap V3. Okay, here it is under Topics, Uniswap V3. Click on this, and this will take you to another page. Inside here, it links to all of the resources that you'll need for this course. In particular, here I want to show you what the exercises will look like. Scrolling all the way down. Okay, here it is. Exercise 1, single pool exact input. Let's click on this to see what the exercise looks like. Okay, here it is. Here is the exercise. Inside this contract, the instructions are laid out to how to do the exercises. Once you fill out code inside here, you'll execute the Foundry test to check your answer. Now, if you're feeling stuck, you can check the solutions. Notice how the folder is structured. Let's click on this folder called Uniswap V3. There are two folders here, exercises and solutions. Exercises will contain incomplete Solidity files where you will fill out the code to complete the tasks. Solutions will contain the contracts with the answers filled in. And finally, I'll show you where to look for instructions on how to set up Foundry for this course. Let's go back to Advanced DeFi 2024. Okay, and then under README, go all the way down to a link called Exercises and Solutions under Table of Contents. Click on this, and then this will take you to a section called Exercises and Solution. Here you'll find all of the instructions that you need to set up the test for Foundry. Basically, what you need to do is forge build to install dependency and to initialize Foundry project, and then afterwards, to execute the test, you'll need to set up the fork URL. This will be the RPC URL to the mainnet fork. And here are some example test commands that you can execute to either execute the exercise or to execute the solution. The full version of this course is available on Cyfin Updraft. Follow the course on Cyfin Updraft for better tracking, quizzes, prove your knowledge, and join a community of over 50,000 Web3 engineers ready to help you out and answer your questions. Imagine that on DAI USDC pool in Uniswap V2, we have 100 tokens each. At this point, the price of 1 DAI is equal to 1 USDC. Let's say that we swap 1 DAI for 1 USDC. We will have 101 DAI and roughly 99 USDC. And at this point, the price of 1 DAI is roughly 0.98 USDC. But if you want to have a DAI USDC pool so that after swapping one token for the other, the price remains between 0.99 and 1.01, then we would need far more tokens inside this pool. To be able to swap 1 DAI for some amount of USDC so that the price remains above 0.99, or to swap 1 USDC for some amount of DAI so that the price remains below 1.01, we will need 200 tokens each. Drawing this out on the constant product curve x times y equals L squared, we will have 200 DAI and 200 USDC, which would produce this curve in purple. And let's say that the price 0.99 corresponds to this point on the curve, and the price 1.01 corresponds to this point on the curve. When the amount of DAI in this pool is 200, and the amount of USDC is also 200, then on this curve, we can swap one token for the other, and then after the swap, the price will remain inside 0.99 and 1.01. For the price to remain in these two price ranges, we roughly need only one token. But to produce this curve, we need 200 tokens. In other words, we need 200 DAI and also 200 USDC so that after swapping one token for the other, the price remains inside 0.99 and 1.01. But if we zoom in over here, we can see that starting from the current price, let's say is over here, to move this price to 0.99, the amount of USDC that goes out is this part. So we only need this much amount of USDC to support the price change from the current price to 0.99. And likewise, for the price to increase from 1 to 1.01, the amount of DAI that we'll need is this much. So if we have this much amount of DAI and this much amount of USDC, then we can create a constant product AMM so that when we swap one token for the other, it will still remain inside the price ranges of 0.99 and 1.01. And the rest of the tokens that are over here and the tokens that are over here are no longer needed. And this is the core idea of Uniswap V3. This is called concentrated liquidity. Concentrated liquidity means liquidity bounded within some price range. Going back to our previous example, let's say that we have 200 USDC and 200 DAI. What Uniswap V3 does is using these real amounts of tokens, 200 USDC and 200 DAI, and given the price ranges 0.99 and 1.01, it can construct this larger constant product curve so that all of this 200 USDC and 200 DAI will be utilized within the price ranges of 0.99 and 1.01. For example, again, let's say that the current price is equal to 1. We can swap out all of the 200 DAI so that the price will increase to 1.01. Or we can again start from the current price equal to 1 and swap out all of the USDC so that after the swap, the price will be 0.99. On Uniswap V2, the maximum amount of tokens that we can swap so that the price remains inside 0.99 and 1.01 was one token. However, by concentrating our liquidity inside the price ranges, in Uniswap V3, we are able to create a pool that can swap 200 tokens. If we were to construct the same green curve in Uniswap V2, then we would roughly need about 40,100 tokens each. However, in Uniswap V3, by concentrating our liquidity, we only need 200 DAI and 200 USDC. This 200 DAI and 200 USDC that is actually needed in this price range is called the real reserves. These are the actual amount of tokens that we need in this price range to create this green curve. This 40,100 token of USDC and 40,100 of DAI is called the virtual reserves. This is the hypothetical amount of tokens that are needed to create this green curve. Let's make a comparison of how much more efficient this Uniswap V3 curve is compared to the Uniswap V2 curve. If we were to create this green curve on Uniswap V2, then we would need 40,100 tokens. In Uniswap V3, we can accomplish this only by having 200 tokens. Dividing 40,100 by 200, this is roughly equal to 200. So in our example, by using Uniswap V3, we can amplify our liquidity by roughly 200 times. In this video, I'll list out some differences between Uniswap V2 and Uniswap V3. Inside the smart contract of Uniswap V2, it tracks the reserves of token X and token Y. And from this, we can calculate the liquidity and the price. However, in Uniswap V3, things are the opposite. The smart contract of Uniswap V3 tracks liquidity and price. Using this liquidity and price, we can calculate the reserves of token X and token Y between some price ranges, P of A and P of B. The next difference between Uniswap V2 and V3 is passive liquidity management and active liquidity management. As a liquidity provider in Uniswap V2, all you have to do is deposit some tokens. Over time, your liquidity will collect swap fees. This liquidity that the liquidity providers deposited is represented as a ERC20 token. However, in Uniswap V3, liquidity must be managed actively, and the token that you get for providing liquidity is a ERC721. When you add liquidity to Uniswap V3, you'll have to specify a price range. When the current price is within that price range, then your liquidity position will collect swap fees. When the current price goes outside of the price range that you set, then your liquidity will no longer collect swap fees. So in order to collect swap fees, you'll have to reposition your liquidity to the current price range. So as a liquidity provider, you'll need to actively engage with the Uniswap V3 pool to constantly collect swap fees. The liquidity that the users provide and the amount of swap fees that's been collected by that liquidity depends on the price range, when the liquidity was provided, and how long the liquidity was provided. So this can no longer be represented as a ERC20. And this is why it is represented as a ERC721. Some other difference between Uniswap V2 and V3 is the swap fees. On V2, there is only one swap fee, 0.3%. However, on V3, currently there are 4 swap fees, 0.01, 0.05, 0.3, and 1%. More fees can be added by the Uniswap governance. Another difference between Uniswap V2 and V3 is how the TWAP is stored, the time-weighted average price. In Uniswap V2, the time-weighted average price is stored as an arithmetic mean. However, in Uniswap V3, it is stored as a geometric mean. Next, let's look at some pros and cons of Uniswap V3. Let's start with the pros. Concentrated liquidity in Uniswap V3 allows liquidity providers to utilize all of their tokens. So, in Uniswap V3, we have a higher capital efficiencies for LPs. We can also add liquidity using one token. In Uniswap V2, when you add liquidity, you need to deposit both tokens. However, in Uniswap V3, by specifying a price range that is outside of the current price, we can only add one token. Using this feature, we can easily create a range limit order. For example, let's say that the current price of ETH is 1,500 USDC, and you're willing to sell your ETH for 1,600 USDC and above. So what you can do is add liquidity, let's say to the price range of 1,600 USDC and 1,700 USDC. And if the current price of ETH goes above 1,700 USDC, then all of your liquidity is now in USDC. And you were able to sell all of your ETH above 1,600 USDC. So that's range limit order. Next, let's look at some cons of Uniswap V3. One of them is active liquidity management. If you want to continuously collect swap fees on Uniswap V3, then you'll have to reposition your liquidity every time the current price goes outside of your price range. Another con of Uniswap V3 is that liquidity is represented as ERC721s, non-fungible tokens. Liquidity can no longer be transferred easily like in Uniswap V2. So for a smart contract developer, you'll need to put in more effort to integrate Uniswap V3 into your smart contracts. So these are some pros and cons of Uniswap V3 and the difference between Uniswap V2 and V3. Here we have a constant product curve x times y equals L squared, the curve that is used in Uniswap V2. For such pool, it is desirable to have a higher liquidity. On the graph, if we increase the liquidity, you'll see that the constant product curve, displayed in purple, shifts over to the top right. Furthermore, you can see that the curve becomes more flat. The reason why it is desirable for AMMs to have higher liquidity is that higher liquidity means less price impact. On an AMM with large liquidity, we can swap a lot of tokens before the price changes. However, in an AMM with low liquidity, then even if we were to swap a little amount of token, the price will change a lot. For example, if we had a Uniswap V2 DAI USDC pool, and let's say that the liquidity is really low, then for putting in one DAI, you might only get 0.9 USDC. This is not a good deal for a swap. So, higher liquidity means less price impact, and this will also mean that more traders will be swapping on this AMM. Now let's say that we have a constant product AMM, and the amount of token X is equal to 100, and the amount of token Y is also equal to 100. And this dot over here, labeled as P, represents the current price. Now let's say that we only want to provide liquidity to some price ranges, P of A and P of B. For example, if this was a DAI USDC pool, we can say that the price range we want to provide liquidity is between 0.99 and 1.01. And if we were to swap tokens on this AMM curve so that the price after the swap remains inside this price range, then the amount of tokens that we can swap will be about this much for token X and about this much for token Y. This is a really small amount. But what if we wanted to utilize all of this 100 token X and all of this 100 token Y, and we only want to provide liquidity between these price ranges? This is possible in Uniswap V3. Uniswap V3 will allow us to concentrate our liquidity between the price ranges P of A and P of B, so that all of this original token X will be used between the current price P and the upper price P of B, and all of token Y will be used between the price ranges P and the lower price P of A. If we were to create the same curve on Uniswap V2, then we would roughly need 254 token X and 254 token Y. Making these price ranges P of A and P of B smaller, we get a higher liquidity. And higher liquidity means less price impact. On the opposite direction, if we increase the price range, then liquidity is decreased. And as we increase the price range further, the curve of the concentrated liquidity converges into the curve of Uniswap V2. What this means is that if we were to provide liquidity to the price range 0 to infinity, then we get the same curve as Uniswap V2. As we decrease the price range, the liquidity will be concentrated into a smaller price range, and we will have a curve with higher liquidity. For example, let's imagine that this curve represents DAI and USDC pool, and we only want to support the price ranges between 0.99 and 1.01. So to do this, I'm going to set the price range between 0.99 and 1.01. And let's see where the concentrated liquidity curve is on the graph. So I'm going to zoom out all the way. And you can see over here, this is our original Uniswap V2 curve. And this is the curve of the concentrated liquidity when the liquidity is concentrated between the price ranges 0.99 and 1.01. If we were to create the same curve on Uniswap V2, then we will roughly need about 20,051 token X and 20,051 token Y. However, in Uniswap V3, we can construct the same curve by concentrating our liquidity between the price ranges of 0.99 and 1.01. And the only amount of tokens that we use to create this liquidity curve is 100 token X and 100 token Y. In Uniswap V2, if you know the amount of tokens inside the contract, then you can calculate the spot price. However, in Uniswap V3, it is the opposite. The smart contracts keep track of the price and liquidity. Knowing the price, liquidity, and the price ranges, we can calculate the amount of tokens that must be locked in those price ranges. The way that the price is stored inside Uniswap V3 is by this formula. Inside the smart contract of Uniswap V3, it keeps track of the current tick. And to get the price, you will take 1.0001 raised to the tick. This tick can both be a negative number and a positive number. When the tick is equal to 0, the price is equal to 1. When this tick is negative, then the price will be less than 1. And when the tick is positive, then the price will be greater than 1. To show you this, as I slide this tick over to the negative number, you see over here that the price is less than 1. And as I move this further and further to the negative numbers, you see that the price approaches 0. If I go the other way, as I increase the tick, the price increases. And if I increase further, the price goes above 1. And if I increase it further, you can see that the price skyrockets to infinity. So this is how Uniswap V3 keeps track of the spot price. It uses a formula, price is equal to 1.001 raised to some tick. This formula is an exponential function that ranges from 0 to infinity. As the tick slides to negative infinity, the price approaches 0. And as the tick slides over to positive infinity, the price also skyrockets to infinity. In the previous video, we saw how Uniswap V3 calculates the price. It uses this formula. The price is equal to 1.0001 raised to some tick. In this video, let's see where this price will be on the constant product curve as we increase the tick and as we decrease the tick. So as a review, on Uniswap V2, we can calculate the spot price given the amount of tokens. In Uniswap V3, given the price and the liquidity, we can calculate what the amount of tokens should be. And using this fact that given the liquidity and the price, we know exactly where the amount of tokens should be on this curve, we can plot this price as we change the ticks around. So, for example, if I increase the tick, we can see that the price increases. And if I decrease the tick, you can also see that the price decreases. Let's imagine that we are a liquidity provider to our Uniswap V3 pool. For simplicity, we will say that we are the only liquidity provider to this pool. When we add liquidity to our Uniswap V3 pool, we are creating a position. Position means liquidity concentrated in a price range. And to add liquidity, we'll need to know several things. The current price that is stored inside the Uniswap V3 pool contract, the price ranges to add liquidity, and the amount of tokens to add. There are several conditions to the amount of tokens that we can add, depending on the current price and the price ranges. But here, we won't get into the detail of that. What I want to explain in this video is how to visualize this liquidity between the price ranges P of A and P of B. And to visualize this position, we'll plot prices against liquidity. On the horizontal axis, we'll plot the prices. The price in Uniswap V3 is given by 1.0001 raised to some tick. So here, instead of using prices, I'll use ticks. And here on the horizontal axis, we have T of A, which corresponds to a tick of the lower price, P of A. And we have T of B, which corresponds to the tick of the upper price, P of B. And here's the current tick that corresponds to the current price. As the price increases, so does the tick, and it shifts over to the right. As the price decreases, the tick shifts over to the left. So, on this horizontal axis, if we move over to the right, it's moving over to positive infinity, and if we shift over to the left, it's moving towards negative infinity. On the vertical axis, we'll plot liquidity. When liquidity is high, the height of this purple rectangle is also high, and as we decrease the liquidity, the height of this purple rectangle decreases. Right now, the current tick T is below the lower tick T of A. As the price increases, the tick moves over to the right, and now this current tick is in between our position between the price ranges T of A and T of B. As the price increases, the current tick moves over to the right, and when the current price crosses over the upper price P of B, this tick goes outside of our liquidity position. Furthermore, we can color this purple rectangle with red for token X and blue for token Y. First, notice that when the current price is above the upper price range P of B, this liquidity position will all be in token Y. The amount of token Y in between this price range is 214, and the amount of token X is 0. So on this graph, we can say that when the current tick is above the upper tick T of B, then all of this liquidity will be in token Y. And when the current price is below the lower price range P of A, on this graph over here, we can see that the position between P of A and P of B consists only of token X, and the amount of token Y in this position is 0. So on this graph over here, we can represent this as all of this liquidity being only in token X. As the price increases, the amount of token Y in this liquidity position increases, and the amount of token X decreases. And if we go the other way around, as the price decreases, the amount of token X in this position increases, and the amount of token Y decreases. In the previous video, we learned how to visualize a single position on the liquidity price graph. On the horizontal axis, we map the price, or the tick, and on the vertical axis, we map the liquidity. On the left, you see some constant product curve of the concentrated liquidity for several positions. And for different positions, I've highlighted them in different colors. For example, take a look at this constant product curve with a low liquidity. The liquidity is only provided within these price ranges, so the part that is highlighted in purple represents the price range where this liquidity is positioned. The same goes for this light blue position, this orange position, and this lime green position. Let's start by reviewing what a single position will look like on the liquidity price graph. So we're focusing on this single position. This position provides a liquidity between these two price ranges, P of A2 and P of B2. And on the liquidity price graph, you can see that the position is displayed over here in orange. As I increase the price, you can see that the current tick moves over to the right, and when the current tick overlaps the lower price range, this liquidity becomes active. And when this liquidity becomes active, I've highlighted this active liquidity in bright purple. As we move the price along this position further, Currently, this orange position is active, and as the price increases, the current price goes outside of this position, and there is no active liquidity anymore. So that's a review of a constant product curve when a liquidity is active for a single position. Let's now consider the case when there are multiple positions. What does the curve of the active liquidity look like? And what does the liquidity price graph look like when we have multiple positions? So to begin with, I'm going to first show you where the positions are on this liquidity price graph. Here we have the position for the concentrated liquidity curve in purple over here. Next, we have the one in bright blue. We've already seen the one in orange. And here's the one in lime green. Showing all of them together, it looks like this. The liquidity for these individual positions are all overlapped. To show them correctly on the liquidity price graph, we need to stack them up. And here's what we get when we stack all the liquidity up. So you can see over here that on top of the purple position, we stack up the green position. And over here, all three positions overlap: the purple, the blue, and the green. Let's see what happens to the constant product curve of the active liquidity as we increase the price. As we increase the price, this tick will swing from left to right. So as we increase the liquidity, you can see that the first position, the one in pink, becomes active. So the active liquidity will only be this position. The curve of the active liquidity matches the curve of the concentrated liquidity for this purple position. And as we increase the price, next we see that there are two positions that are active now. And by active, I mean that the current price is within some price range that is set by a position. And here we have two positions that are in range of the current price. We have the position in purple that's active, and we also have the green position that is active. The total liquidity that can be utilized at this current price is a sum of the liquidity of the purple position and the green position. And the resulting constant product curve is displayed in bright purple. Notice that this bright purple curve is greater than both the curve for the purple position and the curve for the green position. Okay, as we swing the price further, next there are three active positions: purple, bright blue, and lime green. We sum up the liquidity for these three active positions, and the resulting liquidity is displayed in this bright purple curve. And again, this constant product curve is greater than any of the individual constant product curve: the one for green, the one for bright blue, and the one for purple. Also note that for this narrow price range where three positions are active, tokens from this green position, the tokens from this blue position, and the tokens from this purple position are all utilized for a swap. And as we increase the tick further, now the purple position becomes inactive since the current price is above the upper price range of this purple position, and the total active liquidity has decreased. And as the price increases, the tick swings over to the right. Now this green position has become inactive. As the price increases further, the only active position is this blue position. And as the price increases further, there are no longer any position that is active. So we looked at how each individual position stack up on this liquidity price graph. Another way to look at this is to just look at the shape of the total liquidity, and to the right of the current tick, all of the liquidity will be in token X, and to the left of the current tick, all of the liquidity will be in token Y. So I'm going to remove the highlight for these individual positions. Now you can see that to the right of the current tick, liquidity is all in token Y. As the price decreases and the current tick shifts over to the left, you can see that to the right of the current tick, liquidity is in token X, and to the left of the current tick, liquidity is in token Y. As the price decreases, the tick moves over to the left, more of the liquidity is converted to token X, and when the current tick is below the price range of all of the positions, all of this liquidity will now be in token X. Let's look at a real-world example of what the liquidity price graph looks like. And if you want to follow along, you can go to app.uniswap.org and then click on Explore. For this example, I picked the pool WEF USDT. And the reason why I picked WEF USDT is because WEF is token 0 and USDT is token 1. In the previous video, when we looked at the liquidity price graph, to the left of the current price, liquidity is all in token Y, and to the right of the current price, liquidity is all in token X. Here we'll say that token 0 is token X and token 1 is token Y. So in this example, token X will be WEF and token Y will be USDT. And what you see over here on the bottom is the liquidity price graph of USDT and WEF. As we swing the cursor from left to right, you'll see that this price will increase. So as I move the price to the right now the price of 1 WEF is 3,146 USDT. And as I swing it over to the right, the price of 1 WEF in terms of USDT increases. Another thing to notice is that this weird shape of the liquidity price graph. This graph represents the liquidity at each price, and at each price, liquidity is calculated by stacking up all of the position that overlaps with the price. Another thing to note is that at the current price, so if I zoom in, you can see that at the current price, liquidity is partially in USDT and partially in WEF. To the left of the current price, all of the liquidity is in USDT. Again, remember that in this pool, USDT is token Y, or token 1. And to the right of the current price, liquidity is all in WEF. And again, in this pool, WEF is token 0, or token X. So in summary, what we see here is that as we move the cursor from left to right, the price increases, and to the left of the current price, all of the liquidity is in token Y, in this case USDT, and to the right of the current price, liquidity is all in token X. In this case, this is WEF. There are several important contracts that you need to know to interact with Uniswap V3. And these contracts are split into several repositories. We have B3 Periphery, B3 Core, Swap Router Contracts, and Universal Router. Inside the repository B3 Periphery, the most important contract that you'll need to remember is called Non-Fungible Position Manager. This is a contract that will manage your position when you add and remove liquidity and to collect fees. The two important contracts inside the B3 Core repository are Uniswap V3 Factory Contract. This will deploy the Uniswap V3 Pool Contract, and this Uniswap V3 Pool Contract is a contract that holds onto 2 tokens, adds, removes liquidity, and it's also the contract that you'll be able to call swaps on. Now, similar to Uniswap V2, this pool contract is a low-level contract, and to interact with it, you need another contract, similar to Uniswap V2 where we had the Uniswap V2 pair contract and the Uniswap V2 router contract. Also in Uniswap V3, we have the Uniswap V3 pool contract and some other router contract. The main router contract that we'll be looking at is called Swap Router 02. This contract is inside the repository Swap Router Contracts. Now this Swap Router 02 contract has been upgraded to another contract inside the repository Universal Router. This Universal Router contract is a more comprehensive contract that will allow you to swap between Uniswap V2, V3, and some NFTs. But in this course, we won't touch on this Universal Router contract. Instead, we will look at Swap Router 02. Okay, let's take a look at how the different contracts connect to each other and what are some important functions that you'll need to remember. We will start from Uniswap V3 Factory contract. This contract is used to deploy the Uniswap V3 Pool contract. To deploy a contract, the user will call the function called createPool, and inside the Uniswap V3 Factory contract, it will deploy the Uniswap V3 Pool contract. Inside the Uniswap V3 Pool contract, the important functions that we need to remember are mint, burn, collect, swap, and flash. Mint and burn are used to add and remove liquidity. When the function burn is called inside the Uniswap V3 Pool contract, it doesn't actually send the tokens back. All it does is it removes the position. To collect swap fees and to also actually remove the tokens, we need to call the function called collect. There's also a low-level function called swap, and if you wanted to get a flash loan, you can also call the function flash. Most of these functions are low-level, and when these functions are called, it will call back into message sender. So this usually means that to call these functions, the caller must also be a smart contract. For example, the function mint to add liquidity to Uniswap V3 Pool contract will have a callback function that will call back into message sender. Again, this means that the caller of the function mint must be a smart contract. The easiest way to add liquidity to a Uniswap V3 Pool contract is to use the contract called Non-Fungible Position Manager. This contract will call the function mint on Uniswap V3 Pool contract, and Uniswap V3 Pool contract will call back into this Non-Fungible Position Manager. By using this contract, the liquidity that we add to Uniswap V3 Pool contract will be represented as a ERC721. To remove a position from Uniswap V3 Pool contract, the Non-Fungible Position Manager will also call the function burn, And to collect fees, the non-fungible position manager will also call the function collect on Uniswap V3 pool contract. A liquidity provider can call the functions mint, increase liquidity, decrease liquidity, collect, and burn on the contract non-fungible position manager. Mint is called when a user wants to add liquidity to a position for the first time. If this user wanted to increase liquidity to the same position, then they would call the function increase liquidity. If they wanted to decrease the liquidity to this same position, then they would call the function decrease liquidity. Now, similar to the function burn inside Uniswap V3 pool contract that doesn't actually send the tokens back, it just removes the position, the function decrease liquidity behaves in a similar manner. When this function is called, it doesn't actually send the tokens back. All it does is it decreases the liquidity from the position. To actually remove the tokens, and to also collect swap fees, we must call the function collect. And lastly, to burn this NFT, the user will call the function burn. Okay, so there are two other low-level important functions inside Uniswap V3 pool contract. Let's start with Flash. Flash is used to get a flash loan from Uniswap V3 pool contract. Since the amount that is borrowed must be paid in the same transaction, this Flash must also be a smart contract. This contract is not part of Uniswap V3 protocol. This is a contract that the developer writes and then deploys, and to get a flash loan, this smart contract will have to call the function flash on Uniswap V3 pool contract. Okay, the last low-level function is swap. This is used to swap tokens. Remember that in Uniswap V2, when the low-level function swap is called on Uniswap V2 pair contract, before the swap is done executing, we'll have to manually send the tokens into the pair contract. The function swap inside Uniswap V3 pool contract executes in a similar way. When this low-level function swap is called, it will call back into message sender. And inside the callback, we'll have to send the tokens to the Uniswap V3 pool contract. So the only way that this low-level function swap can be called on Uniswap V3 pool contract is by another smart contract. There are several router contracts that can call into Uniswap V3 pool contract. The router contract that we'll take a look at is called swap router 02. And this router contract will call the low-level function swap on Uniswap V3 pool contract. For a user to execute a swap on the swap router 02 contract, they can call the functions exact input single, exact output single, exact input, and exact output. Exact input single will swap with a single pool, and it will try to swap all of the tokens that the user sent. Exact output single will also swap with a single pool contract. This function is called by the user when the user wants some exact amount of token out. For example, let's say that we have DAI WEF pool, and the user wants exactly 1 WEF, and the maximum amount of DAI that they're willing to spend is 3000 DAI. Then they will call the function exact output single and tell swap router 02 contract that they want exactly 1 WEF and they're willing to spend 3000 DAI. The functions exact input and exact output work in a similar manner to the functions exact input single and exact output single. The difference is that they swap between multiple pools. For example, if you wanted to trade from WEF to DAI and then from DAI to MKR, that's a multi-hop swap, so it will involve multiple Uniswap V3 pool contracts. So in this case, the user will call either exact input or exact output. How do you get the spot price directly from Uniswap V3? For example, how would you get the price of ETH in terms of USDC from a Uniswap V3 contract? To get the spot price, you'll need to look at the contract called Uniswap V3 pool. This contract has a struct called slot0, and it is stored as a state variable. Inside the struct, there are two datas that we need to get to calculate the spot price. The two datas that we can use to calculate the spot price are the square root price x96 and the tick. Knowing either one of them, we'll be able to calculate the spot price. We'll take a look at an example later. Here I want to briefly explain why this struct is called slot0. The struct is called slot0 because all of this data goes into the 0th slot in the storage. As a quick review, in EVM, when you declare a state variable, these state variables are stored in different slots. Each slot can store up to 32 bytes. And the struct is called slot0 because all of this data fits inside 32 bytes, and all of this data is stored in the 0th slot of the storage. And we can see over here that the first state variable that is declared inside this smart contract is called slot0. So in this state variable, all of this data is stored. So that is why it is called slot 0. And the main reason why all of this data is stored in slot 0 is to save gas. Okay, with that said, let's now take a look at a real-world example of square root price x96 and tick. We'll look at the Uniswap V3 pool contract for WEF USDT. So I'll scroll down and I'm inside Etherscan. I'll click on read contracts and then scrolling down, I'm looking for a function called slot 0. So there it is. Click on this and then hit on query. And you see over here that the tick is minus 195,301 and the square root price x96 is this big number. In the following videos, I'll explain the math for how to use this tick and square root price x96 to calculate the price. In this video, I'll explain the math equation for how to calculate the price given that we know the tick. We'll say that x represents token 0 and y represents token 1. P will be the price of x in terms of y. A simple example is, think about x as being WEF and y as being USDC. In this case, P will be the price of WEF in terms of USDC. In Uniswap V2, to get the spot price of token X in terms of token Y, what we had to do was get the amount of token 1 that is stored in the Uniswap V2 pair contract, and then divide by the amount of token 0 that is stored in the Uniswap V2 pair contract. However, in Uniswap V3, we can no longer do this. And this is because in Uniswap V3, it no longer keeps track of the amount of tokens that is locked inside the contract. Instead, it keeps track of the current price, and from the current price, if we know the liquidity and the price ranges, then we can calculate the amount of tokens that must be locked in those price range. But this is still a useful equation, knowing that the price P is equal to the ratio of token Y to token X, especially when we're dealing with decimal conversions. For example, let's say that X is WEF and Y is USDC. USDC has 6 decimals, and WEF has 18 decimals. So when we take the ratio, we're left with 10 to the 6 divided by 10 to the 18, which is 10 to the minus 12. And if you wanted to normalize this ratio to, let's say, 10 to the 18, then we'll have to multiply by 10 to the 12 to cancel out with the 10 to the minus 12, and then multiply by 10 to the 18. I'll explain more about decimal conversions when we actually write some code. Moving on, in Uniswap V3, the price is defined to be 1.0001 raised to the tick. So if you know the number for what this tick is, then we take 1.0001 raised to the tick to calculate the current price. Let's go over some examples of calculating the price, given that we know the tick. For this example, I'll use the tick that I got from WEF USDT pool. So in this contract, WEF is token 0 or token X, and USDT is token 1 or token Y. To get the price, I'll label this P. We'll do 1.0001 raised to the tick. Let's print this out and see what this number is. Print P. And here it is. Notice that this number is equal to 3.53 and so on, multiplied by 10 to the minus 9. We're getting the price of WEF in terms of USDT, and currently the price of beef is around 3,500 USD. So why isn't this number around 3,500? Instead, it's a really small number. The reason why we're seeing a small number here is because we haven't done the decimal conversion. As a review, we said P is equal to the ratio Y divided by X. And this is the price of token X in terms of token Y. In our case, we said that token X is WEF and token Y is USDT. WEF has 18 decimals, so 1 WEF is represented as 1 E18 or 10 raised to the 18. And 1 USDT has 6 decimals, so this is represented as 1 E6 or 10 raised to the 6. And now, when we look at the ratio of P equals Y divided by X, this will be the ratio of USDT divided by WEF. USDT has 6 decimals, so the numerator will also have 6 decimals for the ratio of P, and the denominator is WEF, so it will have 18 decimals. This whole ratio will have a decimal of 1E minus 12. And that is why we're seeing a small number here, because we're multiplying the price of WEF in terms of USDT by this number, 1E minus 12. If we remove these decimals from the price P, then we'll get a number that is closer to the market price. So from P, P is multiplied by 1E6 and then divided by 1E18. So to cancel out with the first 1e6, we'll divide by 1e6, and then to cancel out with the next 1e18, we'll multiply by 1e18, and then print it out, and we get that the price of one WEF in terms of USDT is around 3,531. Let's look at another example of calculating the price from the tape. And this time, we'll use the pool USDC WEF. So in this pool, USDC will be token 0 or token X, and WEF will be token 1 or token Y. In the last example, the pool was WEF for token 0 and USDT for token 1. In this example, its USDC is token 0 and WEF is token 1. And remember that the ratio P is equal to Y divided by X, and this is price of token X in terms of token Y. In this example, if we replace the X with USDC and Y with WEF, we get that P will represent the price of USDC in terms of WEF. For example, this P might be some number like 1 USDC equal to 0.0001 WEF. That number is a little bit hard to comprehend since when we think about the price of WEF, we think about it in the opposite terms. The price of WEF in terms of some stablecoin like USDC or USDT. So to get the price of WEF in terms of USDC, we'll need to flip this P. 1 divided by P will be equal to the ratio X divided by Y, and this will be equal to the price of WEF in terms of USDC. Okay, with that said, let's try to calculate the price of WEF in terms of USDC, given that we know what the tick is. Here's the tick that I fetched from the pool USDC WEF from this address. And the price P, again, will be equal to 1.0001 raised to the tick. And let's print this out. Print P. And we get a really large number. The current price of ETH in terms of USD is around 3,000 to 3,500. So this number is way off. And as I mentioned earlier, to get the price of WEF in terms of USDC, we'll need to do 1 divided by P. So let's do that. Print 1 divided by P, and then print it out, and we now get a small number, roughly 3.53 multiplied by 10 to the negative 9. The reason why this number is really small is because we haven't done the decimal conversion yet. So let's work through this out. 1 WEF has 18 decimals, 1 E18, and 1 USDC has 6 decimals, 1 E6. We said that 1 divided by P is the price of WEF in terms of USDC, and the ratio is given by X divided by Y. In this pool, token 0 or token X is USDC, and token 1 or token Y is WEF. 1 divided by P equal to X divided by Y is the ratio of USDC divided by WEF, and this is equal to 1E6 divided by 1E18. And this is equal to 1e minus 12. To remove this decimal, what we need to do is take 1 divided by P, and then we cancel out this 1e6 by dividing by 1e6, and then we'll cancel out this 1e18 by multiplying by 1e18. Multiply 1e18. Okay, let's print this out. Print, and then execute the code. And we get that the price of WEF in terms of USDC is roughly around 3,537. Remember that weird variable inside slot 0 called square root price x96? In this video, I'll explain what this is and how to use this to calculate the price. The square root price x96 is defined to be the square root of price P, this is obvious from the name, and then it multiplies by some factor called x96. Inside the code of Uniswap V3, this is called Q96. And Q96 is simply equal to 2 raised to the 96 power. To calculate the price P, given that we know what square root price x96 is, we first take this square root price x96, and this square root price P is multiplied by a factor of Q96, so we'll first divide this square root price x96 by Q96. After we divide this, we're left with square root price P. So to get back the price, we square this, and we get back P. And this is how we will calculate the price P, given that we know square root price x96. Let's look at another example of calculating the spot price in Uniswap V3. This time, we will calculate the spot price given the square root price x96. And for this example, I'll use the square root price x96 that I got from the WEF USDT pool. Remember that this square root price x96 is the square root of price multiplied by some factor, and inside the code of Uniswap V3 this is called Q96. So let's define Q96 in our Python code. Q96 is equal to 2 to the 96. To get the price, you'll say P is equal to, you'll first divide this square root P x96 by Q96. sqrt P times x96 divided by Q96. This will give us the square root of price. And to get the price, we square this. Okay, let's print out P. Print P. And again, we get a small number, 3.37 times 10 to the minus 9. We're getting a small number because we have not canceled out the decimals for WEF and USDT. So let's go back to the equation again. Price P is the ratio of token Y over token X. In this pool, WEF USDT, WEF is token X and USDT is token Y. So Y is USDT and X is WEF. Okay, how about the decimals? USDT has 6 decimals, 1E6, and WEF has 18 decimals, 1E18. So at the moment, this price will be the price of WEF in terms of USDT, and we also have these decimals, and that is why we're seeing a small number over here. And to cancel out these decimals, we need to first divide by 1E6, since here the price is multiplied by 1E6, and then we need to multiply by 1E18 to cancel out the division by 1E18. Okay, and let's print out the price again. And this time, we get that the price is equal to 3,378. One WEF is roughly 3,378 USD. Another useful math equation to keep in the back of your head is the conversion between square root price x96 and tick. So as a review, the price P is defined to be 1.0001 raised to the tick. And we also saw that given the square root price x96, we can calculate the price by using this equation. Square root price x96 divided by q96, and then squaring this. Now I want to explain, given that we know the square root price x96, how do we calculate the tick? And this math is used inside the smart contract of Uniswap V3 during a swap to calculate the current tick given the square root price x96. So to calculate the tick, given that we know the square root price x96, we will first take the log of both sides. So I'll copy this equation and then paste it here. Taking the log on both sides of the equation, on the left side, this tick comes out, and on the right side, this 2 will come out. Next, I'll divide both sides of the equation by log of 1.0001. Dividing this side of the equation by log of 1.0001, this will simply be 1. And dividing the right side of the equation by log of 1.0001, we will have this. And now we have an equation for the tick. You don't have to remember this equation, but if you need to find the tick, and given that you know the square root price x96, you can use this equation to calculate the tick. For our final example of playing around with the spot price of Uniswap V3 using Python code, we will calculate the tick given that we know the square root price x96. And for this example, we'll be using the USDC WEF pool. First, I'll define the constant Q96. Q96 is equal to 2 to the 96. Next, I'm going to copy paste the square root price x96 and the tick that I got from this contract address. Okay, here they are. So what we'll do next is we'll calculate the tick from this square root price x96, and we'll double check that the tick that we calculated matches this tick. This is the actual tick that is stored in the contract over here. So tick, let's name this t, is equal to 2 times math.log, and inside this log we need to do square root px96 divided by q96, and then outside of this math.log we need to divide this by math.log 1.0001. Okay, so that's the tick that we calculated given that we know square root price x96. Let's print this out and compare with the actual tick that's over here. So print t. And the tick that we calculated is 195,402. The actual tick is also 195,402. Here's an exercise to get the spot price from our Uniswap V3 pool contract. The pool contract is USDC WEF. And in this exercise, I want you to get the price of WEF in terms of USDC and then return the price with 18 decimals. One thing that might be useful for you for this exercise is to use the library fullmathmoldib. What this function allows you to do is multiply 2 uint256 and then divide by another uint256 without any overflow. This is a useful function when you multiply square root price x96 with square root price x96. Okay, let's go over the solution. First, let's review what price we need to return. Do we need to return the price y divided by x, or do we need to return the price x divided by y? So, if we have P, this is the ratio of token y divided by token x. And in our case, token x is USDC and token y is WEF. So, this ratio will be WEF divided by USDC. Remember that this ratio represents the price of token x in terms of token y. In our case, this x is USDC and this y is WEF. So once we calculate the price based on the data that is stored in slot 0, we'll get a price of USDC in terms of WEF. But what we actually want to return here is the price of WEF in terms of USDC. So again, to do this, we'll need to flip this ratio. What we need to calculate is 1 over P. This will be x divided by y. And this will be the ratio of USDC over WEF. And when we calculate this 1 over P, we'll get the price of WEF in terms of USDC. So what we need to find is 1 over P. Before we do that, let's also calculate how many decimals this 1 over P has. If we look at P has, Y will be WEF. WEF has 18 decimals, so this will be 1E18. And then on the bottom, we have USDC. USDC has 6 decimals, 1E6. This is 1E12 decimals. For 1 over P, we need to flip the decimals. So 1 over P has, on the numerator, we'll have 1E6, and on the denominator, we'll have 1E18. And this will be minus 12 decimals. So far, we know that we need to calculate 1 over P to get the price of WEF in terms of USDC. And we also know that 1 over P has 1E minus 12 decimals. Next, let's think about how we will get this price P from slot 0. Inside slot 0, there's a data called square root price x96, and we'll need to use this to calculate the price P. Let's start by reviewing what square root price x96 represents. Square root price x96, and we said that this will represent the square root of price P, and this is multiplied by a constant called Q96, and this Q96 is simply 2 to the 96. To get this price that represents P, we need to take the square of square root price x96. So this will be square root price x96 times square root price x96. And this will be equal to 2 of these. 1 over here, and then multiply by the same thing again. And when we do this, we'll get the square root of P times the square root of P, which is simply equal to P. This is the price that we wanted to get. And then it's multiplied by 2 of Q96 times Q96 again. Each of these Q96 has 96 bits. And here we have 2 of these, so this will be 2 times 96 bits. And this is equal to 192 bits. So let's do a little bit of math to see how big the price can be before this number overflows. Just by Q96 times Q96, we use up 192 bits. uint256 has 256 bits minus 192 bits, and this is equal to 64 bits. So this means that we have 64 bits to represent this price P. Now imagine that we want to return 18 decimals. So out of the 64 bits that we have, 2 to the 64, we're going to use 1E18, 18 decimals, to represent the decimal part of the price. And if you punch in the numbers into a calculator, we get that this is approximately equal to 18. And what this means is that if we were to return the price with 18 decimals, then the maximum price that we can return is roughly 18. For example, currently the price of beef is above 3,000. And this means that when we do this calculation, we won't be able to return the price of beef. So when we do this calculation to get this P out, before we do this, we need to somehow make this part of the multiplication smaller. One way we can do this is by saying square root price x96 divided by q96 times square root price x96 divided by q96. And this will give us square root price p times square root price p, so this will be equal to p. The problem with this approach is that because we're dividing by q96, if this square root price x96 represents a really small number, then this will round down to 0 and the price will be inaccurate. Okay, to solve these two problems, one is the problem that if we did this, then the price might overflow, and if we took this approach, then the price might be incorrect. To solve two of these problems, we're going to use the library fullmath.moldib to calculate the price p accurately without any overflow. So you'll say price is equal to fullmath.moldib. The square root price x96 is stored inside slot 0 dot square root price x96, and we'll multiply it by itself, slot 0 dot square root price x96. And then notice here that when we multiply square root price x96 by itself, we get two of these q96. We'll remove one of them by dividing by q96. So right now this price represents the p that we discussed over here. What we actually need to return is 1 over p. So that would be the next step. Currently, the price is equal to square root of p times q96 times square root of p times q96. So that's this part. And then we divide this by q96. And again, by using this moldiv function, we can multiply 2 un256 and then divide by another un256 without any overflows. Okay, so this will be equal to, we have a square root price p over here and a square root price p over here, so this will be p. And then we have 2q96 as a numerator and 1q96 as a denominator. So we're left with 1q96. So this is what this variable price represents, the ratio of token y divided by x and multiplied by q96. What we need to return is 1 over price. So this will be equal to 1 times q96. Now, when we do this 1 over price, notice that we're doing 1 divided by a large number. So in Solidity, this is going to return 0 because divisions round down. So what we need to do is multiply this 1 divided by price by a large number so that it doesn't round down to 0 when we divide by p times q96. So I'll type price is equal to 1 divided by price. 1 divided by price will represent this number over here. First, I'll cancel out this q96 by multiplying the top by q96. And then, remember that when we said over here that 1 over p has decimals 1e minus 12. To cancel out this 1e minus 12 decimals, I'll multiply the top by 1e12. And lastly, for this exercise, we want to return the price with 18 decimals. So we'll multiply this by 1e18. Okay, and that completes the exercise. Let's execute the test. Inside my terminal, I'll first set up an environment variable for the fork URL. And then to execute the test for this exercise, I'll type forge test -- fork URL, and the path to the test is match path test Uniswap V3 exercises Uniswap V3 spot price .test.sol. And then we'll print out the console logs by typing -bbb. Okay, and the test passed. The price that was logged is 3.28 times 10 to the 21. We said that we wanted to return this price with 18 decimals. 21 minus 18 is 3. So the spot price given by the USDC ref pool on Uniswap V3 is currently roughly 3,284 USDC per 1 ref. In Uniswap V3, there are several equations that we need to derive to answer questions like the amount of token X and amount of token Y between a price range, and other questions like the amount of token X or Y that we'll get for a swap. The first two equations that will be helpful to know when we're doing math with Uniswap V3 equations is rewriting the amount of token X and the amount of token Y in terms of the liquidity L and the price P. To begin with, we have the constant product equation, X times Y equals L squared. The spot price P in a constant product curve is given by the amount of token Y divided by the amount of token X. In Uniswap V2, it is easy to know the amount of token Y and the amount of token X in the contract. From these, we can easily figure out what the spot price is. However, in Uniswap V3, this is no longer true. Because there may be multiple positions in different price ranges, we cannot just simply take the amount of token Y and the amount of token X in the contract to figure out what the spot price is. Instead, in Uniswap V3, it keeps track of the current price and the current liquidity. And from these, we can figure out what the amount of token Y and what the amount of token X should be in a price range. To find the amount of token X given the liquidity and the spot price P, first I'm going to copy these two equations and then paste it here. And we can write X in terms of L and P if we do L squared divided by P. So I'll take L squared and then divide this by P. And this will be equal to L squared is X times Y and P is Y divided by X. The Y on the top and the Y on the bottom cancel out, and the X comes to the top, so we will have X squared. So I get L squared divided by P is equal to X squared. I will take the square root of both sides of the equation. On the right, we have square root of X squared, so this is simply equal to X. And if I take the square root of the left side of the equation, the top will be a L, and the bottom will be a square root of P. So we get, if we know the current liquidity L and the price P, then we can calculate the amount of token X. L divided by square root of P is equal to X. Next, we'll do something similar to get an equation for Y in terms of L and P. So I'll copy this equation and then paste it here. If we take L squared times P, then we'll get X times Y times Y divided by X. The X over here cancels out with the X over here, and we're left with Y squared. So we have L squared times P is equal to Y squared. Again, we'll take the square root of both sides. On the right side, square root of Y squared is simply equal to Y. And on the left side, square root of L squared times P is equal to, well, the L is going to come out, and we can remove this power of 2. And we're left with L times the square root of P. So given that we know the liquidity and the price, we can calculate the amount of token Y, and this is equal to L times the square root of P. We need one more equation to answer important questions, like the amount of token X and the amount of token Y that we need between the price ranges P of A and P of B to provide this much amount of liquidity. Or we might ask the question, we have this much amount of token X, and we want to provide liquidity between P of A and P of B. So what is the amount of token Y that we need to provide? To answer questions like these, we need the equation for the curve of the real reserves. So let's say that we have the curve of the virtual reserve in green. This is simply the constant product curve of the concentrated liquidity. The curve of the real reserve, shown in orange, is derived simply by taking the curve of the virtual reserve, shifting it over to the left and to the bottom. We shift this green curve over to the left until the price P of B intersects with the y-axis, and then we move the green curve down until the price P of A intersects with the x-axis. And this represents the curve of the real reserves. The curve of the real reserve is described by this equation. In this video, I'll explain how to derive this equation. As a starting point, let's say that we have the constant product curve, X times Y equals L squared. In a concentrated liquidity between the price ranges P of A and P of B, the amount of token X and the amount of token Y splits into two parts. For the amount of token X, we have the real amount of token and some virtual amount of token. And likewise for the amount of token Y, it splits into two parts, the real amount of token Y and the virtual amount of token Y. We can express this as a mathematical equation. The amount of token X that is needed to create this X times Y equals L squared splits into two parts, the real amount plus the virtual amount. And likewise, the amount of token Y splits into two parts. The amount of token Y that is needed to satisfy this equation X times Y equals L squared splits into two parts, the real amount of token y plus the virtual amount of token y. And now we can rewrite x times y. X is equal to the real amount, x sub r, plus the virtual amount, x sub b. And likewise, y is equal to the real amount, y of r, plus y of b. And since x times y equals L squared, this part must also be equal to L squared. To find the curve of the real reserves, we need to find what this value xb and yb is equal to. And to find the values x of b and y of b, we will use these two equations. Rewriting x in terms of the liquidity L and the price P, and rewriting y in terms of the liquidity L and the price P. Let's start by solving for x of b. Now to simplify our problem, we take this equation and set x sub r equal to 0. So we'll consider the case when x sub r, the real amount of token x, is equal to 0. On the graph, we will have the curve of the virtual reserve, and the real amount of token x is equal to 0. If the real amount of token x is greater than 0, then we will have some amount of x over here. Since it is equal to 0, the real amount of token x will be over here. And in this case, we still need to satisfy the constant product equation x times y equals L squared. So the amount of token y, such that the point x, y will be on this green curve, is over here. So y must be over here. This vertical line in green is the virtual amount of token y, and this vertical blue line is the real amount of token y. Okay, so when the real amount of token x is equal to 0, on the curve of the virtual reserve, the point xy must be over here. From here, there are two approaches that we can take to solve for x of b. The first one that I'll show you is the geometric approach, and next I'll show you the algebraic approach. So, when the real amount of token x is equal to 0, the point xy will be over here. When xy is over here, the amount of token x will be this much amount, which is equal to x sub b. And the amount of token y must be equal to this vertical blue line plus this vertical green line, which is equal to yr plus yb. Okay, notice that x is equal to xb. And now we already know what xb must be equal to. Going back up, we can use this equation to figure out what x sub b is. So going back down, x is equal to x sub b, and using the equation above, we rewrite this x in terms of the liquidity and the price. The liquidity is L, and the price at this point is P of b. So x sub b will be equal to L divided by the square root of P of b. Another approach we can take is by solving this equation. When x sub r is equal to 0, the equation for the constant product curve, xr plus xb times yr plus yb, since x sub r is equal to 0, this equation simplifies to x sub b times yr plus yb. And this must be equal to L squared. Okay, so we can solve for x sub b by taking this equation and then dividing by yr plus yb. So x sub b is equal to L squared divided by yr plus yb. Okay, and then going back up, we can use this equation to rewrite yr plus yb in terms of liquidity and price. The liquidity is the same, L. How about the price? The price when y is equal to yr plus yb will be P of b. So this price will be P of b. Okay, so we can now rewrite the bottom part of this equation. Replace this with L times the square root of P of b. Now notice that we have a L squared on top and we have a L on the bottom. These two cancel out and we're left with x of b is equal to L divided by the square root of P of b. Okay, so these were two approaches that we can take to figure out what x of b is. Next, we'll do something similar to figure out what y of b is. Okay, to find y of b, we'll go back to this equation. We'll consider the case when the real amount of token y of r is equal to 0. So going back, when the real amount of token y of r is equal to 0, so this will bring y of r over here. And when y is over here, the total amount of token x, this will be x of r plus x of b, must be over here, so that the point xy will be on this curve of the virtual reserve. When we add the real amount of token x with the virtual amount of token x, and we also add real amount of token y, which is 0, with the virtual amount of token y, the point xy must be over here on this green curve. And to find out what y of b is equal to, Again, we'll take two approaches, geometric approach and algebraic approach. At this point, this x is equal to some real amount of token x with the virtual amount of token x, x sub r plus x sub b. The amount of token y is also the same, however, since the real amount of token y is equal to 0, this will simplify to y equals to y of b. Now, using this equation again, we can rewrite y in terms of L and P. So when y is equal to y of b, what is the price? The price is P of A. So at this point, y is equal to, y is all in virtual amount, so this will be y of b, and this is equal to, rewriting in terms of liquidity L and the price, this is equal to L times the square root of P of A. Another approach that we can take is the algebraic approach. So starting from this equation, I'll paste it here. Starting with this equation, we know that y bar is equal to 0, so we can simplify this equation. Y bar is equal to 0, so we can remove this, and we get x of r plus x of b times y of b is equal to L squared. Okay, so we're solving for y of b, and to do this, we'll divide both sides of the equation by x of r plus x of b. So we get y of b is equal to L squared divided by x of r plus x of b. Again, we'll use this equation to rewrite x in terms of liquidity and price. So at this point, we have x is equal to some real amount of token x plus the virtual amount of token x. And the price at this point is P of A. So we can replace the bottom part of this equation with L divided by the square root of P of A. And this is equal to, the L squared on the top cancels out with the L on the bottom, and the square root of P of A comes to the top. And we get that y of b is equal to L times the square root of P of A. So those are two ways to find y of b. Okay, now that we figured out what x of b and y of b is, the last step is to figure out how do we get this orange curve now that we know how to get this equation for the green curve. To draw out the curve of the real reserve shown in orange, what we have to do is move the curve of the virtual reserve shown in green to the left and bottom. What we're doing here is we're moving this green curve over to the left so that when x sub r is equal to 0, this will match the x-axis equal to 0. And by shifting this green curve to the bottom, we're making it so that when the real amount of token y bar is equal to 0, it will match on the y-axis the point where y equals 0. To show you this, let me try dragging this green curve. So we'll shift this green curve to the left so that when xr is equal to 0, this will match the point x equals to 0. Okay, next I'm going to move this curve to the bottom so that when y bar is equal to 0, this will match the point y equals to 0. And you can sort of see that the two curves overlap. The curve of the virtual reserve and the curve of the real reserve overlap. And this is how the curve of the real reserve is derived. We take the curve of the virtual reserve and slide it over to the left. The amount that we'll need to slide is x of b. And then next we slide it down. The amount that we'll need to slide down is y of b. When we do this, we will get the curve of the real reserves. Remember these equations where we can calculate the value of x and y given that we know what liquidity L and price P are. We'll use these two equations to answer two questions. The two questions that we'll answer in this video are, given the liquidity L and the price P, what is the amount of token X between P and P of B? On the graph, we have the current price P and the upper price P of B. What is the amount of token X that we need so that the current price can go all the way up to P of B? And the other question is, what is the amount of token Y between price P and P of A? From the current price P to the lower price range P of A, what is the amount of token Y that we need so that the price can move from the current price P all the way down to the lower price P of A? Well, we can easily find the answers to these two questions by using these two equations. So let's start with the first question. What is the amount of token X between the price P and P of B? In other words, what we're asking here is, what is this length of this red line? And to answer this question, all we have to do is figure out what the X component when the price is at P. So what is the X value over here? And what is the value of the X component when the price is at P of B? So the X will be over here. Taking these two difference, we'll get the length of this red line, which will be the value of X. Let's start by figuring out what the X component is for the current price P. So we have the current price P here, and the X component will be over here. Well, using this equation, that we can rewrite X in terms of liquidity and the price, the X over here will be equal to L divided by the square root of current price P. We're simply using this equation over here to rewrite X. And then we'll do the same when the price is at P of B. When the price is at P of B, the X component will be over here. And again, using this equation, the X value over here will be L divided by the square root of P of B. When we apply this equation, in the case of the price P of B, here we'll need to replace this P with the price P of B. So that is why we have L divided by the square root of P of B. So now that we know what the X values are for when the price is at P and when the price is at P of B, we can now figure out what this distance of the red line is. So X is equal to, X will be this length, and we can get this length by taking the difference of these 2 points. At the current price P, X is equal to L divided by the square root of P. When the price is at P of B, the X component is equal to L divided by the square root of P of B. Taking the difference between these 2 points will give us the length of this red line, which is equal to X. So the amount of X between P and P of B is given by this equation. And now we can do something similar to answer the question, what is the amount of Y between P and P of A? The value of this Y is the length of this blue line. And we can get the length of this blue line by figuring out what the Y component is for the current price P and what the Y component is for price P of A. At the current price P, to figure out what the Y component is, all we have to do is apply this equation. So Y will be equal to L times the square root of P. And then we do the same to figure out what the Y component is for price P of A. To figure out the Y component when the price is at P of A, we would do L times the square root of P. P over here is P of A. So this will be equal to the Y component when the price is at P of A is equal to L times the square root of P of A. Now we can figure out what the value of Y is. The Y will be the distance of this blue line, which is the difference between the 2 points, L times the square root of P minus L times the square root of P of A. Y is equal to L times the square root of P of A. This would correspond to the Y component at the price P minus L times the square root of P of A. This is the Y component at the price P of A. Taking the difference, we get the length of this blue line. And this answers our second question, what is the amount of Y between the current price P and P of A? The answer is given by this equation. So far, these 2 equations use P, P of A, and P of B. But sometimes it's difficult to remember what P, P of A, and P of B are. For example, when we use these equations, do I have to remember that P of B is always greater than P of A? So to make these 2 equations easier to remember, let's generalize these 2 equations. So I'll copy this and then paste it here. Next, I'll replace the terms P, P of A, and P of B with terms that indicate whether the price is higher or lower. So let's start with this equation. For the term P and P of B, in this case, which is the lower price? This will be the current price. So I'll rename this P with P lower to indicate that this is the lower price. And in this case, between P and P of B is the higher price. So I'll rename P of B to P of upper to indicate that P upper is a price that is greater than or equal to P lower. Okay, and we'll do the same for this equation. Between P and P of A, if you look at this graph, which is the higher price and which is the lower price? Well, in this case, P is greater than or equal to P of A, so I'll rename this P to P upper. And then, between P and P of A, the lower price is P of A, so I'll rename PA to P lower. So all we did was we took these 2 equations and then relabeled the terms P, P of A, and P of B with terms that indicate whether the price is high or low by renaming them as P lower and P upper. And now we have 2 equations that tell us the amount of token X and amount of token Y between two price ranges, P lower and P upper. So now, using these two equations, we can answer questions like, what is the amount of token X between the price ranges P of A and P of B? Before we ask the question, what is the amount of token X between the current price P and the upper price P of B? But now, using this equation, we can ask a more generalized question, what is the amount of token X between two price ranges P of A and P of B? The answer is given by the length of this red line, and this length can be calculated by applying this equation. So, for P lower, you put P of A, and for P upper, you put P of B. And likewise, using this equation, we can ask the question, what is the amount of token Y between the price ranges P of A and P of B? The answer is the length of this blue line, which is given by this equation. Another question that you might have is, given the current price P and the current liquidity L, what is the maximum amount of token X that you can put in before this current price goes below P of A? And again, we can answer this question by using this equation. For P upper, you put the current price, and for P lower, you put P of A. And likewise, you can ask the question, given the current price P, what is the maximum amount of token Y that you can put in before this current price exceeds P of B? And again, we can answer this question by using this equation. For P upper, we will put P of B, and for P lower, we will put the current price. The function that actually executes the swap inside Uniswap V3 is inside the contract called Uniswap V3 pool, and the function is called swap. Before we do a code walkthrough of this function, I'm going to first give you an outline of how this algorithm for the swap works. Let's start with the important inputs to the function swap. There are other inputs, but we'll focus on these three inputs. 041 tells the direction of the trade. If we're putting in token 0 and then getting out token 1, then 041 will be true. Otherwise, we're doing a swap, putting in token 1 and then getting out token 0. In this case, 041 will be equal to false. And then amount specified. This amount can either be positive or a negative number. And this tells either how much token the user wants to put in or how much token the user wants to get out of this swap. And then the square root price limit. The swap algorithm will continue to execute until this amount specified reaches 0 or the current price reaches the square root price limit. From these inputs, the algorithm first calculates the type of the swap. The two types of swaps are exact input and exact output. Exact input means that the caller specified the amount of tokens that they're going to put in. Exact output means that the caller specified the amount of tokens that they want out of the swap. And the way it is computed is by looking at amount specified. If amount specified is greater than or equal to 0, this means that the caller is willing to put in this much amount of token into the contract, so it will be a positive number, and this will tell Uniswap V3 that this trade is an exact input. For exact output, user is specifying that they want to get some amount specified amount of tokens out of the pool. The token is leaving the pool, so amount specified will be a negative number. Next, the algorithm runs a while loop to calculate amount in and amount out. We will come back to the details of how this loop calculates the amount in and amount out later. After this loop is done executing, the algorithm knows what the next liquidity is, the next square root price, the next tick, amount 0, and amount 1. Here we have plus and minus. Plus means that token is coming in, and minus means that token is going out. And at this point, it also knows what the swap fee is. From these values, the state variables for liquidity, square root price, tick, and fee growth are updated. Fee growth is a state variable that is used to track the amount of swap fees that were collected. From this plus minus amount 0 and amount 1, if this amount is a negative, then tokens are sent out. The swap callback is executed on message sender. So this means that message sender must be a smart contract, and at this point, message sender must send a token in to the Uniswap V3 pool contract. After the swap callback is done executing, the Uniswap V3 pool contract will check the balance for token in. Okay, so this is an outline of how the swap algorithm works. Now let's dig a little bit deeper and look at what the loop does to calculate amount in and amount out. The loop will continue to execute while the amount specified remaining is not equal to 0, and the current square root price is not equal to the square root price limit. So going back to the inputs, here we have amount specified, and this amount specified is used to set a local variable called amount specified remaining. Inside the loop, it's either going to add some amount or deduct some amount until this amount specified remaining is equal to 0. And the other input that we saw was the square root price limit. The current square root price will be kept in a local variable, and while this square root price is not equal to the square root price limit, the while loop will continue to execute. Inside the while loop, it's going to first get the next tick. The way it gets the next tick will be explained in another video. From the next tick, the square root of the price of the next tick is calculated. We'll call this square root p next. After the next square root price next is calculated, the algorithm calculates the amount in, amount out, and the fee between the two prices, the current square root price p and square root price next. And once that is calculated, the current square root price p is updated. Once you know what amount in and amount out are, next we need to update this amount specified remaining. And the way it is updated is different whether the trade is at exact input or at exact output. If this swap is at exact input, then amount specified is greater than or equal to 0. This is because the caller is specifying the amount of tokens that will come into the pool. From this amount specified remaining, which is greater than or equal to 0, we deduct the amount of tokens that must come in between the price ranges square root price p and square root p next. If the swap is at exact input, this amount calculated is interpreted to be the amount of token that will go out. Remember that for the amount of tokens that's going out, it is represented as a negative number. So from amount calculated, we minus amount out, the amount of token that's going to go out from the two price ranges, the current square root price p and square root p next. Okay, so let's take a look at what if the swap is at exact output. If the swap is at exact output, then amount specified will be less than 0. The user is requesting to take some tokens out. Token is leaving, so amount specified is less than 0. Again, this while loop is going to continue running until this amount specified remaining is not equal to 0. So to amount out specified remaining, we add the amount of token that is going out. And this amount out is calculated over here. We'll come back to how amount in, amount out fee and the next square root price p is calculated. So moving on, for exact output, next it calculates amount calculated. In this case, amount calculated means the amount of tokens that must come in. Since token is coming into the pool, this amount calculated will be a positive number. Once all of these are calculated, it's going to update the local variables inside the while loop to prepare for the next iteration of the while loop. It's going to update the local variables, liquidity, square root price p, tick, and fees. Once this loop is done executing, it's going to return to here. Return to this end of the loop. And among other things, the two variables that it's going to return is amount specified remaining and amount calculated. From these two variables, it will calculate the amount of token 0 to come in and go out, and amount of token 1 to come in and go out. Okay, so this is an outline of what the while loop does to calculate amount in and amount out. Next, let's take a look at how amount in, amount out fee and the next square root price p is calculated between the price ranges, the current square root price p and square root p next. To calculate the amount of token in and out and the fees between the price ranges, the current price p and the next price, square root p next, these are the inputs that we will need to pass, the two price ranges, the current liquidity, and amount specified remaining. Again, here remember that amount specified remaining can mean two things. If this number is greater than or equal to 0, then this means the amount of tokens that's coming in, and if it's less than 0, then it's amount of tokens that's going out. From these, we need to calculate amount in, amount out, and fee. So let's take a look at how it does this. The function that is getting called to compute the amount of in and amount of token out is called compute swap step. First, it needs to determine the type of swap. Is it an exact input or is it an exact output? If it is an exact input, then it needs to calculate the maximum amount of token ins that can come in between the current price P and the next price P target. Here, for the input, we passed in square root P next. But inside this function called compute swap step, this square root price P next is called square root P target. So we calculate the maximum amount of tokens that come in between the current price, square root price P, and square root P target. Next, once we calculate the maximum amount of token in, we can calculate the actual amount of token that will come in. And then it will calculate the next square root price. Okay, so these are the two calculations that are executed for exact input. For exact output, it's going to calculate the maximum amount of tokens that can go out between the price ranges √P and √P target. Based on the maximum amount of token out, next it's going to calculate √P next. So at this step, we know what the next square root price is. And from this, the algorithm calculates the amount in and amount out. From the amount in that is calculated, next it's going to calculate the fees. And once that is done, the result of the calculation is returned to this step. So at this step, we will know what the next square root price P is, amount in, amount out, and the swap fees. For the last part of this video, I'm going to explain a little bit more about this step over here. And to explain the algorithm over here, for this example, we'll say that this swap is a 0 for 1. Token 0 is coming in and token 1 is going out. Let's say that some amount of token is coming in and some amount of token out is going out. And the current price will be the square root of P. The target will be square root of P target. By putting in some amount of token X and then getting out some amount of token Y, this will decrease the price. It will shift the price from over here, from the right to the left. Okay, so over here, I said max amount in and max amount out. What do this look like visually when we represent it on this bar graph? Let's start with max amount in. Max amount in is the maximum amount of token that can come in before the current price, square root P, reaches square root P target. Visualize that as the tokens come in, this will push the current price from right to left, and the liquidity will be more in token X and less in token Y. And this max amount in is the maximum amount of token that can come in for the current price to reach the price target, square root P target. Max amount out is something similar. Max amount out is the maximum amount of tokens that can go out until the current price, square root P, reaches the target price, square root P target. Okay, so that's max amount in and max amount out. Next, I'm going to explain a little bit more about square root P next. Square root P next is the next square root price, either for putting in some amount of token in or taking out some amount of token out. For this example, I'll explain what square root P next is when some amount of token in is coming in. So let's say that we started our liquidity in this position and then some amount of token in came in. The current square root price before this amount of token in came in was over here. And after it came in, after this much amount of token X came in, the next square root price, let's say, is over here. And this is what the code refers to as square root P next. And that completes the explanation for the algorithm for the swap. Imagine that there are multiple liquidity positions. For example, here's one, here's another one, here's another one, and here's another one. When we stack up all of these individual liquidity positions, we get a graph that looks like this. Let's say that the current price is over here represented as a vertical dotted line. To the left of the current price, liquidity is all in token Y. To the right of the current price, liquidity is all in token X. During a swap, this current price will move either to the left or to the right. If token X is coming in and token Y is going out, then the price will shift over to the left. And if token Y is coming in and token X is going out, then the price will move over to the right. As the price goes back and forth, we can see that the liquidity changes. For example, currently the liquidity is at 14. And let's say that there's a swap and it swings the price over to a lower liquidity. And now the liquidity is at 4. And as another example, let's say that the price swings over to the right. As the price swings over to the right, we can see that the liquidity changes. Liquidity is now at 13, liquidity is now at 8, 5, and then 0. As the price changes, how does Uniswap V3 keep track of the active liquidity? Active liquidity is represented as the height of this rectangle, and the height of this rectangle is calculated by stacking up all of the liquidity at that price. For example, when the current liquidity is at 14, this is the sum of two liquidity positions, and we can see this by toggling off and on the positions. Then I'm gonna turn on and turn off the other position, and you can see that at this price, there are two positions that are active. Hence, we get a rectangle that is higher than both of them. The height of the resulting rectangle is calculated by adding up all of the heights of the individual rectangles that are currently active at the price. Okay, but how does Uniswap V3 keep track of the current active liquidity which is the sum of all of the liquidities that are currently active. To understand how Uniswap V3 keeps track of the current active liquidity, we need to understand what's called liquidity net. Liquidity net basically means that when the price changes, eventually it will cross over a tick. And when it does, it will either plus or minus some number to the current liquidity. And this number is called liquidity net. Let's start with a simple example. Let's say that we have a single position and we have a current liquidity equal to L, which is represented by the height of this rectangle. We have the current tick over here at T, and we have two ticks, T lower and T upper, which define the price range for the position. So for this example, we only have one position and it has a liquidity of L between the price ranges T lower and T upper. When a position is created, at the lower tick, it will assign a positive liquidity net, and to the upper tick, it will assign a negative liquidity net. If two positions either overlap or intersects at these boundaries, tick lower and tick upper, then liquidity net is calculated by summing up all of these individual liquidity net. The other thing that we need to understand how the current liquidity is tracked is the direction of the price. If the price increases, we associate this with a positive number, +1. If the price decreases, then we associate this with a -1. With these two numbers, the direction of the price change, and these liquidity nets at the boundaries of tick lower and tick upper, we can now keep track of the current liquidity. Let's say that this current tick associated with the current price moves all the way over to the left. When this current tick crosses over tick lower, we need to update the active liquidity. Let's call this next liquidity. And the next liquidity will be equal to the current liquidity L. To this, we add some number. And this number that we need to add is a multiplication of two numbers. The direction of P, and then we multiply this by plus or minus the liquidity net. For example, in this case, let's start with the direction of the price. The price decreased from over here to over here. So the direction of price will be a -1. And then we need to multiply this by a plus or minus delta L, liquidity net. In this case, at the lower tick, we have the plus delta L that is stored. So, to the direction of P, let's say this is -1, to -1, to -1, we multiply this number. -1 plus delta L. In this example, we only have one position. So let's say that this liquidity net is equal to the liquidity of the position, which is L. So -1 times L. And the current liquidity is also equal to L. So what do we get? We will get, in this case, L plus -1 times L, which is equal to 0. Let's look at another simple example going the other way. Let's say that the current price is somewhere over here and the current liquidity is L. Let's also say that there was a swap and it increased the price. So now the tick crossed over tick upper. When this tick crossed over tick upper, we need to apply this algorithm. So current liquidity is L. The direction of the change of the price is a positive. So we would do +1. And then the liquidity net stored at this tick upper is a minus delta L. In this example, again, there's only one position. So the liquidity net is equal to the liquidity of this single position, which is equal to L. And we have a minus, so I'll copy this, put it here. Single position, so liquidity net is equal to the liquidity of the position, and we keep the minus that we have over here. Okay, so let's do the math. This is equal to L plus +1 times minus L, or this simplifies to L minus L, which is equal to 0. In summary, the way the current liquidity is updated is when the current tick crosses over one of these tick lower or tick upper, it will apply this algorithm. And this algorithm is to take the current liquidity, we multiply by the direction of the price change. If the price increases, then we multiply by +1. And if the price decreases, we multiply by -1. We multiply this direction of the price by liquidity net, which is stored at tick lower and tick upper. Let's look at an example of how the current liquidity is updated using liquidity net. The vertical dotted line in black will represent the initial tick before the price changes. We'll label this as tick 0. The purple dotted line will represent the location of the tick after the price changes. And the difference in tick between the initial tick and the tick after the price changes, we'll represent it as tick delta. For example, if the price increases, then the ticks will also increase, and tick delta is represented as a positive number. Likewise, if the price decreases from the initial tick, then tick delta is represented as a negative number. Now let's say that there are multiple positions. To get the liquidity at each tick, we will stack up all of the liquidity positions that overlap, and we will get a graph that looks like this. To the left of the current tick, liquidity is all in token Y, so we'll color this blue. And to the right of the current tick, liquidity will all be in token X, so we'll color this red. I'll highlight the liquidity at each price as a pink line. And then I'll also display a label. Currently, liquidity is equal to 13. So as the tick moves, you can also see that the current liquidity also changes. Currently, the liquidity is equal to 3, and now it is equal to 0, and now it is equal to 5. Remember in the last video, we said that to get the liquidity net, every time we create a position to the tick lower, we will associate a positive number. For example, if we're creating this position with liquidity equal to 4, then to the lower tick, we associate plus 4. And take a note over here that we have two overlapping positions, one for 10 liquidity and one for 3 liquidity. And to the upper tick, we associate a negative of the same number. Again, looking at this example, we're creating a position with liquidity equal to 4. So to the upper tick, we associate a minus of that liquidity, minus 4. And likewise, we can sort of see a position over here. We have a positive 10 on the lower tick, and we have a minus 10 on the upper tick. And to calculate the liquidity net, all we have to do is add up all of these pluses and minus at each tick. For example, let's start with a simple case. Here we have a single position, so the liquidity net will be plus 4. A more interesting example is where the positions overlap. Here, two positions overlap, one with 10 liquidity and one with 3 liquidity. We add up all of these numbers, so the liquidity net will be plus 13. And then we do the exact same thing for the upper ticks. Let's start with the simple example again. Again, here we have a single position with liquidity equal to 4. At the upper tick, when we add up all of these purple numbers, we get a liquidity net of minus 4. A more interesting example is when we take a look at over here. Notice that for the lower tick, we have a plus 13, but at the same liquidity height, when this liquidity deactivates, we have a minus 10 over here. And this is because when we add up all of these purple numbers, we have a minus 10 over here, and this is the only number. So liquidity net at this tick is minus 10. With these liquidity nets, the numbers that are in pink, let's go through an example of how the current liquidity shown here will change. Let's start with a simple example of using a single position. So I'm going to move the initial price over to here. And then I'm also going to move the current price to match the initial price. The current active liquidity is equal to 4. This matches the liquidity of this position. Let's increase the price and see how this current liquidity will change. So as we increase the price, it's going to cross over this tick. And when it does, the current liquidity is now equal to 0. This is because the way we calculate this liquidity is by taking this liquidity net, this is a minus 4, and then the direction of the price. The direction of the price change was positive, so this will be plus 1. The liquidity before was 4. To this, we add a minus 4, so we will get 0. And if we go the other way, for example, let's say that we start from here again, then when we go the other way, the price is decreasing, so the direction of the price is a minus 1. To minus 1, we'll need to multiply by this plus 4, and then add it to this current liquidity, so it will be equal to 0. Okay, let's take a look at another example. So I'm going to move the initial tick to over here, and then also the initial price to match the initial tick. So I'll give you two more examples. Let's start with an easier one, when the price decreases. When the price decreases, the direction of the price is negative 1, and you can see over here that tick delta is also negative. And as the price crosses over this tick, the current liquidity is equal to 13. The direction of the price is a minus 1. Liquidity net is plus 13. The next liquidity will be current liquidity plus the direction of the price, minus 1, times liquidity net 13. 13 plus minus 1 times 13 is equal to 0. As we decrease the price, you can see that the liquidity updated to 0. Okay, so let me give you one more example. Again, we start at this price, and let's say that the price increases. So the price increases, the current liquidity is 13. The direction of the price is a positive number, so we'll need to multiply plus 1 by liquidity net, which is equal to minus 10. To this current liquidity 13, we add plus 1 multiplied by minus 10, so this will be 13 minus 10. So the active liquidity when the current tick crosses over this tick must be equal to 3. Let's see. The current tick crosses over this tick, and now the liquidity is equal to 3. And then when the current tick crosses over this tick, we will need to apply a minus 3 to the current liquidity, and the liquidity is now 0. So this was an example of how liquidity nets that are stored at the ticks keep track of the current liquidity. Every time the current tick crosses over one of these ticks, it will either add or minus some liquidity net to update the current liquidity. Given some liquidity L and the price ranges P lower and P upper, if you wanted to answer the question what is the amount of token X between these price ranges, P lower and P upper, or if you have another question like what is the amount of token Y between these price ranges, then we saw in the earlier videos that this equation answers our question, that the amount of X between the price ranges is given by this equation, and the amount of token Y in the price range is given by this equation. Now using these two equations, we can also ask a different question. The questions that we can answer using these two equations are, if we were to add or remove this much amount of token X, then what is the resulting price? And likewise, if we were to add or remove this much amount of token Y, then what is the resulting price? The questions that we'll answer in this video are, what is the price after adding or removing delta X amount of token X, and what is the price after adding or removing delta Y of token Y? Let's start with the first question. What is the price after adding or removing delta X? This question is actually two questions. What is the price after adding delta X? And what is the price after removing delta X? Let's start with the first one of what is the price after adding delta X. Let's consider the case when we add delta X from price upper. On the graph, it will look like this. Here we have the constant product curve, and starting from the price upper, we will add this much amount of token X, so the price must decrease. The price will decrease from the starting price, price upper, to the lower price, price lower. So to answer our question, what is the price after adding delta X, we'll use this equation. I'll copy this equation, and then paste it here, and I'll replace this X with a delta X. Okay, using this equation, the question that we need to answer here is what is the price after adding delta X? We started out with P upper, and after adding delta X, the price will be at P lower. So using this equation, what we need to find is P lower in terms of delta X, liquidity L, and P upper. We can derive this answer by simple algebra. So I'll copy this, paste it here. We want to rearrange this equation so that P lower will be on one side of the equation and everything else will be on the other side of the equation. So first I'll bring this over here, and then instead of a minus, this will be a plus, and then I'll bring the plus sign over here. Next, I want a common denominator of square root of P upper. So what I'll do is I'll multiply this delta X by square root of P upper. So our equation will look like this. Next, I'm gonna simplify the left side of the equation. As the numerator, we will have L plus delta X times square root of P upper, and the denominator will be the square root of P upper. Notice that square root of P lower, this is the thing that we want to find, is on the bottom. So I'll bring this to the top by multiplying everything by P lower. And then I'll bring this over to the bottom. Then I'll bring the L over here. And then over here, we'll have a 1. So all I did was flip the numerators and the denominators. Now the square root of P upper will come to the top, and our equation will look like this. To get square root of P lower, all we have to do is multiply everything by L. And finally, we get that the square root of P lower is equal to L times the square root of P upper divided by L plus delta X times square root of P upper. Our original question was what is the price after adding delta X? However, for our final answer, we'll keep it as this. We'll keep our answer in the form of square root of P lower. And this is because when you look inside the code for Uniswap V3, a lot of the math is done using the square root of price. So we'll keep our equation like this, in the form of square root of price. And when you look at the code inside Uniswap V3 pool contract, you'll see this form of equation being used inside the function for swap. Okay, so we answered the first part of the question. Let's also do the same for when we remove delta X. what would be the equation? When we remove delta x starting from price lower, what is the equation for price upper? So if we go back up over here, let's say that we start from price lower and we remove delta x amount of token x. The final price after removing delta x amount of token x must be over here. And what is the equation for this price upper? Again, we can solve this equation by starting from this equation, and with some simple algebra, all we have to do is solve for P upper. So what we're doing here is the price will increase from P lower to P upper, and using this equation, we want to solve for a square root of P upper. So the first thing that I'll do is bring this over to the right and bring this over to the left. Next, on the right side of the equation, I want delta x to have a denominator of square root of P lower. So I'll multiply delta x by P lower divided by P lower. And now we have a common denominator of square root of P lower. Next, I'm going to flip the numerator in the denominator. On the left side, square root of P upper will come to the top and L will come to the bottom. And I'll do the same on the right side of the equation. Bring the square root of P lower to the top and bring this equation to the bottom. The last thing that I'll do is multiply both sides of the equation by L. On the left side, this will remove the L, and on the right side, we'll have a L on the numerator. And now we have an equation for square root of P upper when we remove delta x starting from P lower. So we have two equations, one describing the price lower after adding liquidity, and one describing the price upper after removing liquidity. Comparing these two equations, they look almost identical except for over here we have a plus delta x and minus delta x over here. So we can generalize these two equations into a single equation. So if we were to add delta x to this delta x, we add a plus sign. If we were to remove delta x to this delta x, we will have a minus sign. Next, this left side of the equation, square root of P, describes the price after. So let's relabel this as price after. And on the right side of the equation, this price describes the price before adding or removing liquidity. So let's relabel this as price before. And now we have a generalized equation of what the price is, either after adding or removing liquidity. If we were adding liquidity, this will be plus delta x. And if we were removing liquidity, it will be minus delta x. Okay, we'll do something similar to answer the question, what is the price after adding or removing delta y? Let's start with the first part of the question, what is the price after adding delta y? So, take a look at this graph over here. We'll start from price lower, P lower, and we're going to add delta y amount of token y. The resulting price, let's call this P upper. And what is the equation for P upper? Well, scrolling back up, again, we'll be using this equation to answer our question. And instead of having a y over here, we'll replace this with delta y. Okay, so we're going to be adding delta y. So this will bring the price from P lower to P upper. The price will increase from P lower to P upper. And using this equation, what we want to find is, we want to find P upper. So starting from here, we can find P upper simply by bringing this L times square root of P lower to this side of the equation. This minus will become a plus. To get the square root of P upper, all I have to do is divide both sides of the equation by L. Dividing the first term by L, I get delta y divided by L. And dividing the second term by L, the L on the top cancels out with the L on the bottom. And we're left with square root of P upper is equal to this equation. Next, let's do the same for if we were to remove delta y starting from P upper. If we were to remove delta y starting from P upper, so we start from here and then we remove this much amount of token y. The resulting price will be P lower. And what is the equation for P lower? Again, starting from this equation, we can answer this question. We have a P lower here, so we need to just rearrange the equation to have P lower on one side of the equation and everything else on the other side of the equation. I'll bring this over here to the left and then delta y to the other side. And then I'll divide both sides of the equation, dividing the first and dividing the second term. Dividing the first, the L will cancel out. And we're left with square root of P upper minus delta y divided by L. So we have two equations now. The price lower after adding delta Y and the price upper after removing delta Y. The first equation, I'm going to rearrange it. I'll also remove this L. And notice that we have two equations that look almost identical. We can generalize these two equations now. So if we were to add delta Y, then the resulting price after is given by this equation. And if we were to remove delta Y, then we will have a minus over here next to delta Y. The resulting price, we'll call this price after, and the price before we add or remove delta Y, we'll call this price before. Now we get the equation that the square root of price after is equal to the square root of price before plus minus delta Y divided by L, plus when we're adding delta Y and minus when we're removing delta Y. The function compute swap step inside the library contract swap math computes the amount of token in, token out, and the fees given the price ranges and the liquidity. This function is called inside the function swap of the Uniswap V3 pool contract, and it returns the next square root price x96, amount in, amount out, and fees. The way the fee is calculated inside this function can be a little bit confusing. So in this video, we'll go over the math of how the swap fee is calculated. The swap fee is calculated from the amount of token that comes in. In this video, we'll say that token in is token X and token out is token Y. We'll say that F is equal to the swap fee percentage. This F will be a number between 0 and 1. Capital A will be equal to the amount in before swap fee. Swap fee is charged on amount of tokens that come in. So we can say that fee, the actual amount of fee, is equal to A times F. A is the amount in before swap fee, and F is the swap fee percentage. This AN that you see over here will represent the amount in after the swap fee. Since A is the amount in before the swap fee, and we already have an expression for the fee, we can rewrite AN, which is the amount in after the swap fee, to be equal to A minus the fee. And this amount in must be less than or equal to the maximum amount in. The maximum amount in this case, is the amount of token X that can come into this liquidity until the current price reaches the lower price P of A. You can imagine that as more token X comes in and more token Y leaves this liquidity, then the price will shift over to the left and the amount of token X inside this liquidity will increase. And at this point, where the current price P is equal to P of A, this liquidity is all in token X. And the maximum amount of token in is the maximum amount of token X that can come in until this current price reaches the lower price P of A. And A out represents the amount out. This A out must be less than or equal to the maximum amount of token out. In this case, the maximum amount of token out is the amount of token Y that can leave this liquidity until the current price reaches the lower price range P of A. So imagine that as the current price shifts over to the left, the amount of token Y in this pool will decrease until the current price reaches the lower price P of A. So the maximum amount of token Y that can leave this pool is this amount, the amount of token Y between the price ranges P and P of A. With these variables defined, let's now derive the equation for the fee. Now there are two cases to consider, exact out and exact in. Exact out means that the caller specified the amount of tokens to leave the pool, and Uniswap V3 will calculate the amount of token in that must come in. Exact in means that the caller specified the amount of tokens to come in, and Uniswap V3 will calculate the amount of token that will go out. So let's start with exact out. For exact output, we first need to calculate the maximum amount of token that can come out between the price ranges, the current price P, and the lower price P of A. So scrolling back up, in this example, the maximum amount of token that can come out between the current price and the lower price P of A is the amount of token Y over here. So this will be the maximum amount of token out. We first need to calculate what this maximum amount of token out is between the price ranges P and P of A. Once we calculate this maximum amount of token out between the price ranges P to P of A, next we can calculate the actual amount of token that can come out from the price ranges P to P of A. Once we calculate the amount of token that will come out from this liquidity, we can next calculate the amount of token in that must come in. And once we calculate amount in, we can calculate the fees. To calculate the fees, we'll use these equations. At this point, we know what AN is. So, using this equation, we'll work our way backwards to calculate what the fee is. So AN is equal to the amount in after the swap fee, which is equal to A minus fee. A is the amount in before the swap fee, and the fee is the actual swap fee. We can replace this fee, since we know that fee is simply equal to A times F. This is equal to A minus A times F. We can simplify this to A times 1 minus F. Now we can figure out what A is, given that we know what AN is. All I have to do is divide both sides of the equation by 1 minus F. And I get that this amount in before the swap fee must be equal to AN, the amount that comes into this liquidity, divided by 1 minus F. And once we figured out what A is, we can also figure out what fee is. So going back up, we said that the fee is equal to A times F. We figured out what A times F is, so we can now figure out what the fee is in terms of AN. So this is equal to, A is equal to this equation, so we can replace this A over here with this expression, and then to get the fee, we times this by F. So this is the equation for the fee. The swap fee is equal to AN divided by 1 minus F times F. And we can actually see the formula inside the function compute swap step. Scrolling all the way down, we see how the fee is calculated. Fee amount is equal to amount in times fee divided by 1 minus the fee. Next, I'll explain how the fee is calculated for exact in. For exact in, it turns out that there are two cases to consider: when AN is equal to the max amount in, and when AN is less than max amount in. We'll start with the case when AN is equal to max amount in. For the case when token in is token X and token out is token Y, the current price will decrease. So the first step is to find the maximum amount in between the price ranges P to the lower price, PA. Scrolling back up, this max amount in will be the amount of token X that can come in between the current price P to the lower price P of A. As token X comes in and token Y leaves this liquidity, this rectangle in blue will fill up with rectangle in red. And when the current price reaches the lower price P of A, all of this rectangle will be in red. And at this point, the liquidity is all in token X. The amount of token X that can come in to fill out this blue rectangle is max amount in. Once we calculate what maximum amount of token that can come in is, we can actually calculate the amount in. And once we calculate the amount of token that will come in, we can also calculate the amount of token that will go out. From the amount of token in that we calculated, we can also calculate the fee. So let's start with the case of when amount in is equal to max amount in. For AN equal to max amount in, this is the case where token X will come in to this liquidity, and it will swap all of this token Y for token X. So at the end, we will have the current price equal to the lower price P of A, and all of this liquidity is now in token X. The way that the fee is calculated in this case follows the same equation that we derived over here. In this case, we know what AN is, so we don't have to figure out what this capital A is. We can take a shortcut and just say that the fee is equal to AN divided by 1 minus F times F. Inside the function compute swap step, you can see that the way the fee is calculated is the same equation that we derived. Fee is equal to amount in times fee divided by 1 minus fee. So this is the fee for exact in when amount in is equal to max amount in. The other case that we need to consider is when amount in is less than max amount in. When AN is less than max amount in, we will have the case where some amount of token X comes in and some amount of token Y leaves this liquidity. As a result, the current price will shift over to the left. However, it does not reach the lower price P of A. To the right of the current price, we will have the previous amount of token X plus the amount that came in, and to the left of the current price, we will have some amount of token Y left. In this case, the way Uniswap V3 calculates the fee is to take whatever amount that is remaining minus AN. AN is the amount that was calculated to come into this liquidity, and A is the amount in before the swap fee. And this is equal to A AN is equal to A minus phi. So we can replace this AN with A minus phi. And this equation simplifies to being phi is equal to phi. So what's going on here is that A is the amount of token in before the swap fee is deducted. And AN is the actual amount of token that will come in, which includes the swap fee. If we take the difference, we get the fee back. Going back to the function compute swap step, and looking at the place where the fee is calculated, you can see the code over here. The way it calculates the fee is take amount remaining and minus amount in. This amount in that you see over here is the AN that we saw in the math equation. So that was the explanation of how the swap fees are calculated. If you look at the code, it's a little bit confusing. However, if you do the math, it turns out that in all cases, swap fee is a percentage of amount of tokens that come in. In this video, I'll do a code walkthrough for the function swap inside the contract Uniswap V3 pool. This contract is inside the repo B3 core. The contract name is Uniswap V3 pool.sol. And the function that I want to explain in this video is called swap. This is a low-level function inside Uniswap V3 to swap a token for another token. For the inputs to this function, it's going to take in the recipient. This will be the receiver of token out. 041, if this is set to true, then it will mean that token 0 will come in and token 1 will go out. If this parameter 041 is set to false, then it will mean that token 1 will come in and token 0 will go out. Amount specified will determine whether the swap is an exact input or an exact output. Notice here that this parameter amount specified is an int 256. So it can be both negative and positive number. When this number is a positive number, then this means that this swap is an exact input. The user specifies the amount of token to come in, and Uniswap V3 will calculate the amount of token to go out. On the other hand, if amount specified is less than 0, then this means that the user specified the amount of tokens that they want to pull out of this pool. And in this case, Uniswap V3 will calculate the amount of token that must come in. And then we have the square root price limit x96. This is the price limit that the caller is willing to accept. Notice here that this variable name ends with x96, and you'll see this a lot inside the code for Uniswap V3. So what is x96? Well, to simply put, x96, all it means is that you have some kind of variable, and then it's multiplying it by 2 to the 96. The last input data encodes the data to be passed over to the Uniswap V3 swap callback. So if we go all the way down, at the end of the swap, it transfers the tokens out, and then it calls a function called Uniswap V3 swap callback message sender. And inside the callback, it's going to pass in the amount of token 0 and amount of token 1, which will be leaving from this pool, and the amount of token that must come into the pool. And the last parameter is the data. So this data is the data that was encoded inside the function input for the function swap. Okay, so these are the inputs of the function swap. Moving on, it first checks that this input amount specified is not equal to 0, and then it loads slot 0. So remember that inside slot 0, so I'll go all the way up to find the struct called slot 0. Okay, here it is. Here's slot 0. And inside the EVM storage of slot 0, all of this data is stored. And the main reason that it is stored in slot 0 is to save gas. Inside the struct, we can see that it stores the current tick, the current square root price x96, and other stuff. These are parameters that are used for the price oracle. Okay, so let's go back down. So once it loads slot 0 to memory, again to save gas, it checks that this function is not re-entered. So this is a re-entrancy guard. Okay, and then it checks the square root price limit that was passed as input. Next, it updates the re-entrancy log, and then it loads some state variables into memory. Again, this is used to save gas. Okay, and then it creates a variable called exact input. Remember that the input, if amount specified is greater than 0, this means that some token is coming into this pool contract. So this will be an exact input. If amount specified is less than 0, then this means that the caller is requesting to pull out some token from this pool contract. So in this case, this swap will be an exact output. Okay, moving on. It loads more variables, including state variables, into memory inside a struct called swap state. This swap state will be used inside a while loop to execute swaps. Inside the while loop, it will execute swaps in the current liquidity. Remember that in Uniswap V3, different users can put liquidity into different price ranges. These liquidities will be stacked up to create a bar graph. And inside this while loop, we're only swapping in the bar that represents the current active liquidity. We'll come back to this while loop later. Let's move on. And inside this while loop, it will calculate the final amount of token that must come in and the final amount of token that will go out. It will also update the current tick and the current square root price x96 that is stored in memory. If these values are not the same as the initial values, then it will update the state variables that track the square root price x96 and the current tick. So this is what the code over here is doing. Okay, so moving on. Next, it will update the current liquidity if it has changed. And then it will update state variables called fee growth global 0x128 and fee growth global 1x128. These are state variables that track the amount of swap fees that was collected. Using these state variables, liquidity providers will be able to collect fees. I'll explain in another video how these state variables track fees for liquidity providers. Okay, so moving on. Next, it determines the amount of token 0 and the amount of token 1 that must come in and go out. Now, the conditional statement here is a little bit confusing, so I want to explain what's going on. Here we can see that it compares whether 041 is equal to exact input, and if it is, it will execute the first condition. Otherwise, it will execute the other condition to determine the amount of token 0 and amount of token 1. If we list out all four possible cases for 041 and exact input, and also list out what amount 0 and amount 1 must be, then we'll understand what's going on over here. So let's start with the case when 041 is true and exact input is also true. When 041 is true, then it means that token 0 is coming in and token 1 is going out. Exact input means that amount specified is greater than 0. And this amount specified remaining is the amount specified that is remaining after executing this while loop, which calculates the exact amount of token that must come in. For exact input, if amount specified remaining is greater than 0, then it means this pool could not take in all of the token that the user specified. So the actual amount that will come in is the amount that user specified minus remaining. For the first case, we have 041 equal to true and exact input. So the token that is coming in is token 0, and the amount that must come in is the amount specified by the user minus remaining. And inside the while loop, it's also going to calculate a variable called state.amountCalculated. For exact input, this is the amount of token that will go out. For a 041, token that is going out is amount 1. So to this variable amount 1, we set state.amountCalculated. The other case where 041 is equal to exact input is when both of them are false. So when both of them are false, let's start with 041. 041 equal to false means that token 1 will come in and token 0 will go out. And since exact input is false, then this means that this swap is an exact output. So token 1 will come in and token 0 will go out, and the caller specified the amount of token that they wish to pull out from this pool. Amount 0 will be equal to the amount specified by the user. This is the amount that the user requested to take out from this pool, minus amount specified remaining. The amount of token that must come in is stored inside calculated, state.amountCalculated. In this case, this is a 140 swap, so token 1 will come in, and the amount of token 1 that must come in is calculated. In these two cases, the amount of token 0 and amount of token 1 are calculated in the first expression. Okay, so let's now consider the case when 041 is not equal to exact input. There are two cases, when 041 is false and exact input is true, and when 041 is true and exact input is false. Let's start with the first case. When 041 is false, this means that token 1 will come in and token 0 will go out. Exact input equal to true, so amount specified will be a number greater than 0, and this is the amount of token that the user specified to put inside this pool. The token that's coming in will be token 1, so here we see that amount 1 is equal to the amount specified by the user minus remaining. The token that's going out is token 0, and this is stored in state.amountCalculated. And for the last case, 041 equals to true and exact input equals to false. Token 0 will come in and token 1 will go out. And the user specified the amount of token to go out. Token 1 will go out, so amount 1 must be equal to the amount specified by the user minus the remaining. For exact output, user specifies the amount of tokens to go out, and Uniswap V3 calculates the amount of tokens to come in. Since this last case is a 041, token that's going to come in is token 0, and this amount is calculated by Uniswap V3. So, in the last two cases, amount 0 and amount 1 is calculated by this expression. Okay, so moving on. For the last part of the swap function, it's going to transfer the token out and then call the callback on message sender. The callback is called Uniswap V3 swap callback. And inside here, message sender must send the tokens that is requested. And then afterwards, this contract is going to check that the correct amount of token came in. For 041, token 1 will go out, so the pool will transfer token 1, and token 0 must come in, so it's going to call the callback on message sender, and then afterwards, it's going to check the balance of token 0. If this swap is not a 041, then it is a 140. Token out will be token 0, so it's going to first transfer token 0, and then it's going to call the callback, and then afterwards, this pool contract is going to check the balance of token 1. Okay, for the last part of this video, let's dig a little bit deeper inside the while loop. The while loop will continue to execute while the amount specified remaining is not equal to 0, and the current square root price x96 is not equal to the square root price limit x96 set by the user. Inside this while loop, it's going to first get the next tick. Let's take a look at this function called next initialized tick within one word. Inside the library called tick bitmap, there is a function called next initialized tick within one word. And what this function is going to return is either the next initialized or uninitialized tick up to 256 ticks away from the current tick. Once it gets the next tick, it will make sure that this next tick is within minimum and max tick. Okay, and then moving on, from this tick next, it will calculate the next square root price. And with this next square root price, it will calculate the amount of tokens to come in, amount of tokens to go out, and the fee for the swap. And it will also calculate the current square root price x96. If the swap is an exact input, then from amount specified remaining, it will deduct the amount of token to come in plus the fees. If it is an exact output, then to amount specified remaining, it will add amount out. In both cases, this amount specified remaining will approach 0. For exact input, it will approach from the positive number and decrease to 0. For exact output, it will start from a negative number and increase to 0. Okay, and moving on, next it calculates the protocol fee if it is enabled, and then it will update the state variable fee growth global x128, which is loaded into memory. Again, this is the variable that enables liquidity providers to collect fees on swaps. Okay, and then moving on, if the current square root price x96 has reached the next square root price x96, so this next square root price x96 represents the square root price x96 that we got for the next tick. If the current square root price x96 is equal to this next one, and if the tick is initialized, then it will store some variable for the price oracle, and then what's more interesting is this part. It will get a variable called liquidity net and then update the current liquidity by this liquidity net. Remember that liquidity net is used to keep track of the current active liquidity. This code over here is how it's done. And then at the end of the loop, it will update the tick. Okay, so that completes the code explanation inside the while loop. And that also completes the code explanation for the function swap. The swap router 02 contracts has 4 functions that we can call to swap tokens. The functions are called exact input single, exact input, exact output single, and exact output. We'll examine how each of these functions work. But before we do that, I'm going to first explain one of the internal parameters that is used when any of these functions is called. When a function exact input single or exact input is called, an internal function called exact input internal is called. And when the function exact output single or exact output is called, an internal function called exact output internal is called. Inside the function exactInputInternal, you can see over here that there is a parameter called path. This parameter path encodes the two tokens and the fee which identify the pool to swap one. Inside the function exactOutputInternal, we can also see the parameter path. And again, this parameter named path encodes the tokens and the fee which identify the pool to swap one. The data type of the parameter named path is bytes. And the way that the tokens and the fees are encoded is the following. We start with some token, and then next we encode the fee, and then followed by token. These three parameters will identify a pool. If you wanted to do a swap between two pools, then we follow this by a fee and token, and these three parameters will identify the next pool. For example, let's say that we wanted to swap from DAI to USDC on a pool with fee 0.01%. And then afterwards, we want to swap USDC for WETH on the USDC WETH pool with 0.3% fee. In this case, the path will be encoded as the address of DAI, 100, and then the address of USDC followed by 3000, and then the address of WETH. These two numbers, 100 and 3000, are scaled up by 10 to the 6. So, if you divide 100 by 10 to the 6, you'll get 0.01%. If you divide 3000 by 10 to the 6, then you'll get 0.3%. So this is how the path is encoded. It encodes the tokens to swap and the pools to use for the swaps. Next, let's take a look at how the function exactInputSingle inside the contract swapRouter02 works. We have a user that's going to call the contract swapRouter02, and the swapRouter02 will call into Uniswap V3 pool contract. Inside swapRouter02, there is an internal function called exactInputInternal. And inside this function, the path will be encoded as token in, fee, and then token out. The user will first call the function exactInputSingle. This function is called when you want to swap a token with a single pool. If you wanted to swap with multiple pools, then you will call another function called exactInput, which we will take a look at later. The swapRouter02 will call into the function called swap on Uniswap V3 pool contract. The Uniswap V3 pool will transfer the token out to the user. And then next, it will call a callback called Uniswap V3 swap callback on the swapRouter02 contract. Inside the callback, the swapRouter02 will call a transfer from for token in. Transfer from the user to Uniswap V3 pool contract. Notice here that token out is transferred to the user before the user has to pay the token in. This is the same pattern that we saw in Uniswap V2. Next, I want to dig a little bit deeper and explain what functions are called and how they are called. First, the user calls the function exactInputSingle on swapRouter02. This function will execute an internal function called exactInputInternal. The function exactInputInternal will call the function swap on Uniswap V3 pool. Among other things, the function swap will execute two things. Transfer token out to the recipient. In this case, the recipient is the user. And then afterwards, it will execute the callback, Uniswap V3 swap callback. The callback is executed on the contract swapRouter02. Inside the callback of swapRouter02, it will transfer the token in from the user to the Uniswap V3 pool contract. Let's say that we have a Uniswap V3 pool with token A and B. We have another one with token B and C, and we have another one with token C and D. If you wanted to swap token A for D, then we will need to swap A for B, and then for B for C, and then for C for D. To execute a swap that involves multiple pools, we can call a function called exactInput on the swapRouter02 contract. So let's say that we wanted to swap token A for B, B for C, and then finally from C to D. First, the user will call the function exactInput on the swapRouter02 contract. The swapRouter02 contract will run a loop to execute swaps on multiple pools. For each pool, it will call the function swap, receive some tokens, and then send some tokens out. In our example, it will first call the swap on Uniswap V3 pool, having the tokens A and B. Uniswap V3 pool contract for token A and B will send token B to the swapRouter02 contract. This token B that is sent to this router contract will be used in the next swap to send the token B over to a Uniswap V3 pool with token B and C. And after the token is sent over to the swapRouter02 contract, it will call the callback function, Uniswap V3 swap callback. Inside the callback, the swapRouter02 contract will send token A from the user over to the first pool with token A and B. And that completes the first swap of putting token A and then receiving token B. We still have two more swaps to execute. The swapRouter02 contract will call the function swap on the next pool having the tokens B and C. This second pool will send token C over to the swap router 02 contract, and then again it will call the callback function called Uniswap V3 swap callback. Remember that token that was sent over to the swap router 02 contract in step 3. Now this token is transferred over to the pool with token BC. This completes the second swap of swapping token B for token C. And then we have one more swap to get token D. So at the moment, the swap router 02 contract has token C. It calls the function swap on Uniswap V3 pool with tokens C and D. And again, the Uniswap V3 pool contract will send the token out before receiving any token in. Since this is the last swap, instead of sending the token over to the swap router 02 contract, the Uniswap V3 pool contract will send the token directly over to the user. And then it will call the callback Uniswap V3 swap callback. Inside the callback, token C is sent from swap router 02 over to the last pool, Uniswap V3 pool, with token CD. This is an example of how tokens are swapped between multiple pools when the function exact input is called on swap router 02. Next, I'm going to explain what functions are called and what parameters are passed when the function exact input is executed. When the function exact input is called, we need to pass in the path. For our example, we're swapping from token A, B, C, and then D. So the path will be encoded as token A, followed by the fee that will identify the pool having token A and B, followed by token B, and then followed by fee that will identify the pool for token B and C. And then finally, followed by the fee that identifies the pool for token C and D. The payer will be transferring the token in. In this case, this will be the user. Next, it will execute a while loop to call swaps on the individual pools. Starting with pool AB, inside this while loop, it's going to call the internal function called exact input internal. Here, the recipient, the address that is going to be receiving the token out, is set to the router contract. This is because once it receives the intermediate token, it's going to send it over to the next pool. The function swap is called on pool AB. Token B is transferred over to a recipient. Here, the recipient will be the router contract. This token B that is received by the router contract will be used in the next iteration to send this token B over to the next pool, BC. Once the token is sent, next it's going to call Uniswap V3 swap callback. This function is inside the router contract. Inside the router contract, it will transfer token A from the payer. In this case, the payer is the user. So it's going to transfer token A from the user to pool AB. We're still inside the loop, and to prepare for the next loop, the code will set the payer to the router contract. And the parameter path is set to token B, C, and D. Here, token A is removed from the path since we are done with that swap. The first three parameters, token B, fee, and token C, will identify the pool to swap on. And then we move on to the next iteration of the for loop. Call the internal function exact input internal again. And again, the recipient, the address that will receive token C is set to the router contract. The router contract will receive token C and then send it over to the last pool, CD. So just like in the first iteration, it will call the function swap on pool BC. Token in is token B and token out is token C. The Uniswap V3 pool contract will transfer token C to recipient. Here, since recipient is set to the router contract, this token C is sent over to the router contract. And then afterwards, it's going to call Uniswap V3 swap callback on the router contract. Inside the callback, the router will transfer token B from payer, in this case, the payer is the router, to pool BC. Remember back in this step, token B was transferred over to the router contract. So at this step, we still have token B in the router contract. And this is why the router contract can transfer token B over to pool BC. To set up for the next iteration of the for loop, again the payer is set to the router contract. The last swap will be from token C to token D. Here the payer means that the router contract will transfer token C over to the pool CD. And the parameter path is updated to C, fee, and D. From the previous parameter, we removed token B and fee. And these last three parameters will identify the last pool to execute the swap on. And then for the last iteration, it will call the function exact input internal. Notice that in the previous two iterations, recipient was set to the router contract. For the last iteration, the recipient is set to the user. Here it means that token D will be sent to user. It will call the function swap on pool CD. The Uniswap V3 pool contract will transfer token D to recipient. recipient is set to user. So token D will be sent over to the user. And then the Uniswap V3 swap callback is executed on the router contract. The router contract will transfer token C from payer. Here, payer is set to the router contract. So token C will be transferred over from the router contract over to pool CD. And that completes the call trace when the function exact input is called. If you wanted to get some specific amount of token from a swap, and the swap only involves one pool, then you will call the function exact output single. Inside the swap router 02 contract, when the internal function exact output internal is called, the path will be encoded as following: token out, fee, and then token in. These three parameters will identify the pool to swap on. Here notice that for exact input single, the path was encoded as token in, fee, and then token out. For exact output single, this is the opposite. We start with token out, followed by fee, and then end with token in. The user will first call exact output single on swap router 02. Swap router 02 will call the function swap on Uniswap V3 pool contract. From Uniswap V3 pool, token out will be transferred to the user. Next, Uniswap V3 pool contract will call Uniswap V3 swap callback on swap router 02. Inside this callback, token in will be transferred from user over to the pool contract. Let's take a look at the call trace when the function exact output single is called. So, when the user calls the function exact output single on the swap router 02 contract, this function will first call an internal function called exact output internal. The internal function will call the function swap on the Uniswap V3 pool. Inside the function swap, it will execute many codes, but two of them will be to transfer token out, and then to call the callback, Uniswap V3 swap callback on the swap router 02 contract. Inside this callback, token in will be transferred from the user over to the pool. If a user wants a specific amount of token out from a swap, and the swap involves swapping between multiple pools, then they will call the function exact output. For example, let's say that this user wants 100 of token D. To get 100 token D, they first need to figure out how much token C they need. And to figure out how much token C that they need for this swap, they will first need to figure out how much token B that they will need. And again, to figure out how much token B that they will need, they will first need to calculate the amount of token A that they'll need to put in. So to execute this swap where the user puts in token A, and it will be swapped for token B, this token B will be swapped for token C, and finally this token C will be swapped for token D, the order of the swaps will be reversed. We first execute a swap from C to D, and then we execute a swap from B to C, and then finally we execute a swap from A to B. So first, the user will initiate the swap by calling exact output. Again, the swaps will happen in the reverse order that is shown here. So the first swap will happen with the pool having token C and D. The Uniswap V3 pool with token C and D will first transfer token D to the user, and then it will call the Uniswap V3 swap callback on the swap router 02 contract. At this point, token D has left the Uniswap V3 pool contract, and the swap router 02 contract owes token C to this pool. To pay for this token C that the swap router 02 owes to this Uniswap V3 pool contract, it will call a swap on the Uniswap V3 pool with tokens BC. Transfer the token C over to this Uniswap V3 pool contract. So, the swap router 02 will call the function swap on Uniswap V3 pool with tokens BC. Token C will be sent over to Uniswap V3 pool with tokens CD. And this completes the swap from token C to token D. However, for the pool with tokens B and C, token C has left, so the swap router 02 now has to pay this pool with token B. After token C is transferred, this pool will call the Uniswap V3 swap callback on the swap router 02. Now remember again that currently this swap router 02 owes token B to Uniswap V3 pool with token BC. To pay this pool with token B, the swap router 02 will call swap on Uniswap V3 pool with token AB. This would transfer token B from Uniswap V3 pool with token AB to the pool with BC. And this completes the swap from token B to C in this pool. But now we still have token A that we need to pay to this pool. This pool will call the Uniswap V3 swap callback on the swap router 02 contract. Inside the callback, token A will be transferred over from the user to Uniswap V3 pool contract. And this completes the last swap. Put in token A and transfer token B out. Next, let's examine the call trace when the function exact output is called. When the function exact output is called, it will make a recursive call into the internal function exactOutputInternal. The path is encoded in the reverse order of the swap. If you wanted to swap from token A to B and then from B to C and then from C to D, the path will be encoded as token D and then phi and then token C. These three parameters will specify the pool to swap token C to D. And then we're followed by phi and then the address of token B. These three parameters specify the pool to swap from token B to C. And finally, the last three parameters, the address of token B, phi, and the address of token A, specify the pool to swap from token A to token B. The function exactOutput will call internal function called exactOutputInternal. One of the parameters that is passed into this function is the recipient. For the first call, the recipient is set to the user. This recipient will be the receiver of token out. And inside this function, it will call the swap function on the pool contract. The pool contract that we first call is the pool for token C and D. Token C will come in and token D will come out. Inside the swap function, it will transfer token D to the recipient. Here, the recipient is the user. So, token D will be transferred over to the user. The amount of token that will be transferred here is the amount that the user specified. And then, it will call the Uniswap V3 swap callback on the swap router contract. Inside the callback, it updates this path parameter. We did a swap from token C to D, so we update it by removing token D. The new path will encode that we will need to swap from token B to C and then from A to B. And then it will call the function exactOutputInternal again. Notice here that we call the exactOutputInternal over here, and before this is done executing, inside it we call the function exactOutputInternal again. In other words, it's making a recursive call into the function exactOutputInternal. Notice that for the first call to exactOutputInternal, the recipient was the user. This user received token D. This time, the recipient is set to the pool with token CD. And then we will call the function swap on the pool BC. Token B is coming in and token C is going out. The recipient, here this will be pool CD, will receive token C. Inside the swap function, token C will be transferred over to the recipient. And again, this recipient is the pool CD. And then it's going to call the Uniswap V3 swap callback. Notice that the last time the Uniswap V3 swap callback was called, it updated the path and then called the internal function exactOutputInternal. And again, the code will execute in a similar manner. At this point, the swap from token B to C is completed. So we update the path to our final pool from token A to B. And then we call the internal function exactOutputInternal again. This time, the recipient will be pool BC. exactOutputInternal will call the function swap on pool with token AB. Token A will come in and token B will go out. The recipient will receive token B. In this case, the recipient is pool with token B and C. And this over here will complete the swap from token B to C. Next, it will call the Uniswap V3 swap callback again. And to finish this recursive call, the callback will transfer token A from user to pool AB. Token B left from this pool, and it expects token A to come in. And this transfer of token A from the user to the pool AB will terminate this recursive calls. And this is an example of what the call trace will look like for exact output. In this video, I'll do a code walkthrough for the contract swap router 02. The contract swap router 02 is used to swap tokens for Uniswap V3 pools. This contract is located under the repo called swap router contracts. The contract swap router 02 inherits two contracts, B2 swap router and B3 swap router. To swap with Uniswap V3, we'll look at the contract B3 swap router. So here it is over here. And inside it, we have several functions. The functions that we'll take a look at are exact input single, exact input, exact output single, and exact output. Let's start with exact input single. The function exact input single is used to swap a specific amount of token in for some amount of token out. The amount of token that the user desires to put inside the pool is specified by the user. The amount that comes out will be calculated by Uniswap V3 pool. And this function is called exact input single because it will only swap with a single pool. To swap with multiple pools, you'll need to call the function exact input, which we will take a look at later. The function first checks whether to swap the token using the balance of the token in inside this contract or to pull the token in from the caller. For simplicity, we'll say that token in will come from the caller. So has already paid, we'll assume is set to false. Okay? and then it's going to call an internal function called exactInputInternal. Let's take a look at what this function does. The function exactInputInternal is called both by the functions exactInputSingle and exactInput. Remember that in one of the previous videos we said that this path encodes the tokens and the fees which will identify the pool. And the order in which the tokens are encoded will tell which is token in and which is token out. For example, let's say that the path is encoded as A, fee, and token B. Then in this case, token in will be A and token B will be token out. If we had it the other way, let's say that we encode first token B, fee, and then token A. Then token B will be token in and token out will be token A. Now this function exactInputInternal will also be called by the function exactInput, or the function that you would call if you wanted to swap with multiple pools. For example, let's say that we wanted to swap from DAI to USDC on the DAI USDC pool with 0.1% fee, and then from USDC to WEF in the pool with 0.3% fee. Then the path must be encoded like this. Token in will be DAI, and then token out will be USDC. In the next swap, USDC will be token in, and WEF will be token out. Next, it checks whether this swap is a 0 for 1 by comparing the address of token in and token out. Okay, and moving on, it calls the function swap on the Uniswap V3 pool, which is computed by taking in, token out, and the fee. When this function swap is called, inside Uniswap V3 pool contract, it's going to call this function, and we said in a previous video that at the end, it's going to transfer the tokens, and then it's going to call the callback called Uniswap V3 swap callback. This callback is executed back inside the V3 swap router. So if you go all the way up, here it is the function. It's called Uniswap V3 swap callback. And inside here, this is an example of exactInput. So it will execute this part of the code. Pay token in from the payer. The payer will be the caller of the function exactInputSingle to message sender. This function was called by the Uniswap V3 pool, so message sender will be the Uniswap V3 pool. Pay from the caller to the Uniswap V3 pool for amount to pay. Okay, and that will complete the execution to the function Uniswap V3 callback. And then this swap function will return to here, and that ends the call to exactInputInternal. Moving on, let's take a look at the function exactInput. The function exactInput is similar to exactInputSingle. The caller will specify the amount of tokens that they want to put inside Uniswap V3, and Uniswap V3 will calculate the amount of tokens that will go out. The difference between exactInput and exactInputSingle is that exactInputSingle will only call swap with a single pool. On the other hand, exactInput will execute swaps with multiple pools. For example, if you wanted to swap from USDC to WEF, then you will call the function exactInputSingle. However, if you wanted to swap from DAI to USDC and then from USDC to WEF, then you will need to call the function exactInput. Again, the first part of this code would check whether to swap with tokens that is inside this contract or not. And for simplicity, we'll assume that token in will come from the caller to this function. So we assume that has already paid is set to false. In this case, the payer will be set to message sender. Next, we have a while loop. In each iteration of the while loop, it will call the function exactInputInternal and then execute this part of the code. If there are multiple pools left, this parameter is queried by calling the function hasMultiplePool on the input path. If it has multiple pools, then it will set the payer to this contract, and then from the current path, it will remove the first token that is encoded into path. As an example, imagine that path is encoded as token A, fee, token B, fee, C, fee, and D. On the first iteration, it will remove token A and fee. On the next iteration, it will remove token B and fee. And on the last iteration, this path no longer has multiple pools, so we'll be executing this part of the code. It will set amount out and then break from the while loop. So this is how the while loop works inside the function exactInput. On each iteration, it will call the function exactInputInternal to swap tokens with a single pool of Uniswap V3 pool contract. And then after the swap, it will remove a token and a fee from the path. When the path no longer has multiple pools, the while loop will exit, and we move on to this part of the code, which ends the execution for the function exactInput. Next, I want to go a little bit deeper into how exactInputInternal is called inside this while loop. So in the first iteration, notice that payer is set to message sender, and the recipient of the first token is set to address this. So when there are multiple pools to swap, the initial payer will be message sender, and the recipient of token out will be this router contract. In the last iteration, this boolean has multiple pool will be false, so the recipient of the last token will be the recipient set inside the parameter, and the payer, well, inside the while loop, payer is set to this contract. So for the last iteration of this while loop, token in will come from the router contract, and token out will be sent to this params.recipient. And that completes the code walkthrough for the functions exact input and exact input single. Moving on, let's do a code walkthrough for the function exact output single. The function exact output single is called when a user wants specific amount of token from a single Uniswap V3 pool contract. The Uniswap V3 pool contract will calculate the amount of token that must come in and then pull that amount of token in. This function will call an internal function called exact output internal. The function exact output internal, from the input called path, it will decode the token out, token in, and the fee. I want to show you how the path is encoded when the function exact output single is called. So let's go back, and you can see over here that the path is encoded as token out, fee, and token in. This is the reverse order of how path is encoded compared to exact input single. In exact input single, path will be encoded as token in, fee, and then token out. However, for exact output single, the path is encoded as token out first, fee, and then token in. So going back to the internal function, exact output internal, it will get the token out, token in, and the fees, and then calculate 0 for 1 by comparing token in and token out. Next, it will call the function swap on Uniswap V3 pool contract. Again, the Uniswap V3 pool contract will execute the function swap, and at the end of the swap, it will call a callback called Uniswap V3 swap callback. This callback is again executed inside a swap router contract. And inside here, since this call is an exact output, this part of the code will execute. And also for exact output single, we don't have multiple pools, so this part of the code will execute. What it does is asks the payer, which will be the caller of the function exact output single, to pay to the Uniswap V3 pool for amount to pay. Okay, that's exact output single. Next, let's take a look at the function exact output. The function exact output is the most difficult function to understand in this contract. The reason why it's difficult to understand is because exact output will make recursive calls to exact output internal. This function is similar to exact output single. User specifies the amount of token that they want to take out of Uniswap V3, and Uniswap V3 will tell the user how much token that must come in. The difference between exact output single and exact output is exact output single will only call swap with a single pool. Exact output will swap with multiple pools. For example, if you wanted one WEF from USDC WEF pool, then you will call exact output single. On the other hand, let's say that you wanted one WEF and you only had DAI. One way to get WEF from DAI is to first swap DAI for USDC and then USDC to WEF. In this case, the user will call the function exact output. And continuing with our example of swapping from DAI to USDC and then from USDC to WEF, for exact output, the order of the swaps will be in the reverse order. First, it will swap from USDC to WEF. This WEF will be sent over to the caller. Now this USDC WEF pool still needs USDC to come in to complete the swap. So this swap router contract will next execute a swap between DAI USDC pool. Send the USDC over to the USDC WEF pool and then pull the DAI from the caller. So you can see that it first swapped with USDC WEF pool and then it swapped with the DAI USDC pool. So let's take a look at the function exact output internal. Inside the function exact output internal, the parameter path is encoded as token out, fee, and then token in. For example, if we're swapping from DAI to USDC and then from USDC to WEF, the path will be encoded as WEF 3000. This is the pool fee, USDC 100, and then DAI. This part of the code will get the first pool. In our example, this will be WEF 3000 and USDC. Token out will be WEF and token in will be USDC. Okay, and moving on, it's going to call the function swap on the Uniswap V3 pool. The Uniswap V3 pool will call back into a callback Uniswap V3 swap callback. From here, this will be a swap with exact output, so this part of the code will execute. And for our example, it also has multiple pool, so this part of the code will execute. Now, notice that to get to this part of the code, the function exact output internal was called, which called a function swap on Uniswap V3, and the function swap called back into this function Uniswap V3 swap callback. And from here, we're calling back into this internal function called exact output internal. The function exact output internal calls back into the function exact output internal when there are multiple pools. It is making a recursive call. This part of the code is what makes the function exact output difficult to understand. So assuming that there are multiple pools, let's see what happens over here. First, it will remove the first token from the path. For example, if the path was WEF, USDC, and DAI, it will remove the first token. So it will remove the token, WEF, and fee. This new path will be passed to the function exact output internal. Okay, imagine that when this part of the code is executed, there are two pools to swap with. When this part of the code is executed, it will remove one pool, so we're only left with one pool. It's going to call exact output internal again. Going back to exact output internal, notice that this parameter recipient is now set to the pool that called into the Uniswap V3 swap callback. So if you go back up, you can see over here that this function exact output internal is called with message sender for the second parameter. The second parameter is recipient. Message sender to the callback Uniswap V3 swap callback is the pool itself. The recipient for the next swap is set to the previous pool contract. Okay, and it's going to call the function swap again. And if we started out with WEF 3000 USDC 100 and DAI, in this iteration, the path will be USDC 100 and DAI, and it's going to call the function swap on the pool USDC DAI. And again, this function swap will call back into the callback Uniswap V3 swap callback. This is still our exact output, so this part of the code will execute. However, at this point, let's say that the path is USDC 100 and DAI. It no longer has multiple pool, so this part of the code will execute. And in this case, it will transfer token in from the payer. The payer here will be the caller to the function exact output to message sender, so to the first pool. In our example, this will be the USDC DAI pool for amount to pay. And this part of the code will end the execution to the recursive calls to the function exact output internal. And this completes the code walkthrough for the function exact output and the function exact output single. There are 4 exercises to swap with the Uniswap V3 swap router 02 contract. I'll first explain the setup. So the setup is we have WEF, DAI, WBTC, and the router contract. This will be the swap router 02 contract. If you need to look at the interface, you can locate to source, interfaces, Uniswap V3, and then click on swap router. This is the interface that you'll need to use to call the functions to swap with Uniswap V3. The 4 exercises will be to call the function exact input single, exact input, exact output single, and exact output. Let's start with the first exercise, which is to call the function exact input single. So going back to the test file, the setup is that this contract will be allocated with 1000 DAI. You'll be swapping this DAI with WEF and also with WBTC. And this test contract has approved the router contract to spend DAI that is locked inside this contract. Okay, so the first exercise is to swap 1000 DAI that is locked in this contract for WEF on DAI WEF pool with 0.3% fee. Now, if you want to swap DAI for WEF in a pool with a different swap fee, feel free to do so. For your convenience, I've included a constant called pool fee, which is set to 3000. This is the pool fee for 0.3% fee. Okay, so the first exercise, I want you to call the function exact input single to swap 1000 DAI for WEF. To call the function exact input single, you'll need to look at the iSwap router interface, and if you look at the function exact input single, you'll need to pass in a parameter called exact input single params, which is over here. Token in, token out, and fee will determine the pool to swap on. Token in will be DAI, and token out will be WEF. For the recipient, set it to this test contract. Amount in will be 1000 DAI, and for amount out minimum, Here we'll keep it simple, and you can set it to 0 or 1. And likewise for square root price limit x96, we'll keep it simple, so you can just set it to 0. Okay, so that's the first exercise. Let's go over the solution for the first exercise. The first exercise is to call exact input single on swap router 02 contract. Over here, I'll call router.exact input single, and then we'll need to pass in the parameter. Navigating to the iSwap router interface, this is the struct parameter that we'll need to prepare. So I'll copy this, and then I'll paste it here. Inside this test file, the struct called exact input single parameter is not defined. It is actually imported as iSwap router. So over here, I'll need to type iSwap router dot exact input single. Token in will be DAI. Token out will be WEF. Fee, this will be the pool fee that will determine the pool. We're swapping on DAI WEF pool with 0.3% fee, and the fee is defined over here. So I'll type pool fee. Recipient will be the address that will receive token out. In this case, this will be WEF. This test checks that WEF is sent to this contract. So recipient will be the address this. Amount in, we're going to send 1000 DAI. So this will be 1000 times 1E18. DAI has 18 decimals. Amount out minimum, let's just say 1. And square root price limit x96. We'll set it to 0. That completes exercise 1. Let's try executing this test. We'll execute this test against the main fork, so I'll first set up the fork URL. And then we'll execute the test by typing forge test -- fork URL from the environment variable, match path, test, Uniswap V3, exercises. And the name of the contract that we're executing is called Uniswap V3 swap.test.sol. And I also want to display the console log, so I'll type -bbb. Okay, and our test passed. For putting in 1000 DAI, we currently get about 0.332 WEF. For the second exercise, I want you to call the function exact input on the swap router 02 contract. In this exercise, you'll be swapping 1000 DAI for WEF, and then from WEF to WBTC. This should be done in a single call to the swap router contract by calling the function exact input. The final token that comes out, which is WBTC, should be sent to this contract. Let's take a look at the interface for swap router 02 again. So inside swap router 02, you'll need to call the function exact input, and you'll need to prepare a struct, which will be the input. The struct name is called exact input params. You'll need to encode the path, which will encode the path from DAI to WEF, and then from WEF to WBTC. The recipient will be set to this test contract, and amount in will be 1000 DAI, and for amount out minimum, we'll keep it simple again, and you can set it to 1 or 0. And note that for this exercise, WBTC has 8 decimals. To execute the function exact input on swap router 02 contract, we first need to encode the path. For this exercise, we're going to swap from DAI to WEF, and then from WEF to WBTC. So path will be equal to abi.encode pact. We'll need to encode DAI, followed by the pool fee. Here I'll type uint 243000, and then token out will be WEF. This will be the first swap. The second swap will start from WEF, so WEF will now be token in. The pool fee is again uint 243000, and then token out will be WBTC. Next, we need to call the function exact input on the router contract. Router.exact input. Okay, going to the interface, we'll need to prepare this parameter. The struct exact input is not declared inside this contract, so it must be imported from iSwap router.exact input params. The path will be the path that we prepared above. Recipient will be this contract. Amount in will be 1000 DAI, 1000 times 1E18. Amount out minimum, let's just set it to 1. And this completes the code to execute the function exact input on swap router 02 contract. Let's try executing the test. Inside my terminal, I'll first set the environment variable for fork URL, and then we'll execute the test by typing forge test fork URL match path test Uniswap V3 exercises Uniswap V3 swap.test.sol. And our test executed successfully. We put in 1000 DAI. WBTC has 8 decimals. So we got back around 0.016 WBTC. For exercise 3, I want you to call the function exactOutputSingle on the swap router 02 contract. And in this exercise, I want you to call the function exactOutputSingle to swap a maximum of 1000 DAI to obtain exactly 0.1 WEF. And the WEF that comes out from the swap should be sent to this test contract. The function that you'll need to call is exactOutputSingle. Let's take a look at the interface for exactOutputSingle. ExactOutputSingle will be this function. And again, you'll need to prepare this parameter to pass to this function. Token in, token out, and fee will determine the pool to swap on. Recipient will be this test contract. Amount out will be 0.1 WEF. Amount in maximum will be 1000 DAI. Here we're saying that we're willing to spend a maximum of 1000 DAI and we want exactly 0.1 WEF. And for square root price limit x96, again we'll keep it simple and set it to 0. Okay, so that is exercise 3. Call the function exactOutputSingle. Let's go over the solutions for how to call exactOutputSingle on the swap router 02 contract. First, I'll type router.exactOutputSingle, and let's check back the interface to see what parameter we need to prepare to call the function exactOutputSingle. Okay, here is the function exactOutputSingle, and we'll need to prepare this parameter. We'll need to import this struct called exactOutputSingle params. This is from iswap router.exactOutputSingle params. Token in. We're swapping DAI for WEF, so this will be DAI. Token out will be WEF. Fee will be 3000, or we can use the constant that is defined in this contract, pool fee. Recipient will be this contract. Amount out. In this exercise, we want to get out 0.1 WEF. WEF has 18 decimals, so 0.1 WEF will be 0.1 times 1e18. Amount in maximum. We're willing to spend up to 1000 DAI. 1000 times 1e18. Square root price limit x96. Set it to 0. Okay, let's try executing the test. Set the fork URL as an environment variable, and then execute the test, forge test, fork URL, match path. The path for this test is test Uniswap V3 exercises, Uniswap V3 swap.test.sol. Okay, and our test passed. To get 0.1 WEF, we had to spend about 300 DAI. For the last exercise, I want you to call the function exactOutput on swap router 02. In this exercise, I want you to swap maximum of 1000 DAI to obtain exactly 0.01 WBTC. Swap DAI to WEF and then from WEF to WBTC. Send the WEF back to this test contract. Now note again that WBTC has 8 decimals. Okay, let's take a look at the function declaration exactOutput inside the interface for swap router 02. The function exactOutput is going to take in a single parameter, which is this struct, so you'll need to prepare this struct to call the function exactOutput. The first parameter path will encode the tokens to swap and the pools to call. Remember that for exactOutput, path must be encoded in the reverse order of the tokens. In this exercise, you'll be swapping from DAI to WEF and then from WEF to WBTC. So the path must be encoded as WBTC, WEF, and then finally DAI. The recipient will be this test contract. Amount out will be 0.01 WBTC, and amount in maximum will be 1000 DAI. Okay, so that is the last exercise. Call the function exactOutput on swap router 02. Let's go over the solution for the last exercise to swap with Uniswap V3. In this exercise, we will need to swap from DAI to WEF and then from WEF to WBTC. And we also want exactly 0.01 WBTC, and we're willing to spend a maximum of 1000 DAI. So we first need to prepare the parameter. This will be avi.encode packed. Remember that for exactOutput, we need to list out the tokens and the fees in the reverse order. Here we're swapping from DAI to WEF and then from WEF to WBTC. This order needs to be in the reverse order, so we start out with WBTC. The fee for WBTC WEF will be 3000, so uint24 3000, and then followed by WEF Next, we need to encode the pool from DAI to WEF with pool fee 3000. So again, uint24 3000 and then DAI. Next, we'll call the function exact output on the swap router 02 contract. Router.exact output. Let's check the interface and see what parameter we need to prepare. This is a struct that we need to prepare. Again, we'll need to prefix this with I swap router dot exact output params. The path is the parameter that we prepared above. Recipient will be this contract. Amount out. For this exercise, we want exactly 0.01 WBTC. And WBTC has 8 decimals, so this will be 0.01 times 1e8. Amount in maximum. The maximum amount of DAI that we're willing to spend in this swap is 1000 DAI. 1000 times 1e18. Okay, this completes the code for calling the function exact output on swap router 02. Let's try executing this test. Set the fork URL environment variable, and then execute the test, forge test, fork URL. The path is Uniswap V3 exercises, Uniswap V3 swap.test.sol. Okay, and our test passed. To receive 0.01 WBTC, we had to spend roughly 605 DAI. Uniswap V3 uses create2 to deploy the pool contract Uniswap V3 pool. Because it uses create2, the address of the pool contracts can be determined before they are deployed. But the way the factory contract deploys the pool contracts is not straightforward. So in this video, I'll explain how the Uniswap V3 factory contract deploys the pool contracts. We will first begin with a review of create2. How does create2 compute the contract address? To compute the address, we'll need to take the Keccak 256. The first input will be 0xFF. The next input will be the address of the deployer, the address that deploys the contract. Next will be a random 32 bytes called salt. This will be specified by the deployer. And the last input will be the Keccak 256 of the contract's creation bytecode. When you compile and deploy a contract, there are 2 bytecodes that are produced. When you deploy a contract, it first sends the creation bytecode. The creation bytecode will be executed, do some setups, and deploy the runtime bytecode. Loosely speaking, creation bytecode is the bytecode of the contract and the constructor. And then the next input for this Keccak 256 will be the constructor inputs. After taking the Keccak 256 of these inputs, you would take the last 20 bytes, and this will produce the address determined by create2. Now notice that since we're taking the Keccak 256, there are several inputs that will change the address of the contract. The things that will change the address are the address of the deployer, salt specified by the deployer, and this inner Keccak 256. Assuming that we're deploying the same contract, the creation bytecode will always be the same, and constructor inputs might be different. So, assuming that the deployer and the contract that we're deploying are the same, there are 2 parts that will change the address of the contract. The 2 parts that can change the address of the contract are the salt and the constructor inputs. And why do we need this salt? Well, imagine the case that we want to deploy the same contract at a different address with the same constructor inputs. For example, you might want to deploy multiple ERC20 contracts with the same constructor inputs. In this case, you'll need to change the salt to get a different address. Okay, so this is a review of create2. Let's now look at how Uniswap V3 factory contract uses create2 to deploy the pool contract. Here's how the address of a Uniswap V3 pool contract is calculated using create2. We take the last 20 bytes of Keccak 256 of the following inputs: 0xFF, deployer. Here the deployer will be the address of the factory contract. The salt will be the Keccak 256 of token 0, token 1, and fee. And for the last input, remember that we take the Keccak 256 of the creation bytecode and the constructor inputs. Here the creation bytecode will be that of the Uniswap V3 pool contract. And notice that there is no constructor inputs. This is how the address of Uniswap V3 pool contract is calculated. As I mentioned earlier about salt, since this contract has no constructor input, we need to specify a unique salt so that we can deploy Uniswap V3 pool contract at different addresses. And now you may have several questions. For example, why is the salt set to the Keccak 256 of token 0, token 1, and fee? And furthermore, why is there no constructor inputs when we initialize this Uniswap V3 pool contract? How do we initialize the Uniswap V3 pool contracts without passing any constructor inputs? To understand how the address of Uniswap V3 pool contract is calculated in that manner, we first need to understand the goals that we need to achieve when Uniswap V3 pool contract is deployed. The first goal is that the pool address must be determined by the following inputs: token 0, token 1, and fee. If we know token 0, token 1, and fee, then we can calculate the address of the pool contract. And it doesn't matter whether the pool contract is already deployed or not yet deployed. The second goal that must be achieved when the pool contract is deployed is the initialization parameters of the contract. Inside the pool contract, we'll need to initialize token 0, token 1, fee, the address of the factory contract, and tick spacing. Tick spacing means that every time there's a swap and the price changes, then the tick will jump by this amount of tick spacing, instead of increasing or decreasing by 1. For example, if the tick spacing is 10, then the tick will increase or decrease by multiples of 10. Remember what I said earlier, that given that the address of the deployer and the contract to be deployed are the same, then the only two inputs that we can play around with to change the address of the pool contract is a salt and the constructor inputs. But the first goal, that says that the pool address is determined by these parameters, tells us that token 0, token 1, and fee must be equal to either the salt or the constructor inputs. In other words, when we look at the inputs for the salt and the inputs for the constructor inputs, they must be equal to token 0, token 1, and fee. For example, you can take the Ketchak 256 of token 0 as salt, and for the constructor inputs, you'll need to put in token 1 and fee. Another example is you can take the Ketchak 256 of token 0, token 1, and fee as salt, and have no constructor inputs. This first goal restricts that the inputs to the salt and the constructor inputs must be equal to token 0, token 1, and fee. With this in mind, let's take a look at the second goal. We have token 0, token 1, and fee that needs to be initialized. Furthermore, we have more inputs that needs to be initialized: factory address and tick spacing. And from our first restriction, this tells us that the factory address and the tick spacing cannot be part of the constructor input. If they were, then this would change how the create2 address of the pool contract is computed, which in turn means that the pool address cannot be calculated just by these three inputs. So we have a problem here. We want to be able to calculate the pool address by three inputs, and we need to initialize these parameters, but not all of these parameters can be passed as constructor inputs. So how does Uniswap V3 achieve these two goals? The solution is to set the salt as Ketchak 256 of token 0, token 1, and fee, and have no constructor inputs. This will achieve our first goal. To achieve the second goal, Uniswap V3 factory contract temporarily stores the initialization inputs inside the factory contract. And when the Uniswap V3 pool contract is deployed, it will read this data from the factory contract. Let's see how this is actually executed. To deploy a Uniswap V3 pool contract, the user will first call a function called createPool on the Uniswap V3 factory contract. Next, the factory contract will store the following initialization parameters: factory, token 0, token 1, fee, and tick spacing as a state variable into the factory contract. And then it will deploy the Uniswap V3 pool contract using create2. Here, these initialization parameters are not passed. Inside the constructor of Uniswap V3 pool contract, it will get these initialization parameters by reading the state variables that are stored inside Uniswap V3 factory contract. And this is how Uniswap V3 pool contract is deployed using create2. Finally, let's also take a look at the call trace. First, the user will call the function createPool with the inputs token 0, token 1, and fee. The factory contract will call an internal function called deploy, passing in the address of the factory, token 0, token 1, fee, and tick spacing. This input tick spacing will be a setting that is stored inside the Uniswap V3 factory contract. And this internal function will first store the initialization parameters: factory, token 0, token 1, fee, and tick spacing. Next, it will deploy the Uniswap V3 pool contract using create2. Here, the salt is set to the Ketchak 256 of token 0, token 1, and fee. And also notice that there are no constructor inputs. And this also means that the address of all Uniswap V3 pool contracts can be determined by these three inputs. Inside the constructor of Uniswap V3 pool contract, it will get the initialization parameters from message sender. Here, message sender will be the factory contract. And again, this initialization parameter was stored over here. And once the Uniswap V3 pool contract is deployed, we return back to the internal function deploy, and it will delete the initialization parameters. This is the call trace for the function create pool. There are two exercises for Uniswap V3 factory contract. For the setup, it deploys two ERC20 contracts, which will be used in exercise 2. In exercise 1, I want you to get the address of the USDC pool with 0.1% fee. To get the address of this pool, you'll need to call the function getPool from the interface Uniswap V3 factory contract. Let's go over the solution for exercise 1. Get the address of the pool for the USDC with 0.1% fee. So to get the address of the pool, we'll need to call factory.getPool. And checking back on the interface for Uniswap V3 factory, to call the function getPool, we'll need to pass in 3 parameters: address of token A, token B, and fee. Here, it doesn't matter if we pass in DAI and USDC or USDC and DAI. In either case, we'll get the same pool address. So to the function getPool, we'll pass in the inputs DAI, USDC, and how do we pass in the fee? For 0.1% fee, when the pool fee is calculated, the denominator is 10 to the 6, 1e6, and 0.1% will be 100 divided by 1e6. You can verify this using your calculator. So moving on, for the pool fee, we'll pass in 100. Before we execute exercise 1 on the mainnet fork, I'll first delete exercise 2 for now. Inside my terminal, I'll set an environment variable named forkURL. And then we'll execute the test forge test forkURL set to the forkURL from the environment variable, and the path to the test is test Uniswap V3 exercises Uniswap V3 factory.test.sol. Okay, and our test passed. The second exercise is to deploy a new Uniswap V3 pool contract using the tokens, token A and token B, which are deployed inside the setup. And the pool fee will be 0.1%. To deploy a pool, inside Uniswap V3 factory, inside the interface, Uniswap V3 factory, you'll need to call the function called createPool, passing in the inputs, token A, token B, and fee. This function will return the address of the pool that was deployed. Call the function createPool on the factory contract and assign the address of the pool that was deployed to this variable. Let's go over the solution for exercise 2. To deploy a pool, we'll need to call factory.createPool, and the 3 inputs that we need to pass are token A, token B, and fee. For token A, we'll pass in address of token A, address of token B, and for the fee, we'll need to pass in 0.1, which is 100. Okay, that completes this exercise. Let's try executing exercise 2. Inside the terminal, I'll execute the same test command again, forge test forkURL with the forkURL environment variable, match path. The path of the test is test Uniswap V3 exercises, Uniswap V3 factory.test.sol. Okay, and our test passed again. When adding or removing liquidity from a Uniswap V3 pool, you might have several questions. For example, you might be wondering how to calculate the amount of token X and the amount of token Y to add liquidity, given a price range. Or if you're removing liquidity, you might wonder the amount of token X and the amount of token Y that you will receive for removing liquidity. All of these questions can be answered by 3 equations. But to get there, we first need to derive an equation for liquidity, given the amount of token X, amount of token Y, and the price ranges and the current price are known. So in this video, we'll derive the equations for how to find liquidity, given the amount of token X, amount of token Y, the current price P, and the 2 price ranges P lower and P upper. Recall that in one of the previous videos, we derived the equation for the amount of token X and the amount of token Y between price ranges P lower and P upper. We will be using these 2 equations to derive the equation for liquidity. Let's say that we have some price range PA and PB. And imagine the case where the current price P is less than or equal to the lower price P of A. In this case, liquidity will all be in token X. And this is because for the current price P to swing from P of A to P of B, this much amount of token X must exit the pool. So in this case, what is the equation for liquidity? Well, to derive this equation, we will be using these equations. So I'll copy this equation and then paste it here. And we'll replace P lower and P upper with PA and PB. P lower will be PA and P upper will be PB. From this equation, we can now derive an equation for the liquidity. To begin with, I'll copy this equation, and I'll first simplify the right side of the equation. We have an L here and an L here, So we can factor this out and put a 1 here, and also put a 1 here, and these will be in parentheses. Next, I'm going to flip this equation around, so I'll bring the x over here. Now we can see that if we divide the left side of the equation by these terms, then we'll get an equation for L. And this is the equation for liquidity L, given that we know the amount of token X and the price ranges PA and PB. Now, inside the code of Uniswap V3, you'll see this equation in another form. What you'll see is this equation on the right. The way to get to this equation starting from this equation is to do some algebra on the denominator. So this is how liquidity is calculated when the current price P is less than or equal to the lower price P of A. Next, we'll derive the equation for liquidity when the current price P is above the upper price P of B. Again, let's say that we have two price ranges, the lower price P of A and the upper price P of B. And imagine the case where the current price P is above this upper price P of B. In this case, the liquidity between P of A and P of B will all be in token Y. And this is because for the current price P to swing from P of B all the way down to P of A, this much amount of token Y must exit the pool. Now to derive the equation for the liquidity L, again we'll apply this equation. Here P upper will be PB and P lower will be PA. Now to get the equation for the liquidity L, I'll first paste this equation again, and the first thing that I'll do is factor out liquidity L. We'll have a parentheses here, remove this L, it comes out of the parentheses, and then we'll have another parentheses. Next, I'm going to flip this equation so that the Y will come over here, and this L times these terms will come to the left. And now to get the equation for liquidity L, all I have to do is divide these terms. And we get that when the current price P is greater than or equal to the upper price P of B, then liquidity is equal to Y divided by square root of P of B minus square root of P of A. The last case we'll consider is what happens when the current price P is between the price ranges P of A and P of B. Then what is the equation for liquidity? Well, to answer this question, all we have to do is apply the equations that we have derived so far. Now the liquidity between the price ranges P to P of B will all be in token X, and the liquidity between P to P of A will all be in token Y. And these two liquidity are not necessarily equal, so we'll label them separately. We'll call L of X to be equal to the liquidity from current price P to the upper price P of B. And then for the liquidity from the current price P to P of A, we'll call this L of Y. Let's first derive the equation for the liquidity between the current price P to P of B. Scrolling back up, all we have to do is apply this equation. And we have one small thing that we'll need to change. In the last case, we consider the case for the lower price P of A. So in the equation, we'll have P of A over here. In this example, our lower price will be the current price P. So what we have to do is replace this P of A with the current price P. And this is the equation for liquidity between the price ranges P to P of B. We'll do something similar to derive the equation for L of Y. So I'll scroll back up and then copy this equation. And note here that for this equation, we considered when the current price P is greater than or equal to the upper price P of B. And you can see this P of B over here. In our case, in this case, the upper price will be the current price P, so we'll replace this P of B with the current price P. And these two equations tell us the liquidity between the current price P to P of B and the liquidity from P of A to P. Now that we know how to calculate liquidity, given that we know the amount of token X, the amount of token Y, current price, and the price ranges P of A and P of B, we can now answer the question, what is the amount of token X and the amount of token Y that must be added when we're adding liquidity? And likewise, what is the amount of token X and the amount of token Y that will be removed when we remove liquidity? These two questions can be answered now. We'll first define two variables. L0 will be liquidity before, and L1 will be liquidity after. For example, L0 can be liquidity before adding liquidity, and L1 is liquidity after adding liquidity. Or it can be L0 is liquidity before removing liquidity, and L1 is after removing liquidity. And we'll define delta L to be equal to L1 minus L0. We're just taking the difference of the liquidity. And in this video, we'll answer the question, how much delta X and how much delta Y to add or remove if liquidity changes by delta L between the price ranges P of A and P of B. Let's start with the case where the current price P is less than or equal to the lower price P of A. And in this video, we'll consider the case what happens to liquidity when we add liquidity. The math for liquidity delta when we remove liquidity is exactly the same. So let's say that we have liquidity L0 between the price ranges P of A and P of B. And let's say that in this price range, we add some delta X and the liquidity increases from L0 to L1. In this case, what is the equation for liquidity delta? Remember again, liquidity delta, we defined it as L1 minus L0. We derived in the previous video that liquidity is equal to X divided by 1 over the square root of P of A minus 1 over the square root of P of B. For L1, we can apply the same equation, except the amount of token X will be different. In this case, the amount of token X will be the amount of token X that was before adding liquidity, plus the amount that was added, delta X. And we're now ready to answer the question, what is delta L? By definition, it is equal to L1 minus L0. When we subtract L1 from L0, on the numerator we're left with delta X, and the denominator is the same, so we get this equation. This is the equation for delta L when the current price P is less than or equal to the lower price P of A. And what does this equation tell us? How is it useful to us? Well, let's say that you're adding liquidity to a price range that is above the current price P. In this case, the current price P will be less than or equal to the lower price that you set, P of A. When we apply this equation, we can tell the change in liquidity, and we can also tell the amount of token X that we need if we were to change the liquidity by this much amount. So for example, let's say that we know the amount of token X to put in between the price ranges P of A and P of B, and the current price P is less than or equal to P of A. Then using this equation, we can tell the change in liquidity. Another application is, if we knew the change in liquidity, then we can figure out the amount of token X that we need to put in. Next, we'll derive the equation for delta L, liquidity delta, when the current price P is above or equal to the upper price P of B. To begin with, let's say that we started with liquidity L0. To this, we add some amount of delta Y, and the liquidity increases from L0 to L1. Okay, let's now calculate delta L. Let's start with L0. We apply the equation that we derived in the previous video, and we do the same for L1. For L1, the amount of token Y has changed. Since we added liquidity, we added this much amount of token Y, so the amount of token Y that we put up here as a numerator is the previous amount of token Y plus the amount that we added just now, delta Y. Now that we know L1 and L0, we can now calculate delta L. Again, by definition, this is equal to L1 minus L0. And notice that the denominator for L0 and L1 are the same. The only difference is the numerator. When we subtract the numerator of L1 from the numerator of L0, we are left with delta L. So the equation becomes delta L is equal to delta Y divided by the square root of P of B minus the square root of P of A. Again, the same question. What does this equation tell us and how is it useful? Well, it tells us the amount of token Y that we need and the change in liquidity if we were to add liquidity below the current price P. For example, let's say that we have some amount of token Y and we want to add liquidity between the price ranges P of B and P of A, and the current price P is greater than or equal to the upper price P of B. So we know the amount of token Y that we need to put in, we plug in all the numbers, and we get the change in liquidity. Another way to use this equation is, if we wanted to change the liquidity by delta L, then this equation tells us that we need this much amount of token Y. For the last case, we will consider when the current price P is between the lower price P of A and the upper price P of B. In this case, between the price ranges P of A and P of B, we have some amount of token X and some amount of token Y. Let's say that we added delta X amount of token X and delta Y amount of token Y, and the liquidity increased to L1. In this case, what is the equation for delta L? To answer this question, we first need to follow a rule that says that liquidity between the price ranges P to P of B must be equal to the liquidity between P to P of A. This is a special rule that only applies when the current price P is in between the lower price P of A and the upper price P of B. So let me say it again. The liquidity from the current price P to P of B must be equal to the liquidity from P of A to P. With this in mind, let's calculate L0 and L1. L0 is equal to, In the previous video, we derived that L0 is equal to this expression. Now this liquidity is the liquidity from the current price P to P of B. And this must be equal to the liquidity from P of A to P. The liquidity from P of A to P is given by this equation. So this is the equation that L0 satisfies. And for L1, we'll have similar equations. Here's the liquidity between the price P to P of B. And note that since we added delta X, on the numerator we have the previous X plus delta X. And this must be equal to the liquidity from P of A to P. And again, note that on the numerator we have delta Y because we added some amount of token Y. So these two equations must be satisfied for L1. Let's now calculate delta L. By definition, delta L is equal to L1 minus L0. For L1 minus L0, if you look at this side of the equation, if we do L1 minus L0, we see that the denominators are the same, and for the numerator, we'll have x plus delta x minus x. So evaluating this side of the equation, we get that delta L is equal to delta x divided by 1 over the square root of current price P minus 1 over the square root of P of B. And likewise, we'll do the same for these two equations. L1 will be this, and L0 will be this. When we subtract it, on the numerator, we're left with delta y. And the denominator is the same over here and over here, so we'll have the same denominator after subtracting. And this is equal to delta y divided by the square root of p minus square root of p of a. Okay, but what do these equations tell us? And again, how do we use these equations? Well, it tells us that if we were to add liquidity by delta L, then this is the amount of token X that we need to put in, and this is the amount of token Y that we need to put in. Another application is, let's say that we know the amount of token X that we want to add liquidity between the current price P and the upper price P of B. Then we'll have the question, what is the amount of token Y that we'll need to put in between the price P and P of A? Using this equation, you'll be able to solve for delta Y and answer that question. When a liquidity provider adds liquidity to a Uniswap V3 pool, they'll specify a price range. The lower tick and the upper tick that defines this price range cannot be any arbitrary tick. It has to be a multiple of tick spacing, and this tick spacing is different for each pool. For example, here I have a tick space of 10, and the vertical dotted line represents the ticks that are multiple of this tick space. If you were to add liquidity to this pool, for the lower tick and the upper tick that defines the price range, they have to be a multiple of the tick space. So for example, I can set the lower tick to minus 20 and the upper tick to minus 10. Both of these are multiples of the tick space 10, so they are valid price range to add liquidity. However, in this pool, you won't be able to add liquidity for the price ranges tick equal to minus 20 and tick equal to minus 15. This is because minus 15 is not a multiple of the tick space 10. As I mentioned earlier, different pools have different tick spacing. For example, the USDC DAI pool with 0.01% swap fee has a tick space of 1. On the other hand, the DAI WEF pool with 0.3% swap fee has a tick space of 60. The reason why different pools have different tick spacing is to pick between the concentration of liquidity and the consumption of gas. Lower tick space means liquidity can be concentrated higher, at the cost of using more gas during the swap. On the other hand, higher tick spacing means that liquidity can be concentrated less, and also, during the swap, less gas will be consumed. For example, if we had a tick spacing of let's say 4, since the smallest price range that we can add liquidity to gets smaller, for putting in the same amount of tokens, we will have higher concentration of liquidity. Now during the swap, inside the code of a Uniswap V3 pool contract, it will execute a while loop, and inside this while loop, it will execute a smaller swap between these tick spaces. So for example, we have a current price over here, and as the swap is executing, on the first iteration, it will execute a swap in between these two pink lines, and then in the next iteration, it will swap in between these two pink lines. In the next iteration of the while loop, it will execute a swap in the next multiple of tick spacing. So in this case, to swap from here to all the way to here, we have to iterate through once, twice, and 3 times to move the tick from tick equals to 0 to tick equals to minus 10. So this is how pools with lower tick can consume more gas during a swap. On the other hand, let's consider what happens when the tick spacing is a larger number. For example, let's set the tick spacing equal to 10, and we'll start with the current tick equal to 0 again, and we'll swing it over to -10. So again, let's say that there was a swap, and this would decrease the tick from tick equal to 0 to tick equal to -10. As the tick moves over to -10, we now enter the first iteration of the while loop inside the code of Uniswap V2 pool contract. And then as the tick decreases further, we hit tick equals to -10. And at this point, we only iterated once. In the case of tick spacing equal to 4, we iterated 3 times. In the case tick spacing equals to 10, we only iterated once. The tick jumped the multiple of tick spacing only once in this case. So this is what it means that pools with higher tick spacing may consume less gas during the swap. Now, pools with higher tick spacing also comes with a cost of lower concentration of liquidity. And this is because the minimum price range that we can add liquidity is larger compared to a pool with lower tick spacing. When we look at a pool with tick spacing, let's say equal to 5, then the minimum price range that we can add liquidity is this much. However, for tick spacing equal to 10, the minimum price range that we can add liquidity is larger. Larger price range means that we can concentrate our liquidity less. So in summary, when you add liquidity, the price range that you specify has to be a multiple of the tick spacing, which is different for each pool. Pools with lower tick space can concentrate liquidity higher, but during a swap, it may use up more gas. Pools with higher tick spacing can concentrate liquidity less, but during a swap, it may use up less gas. Pools with low tick spacing are suitable for token pairs where the price has low volatility. For example, USDC DAI pair. Pools with high tick spacing are suitable for token pairs where the price has high volatility. For example, DAI WEF pair. To add liquidity to a Uniswap V3 pool, the function mint inside a contract called Uniswap V3 pool, which is inside the repo V3 core, must be called. Now this function is a low-level function, and if you're adding liquidity as a user, you'll be interacting with another smart contract. The standard contract to interact with is called non-fungible position manager, which is inside the repo V3 periphery. This non-fungible position manager will call into the Uniswap V3 pool contract. In this video, I'll briefly explain what's going on inside the function mint. The function mint is both used to add liquidity for the first time and also to increase liquidity. The parameters to pass are recipient. This will become the owner of the position, and the parameters that specify the position: tick lower, tick upper, and amount. This will be the amount of liquidity to add to the position that is defined by tick lower and tick upper. And this arbitrary data will be passed as a callback to message sender. You can see this data over here. We'll come back to this later. So going back up, these are the parameters. And for the output, it will return the amount of token 0 and amount of token 1 that was needed to add this much amount of liquidity. Inside the function, it first calls an internal function called modify position. The parameter to this function are the owner, which will be the recipient that is specified by the input, the two ticks, tick lower and tick upper, and here we have a parameter called liquidity delta, which is defined by the amount from the input. This liquidity delta tells the internal function modify position to modify this position specified by these three inputs by this much amount of liquidity. Notice that this amount can both be a positive number and a negative number. Okay, let's take a look at this internal function called modify position. The function modify position will take in a struct parameter called modify position params that we saw earlier. And then for the output, it's going to return the position that was either created or updated, and the amount of tokens that must come into the pool or the amount of tokens that must leave the pool, depending on liquidity delta. If liquidity delta is positive, this means that we're trying to increase the liquidity of this pool, so amount 0 and amount 1 will be positive. If we're trying to decrease the liquidity from this pool, then amount 0 and amount 1 will represent the amount of tokens that is leaving the pool, so these numbers will be negative. Okay, so first, it checks ticks. Make sure that tick lower and tick upper are valid ticks. And then it will get slot 0 to save some gas, and then it will call internal function called update position. Let's take a look at this function, update position. Scrolling down, here's the internal function called update position. The first four parameters are obvious. Owner will be the recipient, the two ticks that define the position, and liquidity delta to update the position by. And then the tick will be the current tick. This current tick will be stored in slot 0. And this function is going to return the position. First, it gets the position, which is defined by the owner, tick lower, and tick upper. Next, it will load two state variables into a local variable. These state variables are fee growth global 0x128 and fee growth global 1x128. These two state variables are used to track fees for liquidity providers. Scrolling down, we have a if condition. If liquidity delta is not equal to 0. First, it will store some price information for the time-weighted average pricing price oracle. And then it will call the function update on ticks. Let's take a look at what this function does. This function is inside the library called tick, and scrolling down, the function that I'm looking for is called update. When this function update is called, first it's going to load the data that is stored inside the storage mapping. From the tick, it will load a struct called tick.info, which stores these information. And then it will compute the next liquidity in this tick by taking the liquidity before and then adding liquidity delta. If the liquidity that is stored at this tick was equal to 0, then here it will initialize a tick. If the current tick is less than the tick to store the info for, then it will initialize some parameters. And then set the flag called initialize to true. And then it will update the liquidity. And the last part of this function is to update liquidity net. Remember that liquidity net is a number that is used to update the current liquidity when there is a swap. And this is done either by storing a positive or a negative number at the tick. When the current tick crosses over this tick, it will add this liquidity net to the current liquidity to get the new liquidity. Okay, so this is the function ticks.update. Let's go back to the function Uniswap V3 pool. So it will call the function update on the lower tick and also on the upper tick. And then next, if the ticks for lower tick and the upper tick, if either of them were flipped, here flip means either liquidity before was equal to 0 and liquidity after is greater than 0, or liquidity before was greater than 0 and liquidity after is equal to 0. In this case, it will store the tick in a mapping called tick bitmap. This is a data structure that is used during a swap to efficiently find the next tick. Next, it will calculate the fee growth inside tick lower and tick upper. And this fee growth inside is used to calculate the fee that is owed to this position. So let's take a look at the function position.update, which for the inputs, it will pass in liquidity delta and fee growth inside 0x128 and 1x128. The function position.update will be inside the library called position and the function called update. The first part of the code will update the liquidity by liquidity delta. Next, it will calculate the amount of tokens owed to this position. And here, this tokens owed 0 and tokens owed 1 is the amount of fee that was collected for this position. The way it calculates this is to take the latest fee growth inside and then minus it by the previous fee growth inside. Multiply this by liquidity and then divide it by 2 to the 128. And this is how fee is calculated. This is done both for token 0 and for token 1. We'll come back to how this actually calculates the fee for this position in another video. So moving on, it will update the liquidity and it will also update fee growth inside. And lastly, if there was any fees that were collected, then it will update this by incrementing it by the amount of fee that was collected. Okay, so going back to Uniswap V3 pool contract, the last part of this code is to remove the ticks if liquidity was removed and the liquidity at this tick is equal to 0. So that's the function update position. This function was called by the function modify position. So we'll go back to here. The function modify position calls the function update position. So moving on, the next part of the code inside this if condition, if params that liquidity delta is not equal to 0, calculates the amount of token 0 and the amount of token 1 that is needed to change the liquidity by liquidity delta. If the current tick is less than tick lower, then liquidity is all in token 0, so the amount that we'll need to calculate will just be in token 0. So here we calculate amount of token 0 that is needed. Otherwise, if the current tick is less than tick upper, so in this case, we have the current tick in between the two ticks, tick lower and tick upper. And in this case, we'll need to calculate both token 0 and token 1 to change liquidity by liquidity delta. And you can see this over here. Inside here, since we're modifying the current liquidity, we'll also need to update the current liquidity, which is done over here. Otherwise, The current tick is above tick upper. In this case, liquidity will all be in token 1. So here we calculate the amount of token 1 that is needed to change liquidity by liquidity delta. And that completes the function modify position. Basically what it does is updates the position that is defined by the owner and the two ticks, tick lower and tick upper, and then it calculates the amount of token 0 and amount of token 1 that must either come into the pool or leave the pool. So that completes the function modify position. Let's now go back to the function mint. Inside the function mint, after calling the function modify position, it's going to use two of the outputs that was returned, amount 0 and amount 1. Notice that here they are both in int 256 to represent either tokens coming in for positive and negative for tokens going out. Since we're adding liquidity, here we assume that this amount 0 int and amount 1 int are both positive number. So here we'll cast it into uint 256. And with these amount 0 and amount 1, it will call a callback called Uniswap V3 mint callback on message sender. And inside here, message sender must send an amount 0 of token 0 and amount 1 of token 1 into this contract. And after this callback is executed, this code checks that the balance increased by amount 0 and amount 1. And that completes the code walkthrough for the function mint. To add liquidity, the function mint is called inside the contract Uniswap V3 pool. To remove liquidity, we'll need to call the function burn. This function burn is a low-level function, and if you are a regular user, then you won't be calling this function directly. Instead, you will probably call the contract non-fungible position manager, which will call into the function burn. For the inputs, it takes in three inputs: the two ticks that define a position, tick lower and tick upper, and the amount of liquidity to remove. For the output, it's going to return the amount of liquidity that was removed, amount 0 and amount 1. Now this function removes liquidity, but surprisingly, it does not transfer the tokens amount 0 and amount 1. To actually transfer the tokens, we'll need to call another function called collect, which we'll do a code walkthrough later. So the function burn is used to remove liquidity. Inside the function, it first calls a function called modify position. And for the parameters, for the owner, it's going to pass in message sender and the two ticks, tick lower and tick upper. For liquidity delta, notice that it's passing in a negative amount. Since we're removing liquidity delta will be negative. We already discussed how the function modify position works when we looked at the code for the function mint. So we'll omit the explanation here. What's important to notice here is that the position here is defined by message sender and the two ticks. So this means that only the owner will be able to remove liquidity from their position, since the only position that they can remove liquidity from is the position that they own. This function modify position returns three outputs: the position and amount of token 0 and amount of token 1 that must exit this pool when the liquidity in this position is updated by liquidity delta. This amount 0 and amount 1 will be negative, so here we cast it into a positive number. And if either of these is positive, then we update the position by incrementing tokens owed 0 and tokens owed 1. And again, notice that just by calling the function burn, it does not transfer any tokens out. To actually transfer the tokens, we will need to call a function called collect. The function collect is used both to collect fees on swaps and to actually transfer out the tokens from removing liquidity. To remove liquidity, we first need to call the function burn to decrease the liquidity for a position. And to actually transfer the tokens out, we'll need to call the function collect. For the inputs, it's going to take in the recipient. This will be the address to send the tokens to, the tick lower and tick upper that defines a position, and the amount of tokens to transfer out. If these amounts are greater than the actual amount that is owed to this position, then the maximum amount that will be transferred out is the amount owed to this position. Inside the function, it's going to first get the position that is defined by message sender and the two ticks, tick lower and tick upper. And then it calculates the actual amount of tokens that can be transferred out. If this amount requested is less than the amount of tokens that are owed, then the amount that will be transferred out is the amount that is requested. In other words, the amount of tokens that will go out is the minimum between the tokens that are owed and the amount requested. If there is any amount of tokens that can be transferred out, then the position will be updated. Tokens owed will be decreased and the amount of tokens will be transferred out. You can see this over here for token 0 and for token 1. And that ends the code walkthrough for the function collect. The most common way to manage liquidity for a Uniswap V3 pool is to interact with a smart contract called Non-Fungible Position Manager. There are 4 functions that you can call on this contract. The functions are mint, increase liquidity, decrease liquidity, and collect. In this video, I'll show you an overview of how the contract's Non-Fungible Position Manager and the contract Uniswap V3 pool interacts when a user calls the function mint. Let's say that a user wants to create a new position in a Uniswap V3 pool. To do this using the contract Non-Fungible Position Manager, the user will call the function mint, specifying the price range that they want to add liquidity to and the amount of tokens that they want to add. Next, the Non-Fungible Position Manager will call the function mint on Uniswap V3 pool. The pool contract will calculate the amount of tokens that the user must send and then call a callback called Uniswap V3 mint callback. And inside the callback, tokens, token 0 and token 1 are transferred from the user over to the contract Uniswap V3 pool. Let's look at the code for the function mint inside the contract Non-Fungible Position Manager. This contract is inside the repo called V3 Periphery. The contract Non-Fungible Position Manager is a ERC721. So when we call the function mint, it will mint an NFT, and this NFT represents our position. The function mint takes in a single input, a struct called mint params. This mint params is specified inside the interface I Non-Fungible Position Manager. Here's the data that is passed as inputs. Token 0, token 1, and fee, which determine the pool, the price ranges to add liquidity, tick lower and tick upper, the 2 amount of tokens we wish to add, the minimum amount of tokens that must be added, the recipient of the NFT, and deadline. The last timestamp the function to call mint is valid. Okay, so these are the parameters that are passed to the function mint. Going back to the function, first it checks the deadline, and for the output, it's going to return token ID. This will be the ID of the NFT that was minted. Liquidity will be the actual amount of liquidity that was added, and amount 0 and amount 1. The amount of tokens that was transferred over from message sender to increase liquidity by this much amount. Okay, let's take a look at the function body. First, it calls a function called add liquidity. This function inherits from another contract, and this contract is under base, and the name of the contract is called liquidity management. Inside here, there's a function called add liquidity. First, it creates a struct called pool key. This pool key is not that important, but it might be useful to remember that this pool key stores 3 data: token 0, token 1, and fee. And remember that from these 3 parameters, we can identify the pool. From this pool key, it will calculate the address of the pool, and then get the current square root price x96 from the pool, and then calculates the liquidity. The amount of liquidity that will increase if we were to add these much amount of tokens into the price ranges, square root ratio AX96 and square root ratio BX96. These 2 square root ratio are calculated above by taking the tick lower and tick upper. Okay, once the liquidity is calculated, next it calls the function mint on the contract in Uniswap V3 pool. Now the pool contract will call back into a callback called Uniswap V3 mint callback, and it specifies the amount of tokens that are needed to increase the liquidity by this much amount. Okay, so going back to the callback, it will transfer the tokens from the payer over to message sender. Since the Uniswap V3 pool contract called this function Uniswap V3 mint callback, here message sender will be the Uniswap V3 pool contract. For token 0, it would transfer from the payer over to the pool contract for the amount 0 owed, which is specified over here. And the next line does something similar except for token 1. Transfer token 1 from the payer over to the pool contract for the amount 1 owed. Once the callback is done executing, the function add liquidity is also done executing, and we go back to the function mint. So we call the function add liquidity, and after adding liquidity, at this point we transferred over the tokens from message sender over to the pool contract. Next, it will call internal function called mint. This function will mint an NFT, and the owner of this NFT will be the recipient, which is set by the input parameters. Next, it will calculate the position key, which is specified by the address of this contract and the 2 ticks, tick lower and tick upper. This position key is used to get the position data that is stored in the contract Uniswap V3 pool. And from this, it gets the latest fee growth inside 0, last x 128, and 1x 128. These are data that is used to calculate the amount of fees that this position can collect. Next, it caches the pool key, and what it does is it stores this data over here as a state variable, and then assigns a pool ID to this data. This data stores the address of token 0, token 1, and fee. Next, it stores the data called positions for the token ID, setting the pool ID, the 2 ticks, the amount of liquidity that was added, and the latest fee growth inside 0 last x128 and 1x128. And that ends the execution for the function mint. Once a position is created by calling the function mint on the non-fungible position manager, let's say that this user decides to increase liquidity to this position. The function that he'll have to call is called increase liquidity on the contract non-fungible position manager. So to increase liquidity to an existing position, which is managed by this non-fungible position manager contract, the user will first call the function increase liquidity. The non-fungible position manager will call the function mint on Uniswap V3 pool. Uniswap V3 pool will calculate the amount of tokens that are needed and then call callback called Uniswap V3 mint callback. Inside this callback, token 0 and token 1 that are needed to increase liquidity is transferred over from the user to the Uniswap V3 pool contract. The function increase liquidity inside the contract non-fungible position manager is used to increase the liquidity for a position. This position must be a position that was created by calling the function mint on the non-fungible position manager. For the input is defined inside the interface I non-fungible position manager. And here's the inputs that must be passed. Token ID will be the ID of the NFT that was minted. The next 2 inputs are the amount of tokens that the user wished to add. And the 2 inputs after that are the minimum amount of tokens that must be added, and the deadline. If the timestamp when the function increase liquidity is executed is more than this deadline, then the function call will revert. Let's go back to the function increase liquidity inside the contract non-fungible position manager. When the function increase liquidity is executed, it will first check that deadline has not expired. And for the outputs, it's going to return the amount of liquidity that was added and the amount of tokens that was transferred into the pool contract. Inside the function, it first gets the position, which is identified by the token ID. This is the NFT token ID. Next, it gets the pool key. And remember that this pool key stores 3 data: address of token 0, token 1, and fee. And it calls the function add liquidity. Add liquidity will call the function mint on Uniswap V3 pool contract, and then it will transfer the tokens from message sender over to the pool contract. In return, it returns the amount of liquidity that was added and the amount of token 0 and token 1 that was transferred over from the caller to the pool contract. Next, it calculates the position key, which is computed by taking the address of this contract and the 2 ticks, and then it gets the position that is managed by this non-fungible position manager by calling the function pool.positions. And this is done to fetch the latest fee growth inside 0 last x128 and 1x128. Again, these 2 variables are used to calculate the amount of fees that was collected by this position. To calculate the fees, we take the latest fee growth inside 0 last x128 and then minus it from the previous one, which is stored inside position.fee growth inside 0 last x128. We take this difference, multiply by the previous liquidity, and then divide it by 2 to the 1 to 8. And this will calculate the amount of fee that was collected by this position. We'll discuss how the math for this works in a later video. Okay, moving on, it does the same for token 1. Calculate the amount of fees that was collected by this position. Next, it updates the fee growth inside 0 last x128 and fee growth inside 1 last x128 to the latest values, and then increment the liquidity. That completes the code walkthrough for the function increase liquidity. Once a user has a position which is created by the non-fungible position manager, let's say that this user decides to decrease liquidity. Then this user will call the function decrease liquidity. So first, the user will call the function decrease liquidity on non-fungible position manager. Next, the non-fungible position manager will call the function burn on Uniswap V3 pool. Now, if you remember from the code walkthrough for the function burn, inside Uniswap V3, when the function burn is called, it decreases the liquidity, but it doesn't actually transfer the tokens. And this is the same over here. When the user calls the function decrease liquidity, it calls the function burn on Uniswap V3 pool contract, but no token is transferred over to the user. To actually transfer the tokens, the user will have to call another function called collect. The function decrease liquidity will decrease the liquidity for a position but it doesn't actually transfer the tokens. For the input, it's going to take in a single struct called decreased liquidity params, which is defined inside the interface non-fungible position manager. Inside the struct, here are the parameters that we will need to pass. Token ID will be the ID of the NFT that was minted, which represents a position. Liquidity will be the amount of liquidity to decrease by. And amount 0 min and amount 1 min are minimum amount of tokens that will be deducted when we decrease the liquidity by this much amount. And deadline is the last timestamp that the call to this function is valid. Let's go back to the function decrease liquidity inside the contract non-fungible position manager. There are two modifiers for this function: check deadline, which will make sure that the deadline is not expired, and it also has a modifier called isAuthorized for token, which checks the authorization of message.sender for token ID. And then it's going to return two outputs, amount 0 and amount 1, which is the amount of tokens that were deducted for decreasing liquidity. First, it checks that liquidity from the input is greater than 0, and then gets the position identified by the token ID. Next, it checks that the liquidity of this position is greater than or equal to the liquidity that was passed from the input. And then it gets the pool key, gets the Uniswap V3 pool contract from the pool key, and then calls the function burn on Uniswap V3 pool. Calling the function burn on Uniswap V3 pool does not transfer any tokens. It just decreases the liquidity and then also tells us how much token we can deduct. Next, we get the latest fee growth inside 0 last x128 and 1 last x128, which is stored inside pool.positions for the position key. The position key is computed by the address of this contract and the two ticks, tick lower and tick upper. Next, it updates the position that is stored in this contract. It adds the amount of tokens that were deducted for decreasing liquidity, and then it also adds the amount of fee that was collected for this position. And it does the same for token 1. The fees for the position is calculated by taking the difference of the latest fee growth inside and the fee growth inside that was stored in the position. So after it calculates the amount of fee that can be claimed, it updates this fee growth inside 0 last x128 and 1 last x128 to the latest fee growth inside, which was fetched over here. And finally, it updates the liquidity for this position by decreasing this liquidity by the amount that was specified by the input. Okay, and that completes the code walkthrough for the function decrease liquidity. The function collect inside the contract non-fungible position manager can be called in two situations. The first situation is to just collect the swap fees for providing liquidity. The other situation is to remove liquidity. To remove liquidity, the user will first call the function decrease liquidity on the non-fungible position manager. And to actually transfer the tokens out, the user will next call the function collect. So in either case, to collect fee or to remove tokens after decreasing liquidity, the user will call the function collect on the non-fungible position manager. Next, the non-fungible position manager calls two functions on Uniswap V3 pool. First, it calls the function burn. When this function is called, it will calculate and update the amount of fees that can be collected by the contract non-fungible position manager. And then next, it will call the function collect on Uniswap V3 pool. This will transfer the tokens from Uniswap V3 pool contract over to the user. To collect swap fees or to remove tokens after decreasing liquidity, you'll need to call the function collect. It takes in a single input, a struct called collect params. This collect params is defined inside the interface non-fungible position manager. For the inputs, it's going to take in token ID. This will be the ID of the NFT, recipient. This will be the address that will be receiving the tokens, and amount 0 max and amount 1 max, the maximum amount of tokens to transfer. First, this function checks that the input amount 0 max is greater than 0 or amount 1 max is greater than 0. And then it sets the address for the recipient. If the recipient is not set, then it sets the recipient to this contract. Otherwise, it uses the recipient that is specified by the input. Next, it gets the position that is stored inside this contract, gets the pool key, and then gets the Uniswap V3 pool contract. Caches the variable tokens owed 0 and tokens owed 1, which is stored inside position.tokens owed 0 and tokens owed 1. If this position has any liquidity, then it will call the function burn on Uniswap V3 pool contract. And this is done to update the fee growth inside 0 last x128 and fee growth inside 1 last x128 that is stored inside the pool contract. So once it calls the function burn, these values will be the latest value. Using this, it calculates the amount of fee that was collected for this position and then adds it to the variable tokens owed 0 and tokens owed 1. Since the fees that can be claimed are now up to date, the code will update fee growth inside 0 last x128 and fee growth inside 1 last x128 to their latest values. Moving on, next it calculates the amount of tokens that can be transferred out. If the amount that was specified by the input is greater than the actual amount of tokens that are owed, then the amount of token to transfer is the amount of tokens that is owed. Otherwise, the amount that was specified by the input will be transferred over. In other words, the amount to be transferred is the minimum of the input, amount 0 max, and the amount of tokens that are owed. This is done for both token 0 and for token 1. Then to actually transfer the tokens, it will call the function collect on the contract Uniswap V3 pool. After the tokens are transferred, it will update the position that is stored in this contract. The tokens that are owed are stored inside the variable tokens owed 0 and tokens owed 1. When the function collect was called, amount 0 collect and amount 1 collect was transferred out. So the current amount of tokens that are owed are the difference tokens owed 0 minus amount 0 collected and tokens owed 1 minus amount 1 collected. The new value is stored inside the position.tokens owed 0 and tokens owed 1. And that ends the code walkthrough for the function collect. There are 4 exercises for managing liquidity with Uniswap V3. The contract for the exercises are located under Foundry, Test, Uniswap V3 Exercises, and the name of the contract is called Uniswap V3 liquidity.test.sol. Let's take a look at the setup. Scrolling down. In this exercise, you'll be managing liquidity with the WEF DAI pool with a 0.2% swap fee. So WEF, DAI, and the non-fungible position manager are all initialized. Next, there are some constants that may be helpful to complete the exercises. Minimum tick, maximum tick, and the pool fee for the DAI WEF pool with 0.3% swap fee, which is equal to 3000, and inside this pool, the tick spacing is equal to 60. Inside the function setup, this contract is given 3000 DAI and 3 WEF. And this contract approves the non-fungible position manager to spend all of WEF and DAI. Next, this contract has some helper functions that are used for the test. Mint to mint liquidity, and the function to get the position based on the token ID. The first exercise is to mint a new position by adding liquidity to the DAI WEF pool with 0.3% swap fee. You are free to choose the price range, and note that when you pick a price range, both the lower tick and the upper tick of the price range must be divisible by the tick spacing of the pool. Again, this contract is given 3000 DAI and 3 WEF. Put any amount of tokens to create a new position. Recall that when you mint a new position using the non-fungible position manager, the non-fungible position manager mints a NFT. Set this recipient of the NFT to this contract. Write your code here to mint a new position using the non-fungible position manager. So that's exercise 1. Let's go over the solution for the first exercise. The first thing that we'll need to do is call the function mint on the contract non-fungible position manager. So over here, I have the interface for non-fungible position manager, and here's the function mint that we need to call. So I'll copy this struct because this is a struct that we'll need to pass in to call the function mint. And then back inside our exercise, I'll paste the struct over here. So the contract that we need to call is called non-fungible position manager. This contract inside this exercise is initialized as manager. And then call the function mint. And then we'll need to pass in this struct non-fungible position manager dot mint params. And then we'll need to pass in these parameters. For token 0, we'll pass in DAI. And for token 1, we'll pass in WEF. The pool fee for this DAI WEF pool will be 0.3%. So inside here, we'll put 3000. Tick lower and tick upper. This is the price range that we're going to put liquidity into. And for this exercise, it doesn't matter what we put in here as long as tick lower and tick upper are multiple of tick spacing of this pool. So scrolling back up, the tick spacing for this pool will be 60. And for this exercise, I'll use max tick and min tick and then round it to a multiple of tick spacing. I'll say int 24 tick lower is equal to min tick divided by tick spacing and then multiply by tick spacing. When we divide min tick by tick spacing, then solidity division cuts off the remaining decimal parts. So we'll get a number that is a multiple of tick spacing. And then we multiply this number by the tick spacing again. We'll do the same for tick upper. Int 24 tick upper is equal to max tick divided by tick spacing times tick spacing, and then pass it as a parameter here. Tick lower and tick upper. Amount 0 desired. Amount 0 is DAI, and for this exercise we are given 3000 DAI. So for here, I'll just put 1000 DAI. 1000 times 1e18. And token 1 will be WEF. We are given 3 WEFs. So here I'll put 1 WEF, which is 1e18. Then amount 0 minimum. The minimum amount of token 0 that must be added as liquidity. For simplicity, I'll put 0. And then amount 1 min. Again, for simplicity, I'll put a 0. And the recipient of this NFT that represents this position, for this exercise, we'll have to set it to this contract. So let's say address this. And deadline will be block.timestamp. Okay, let's try executing exercise 1. Inside my terminal, I'll set the fork URL as an environment variable. And to execute the test, I'll type forge test -- fork URL match path test Uniswap V3 exercises Uniswap V3 liquidity.test.solve. And furthermore, inside this contract, we have several exercises. I only want to execute this test called test mint. So I'll pass in an extra parameter called -- match test, and then the name of the test mint. Okay, and our test passed. The second exercise is to increase liquidity for a position. The position is already minted by calling a helper function called mint, and it assigns a variable called token ID. Given this token ID, what you'll need to do is increase liquidity for this token ID. Again, initially this contract is given 3000 DAI and 3 UF. Some of these tokens were used to mint the position by calling the function mint. To get the amount of tokens that are left inside this contract, you can call balance of on ERC20. So using any amount of tokens that is less than or equal to the remaining amount of tokens inside this contract, I want you to increase the liquidity for this position. And to increase liquidity, you'll need to call the function increase liquidity on the non-fungible position manager. If you need to take a look at how to call this function, you can do this by going to Foundry, Source, Interfaces, Uniswap V3, and click on I non-fungible position manager, and then scroll down to find the function called increase liquidity. This function takes in a single struct parameter, and these are the parameters that you'll need to pass in. The next exercise is to increase liquidity to a position that already exists. And this position is represented as an NFT, which has the token ID given over here. To increase liquidity to an existing position, you'll need to call the function increase liquidity on the non-fungible position manager. So here I'll say manager dot increase liquidity, and then we'll need to pass in a struct. The struct will be declared inside the interface I non-fungible position manager. And here's the struct increase liquidity params. I'll copy this, and then I'll paste it inside here. The struct will be I non-fungible position manager that increase liquidity. Then for the token ID, I'll pass in the token ID that is given. Amount 0 desired. Here we can say, for example, DAI.balance of address this, saying that whatever amount of DAI that is inside this contract, try to put it in as liquidity. But for simplicity, I'll just put in a number. Let's say 500 DAI. 500 times 1e18. And amount 1 desired, I'll just try to put in, let's say 1e18. Amount 0 minimum. Again, we'll keep it simple, put a 0. And for amount 1 minimum, again, put a 0. Deadline, block.timestamp. Okay, that completes exercise 2. Let's try executing this test. Note that the name of this test is called test increase liquidity. Inside the terminal, I'll execute the same test command as in the previous exercise, and then change the last parameter for match test. We're going to execute the test called test increase liquidity. And then we also display the console log, so say -bbb. And our test passed. For increasing liquidity, we put in approximately 499 DAI, and for the same amount, we put in 0.12 ETH. The next exercise is to decrease liquidity for a position. The position is minted by calling a helper function called mint, and it assigns a token ID. Given this token ID, the exercise here is to decrease liquidity. The amount of liquidity to decrease is up to you. The amount of liquidity in this current position is fetched by calling the function getPosition, and it is stored in the struct position. This will be the maximum amount of liquidity that you'll be able to decrease. Any amount equal to or less than that is okay for this exercise. To decrease liquidity, you'll need to call the function decrease liquidity on non-fungible position manager. And if you need a refresher on how to call this function, you can navigate to the non-fungible position manager interface and then take a look at the function decrease liquidity. These are the params that you'll need to pass. The third exercise is to decrease liquidity. As a setup, we are given a position where the token ID is initialized as a variable called token ID. One requirement for this exercise is that the amount of liquidity to decrease cannot exceed the position's liquidity, and this position's liquidity is stored inside a struct called position. To decrease liquidity, we'll need to call the function decrease liquidity on non-fungible position manager. Manager.decrease liquidity, and then we'll need to pass in a parameter. The parameter is defined inside the non-fungible position manager interface, and here's the struct that we'll need to fill out. I'll copy this and then paste it here. This will be non-fungible position manager dot decrease liquidity. For token ID, we'll pass in token ID, and for liquidity is stored inside a struct called position, and this position struct is defined up at the top over here. The way this data is fetched is by calling the function getPositions, and it gets all the information by calling positions on non-fungible position manager. Once it fetches all of these data, it just stores it into a struct called position, and one of the data that is stored is the liquidity of the position. So for this exercise, let's try decreasing all of the liquidity. P0.liquidity. Amount 0 min. Minimum amount of token 0 that must be decreased. Let's set it to 0 for simplicity. And for minimum amount of token 1 that must be decreased, again, let's set it to 0. And deadline will be block.timestamp. Okay, that completes exercise 3. Let's try executing this. Note that the name of this test is called test decrease liquidity. Inside my terminal, I'll execute the same command again, and the test to execute will be test decrease liquidity. Okay, and our test passed. So when we decreased all of the liquidity, we withdrew 999.999 and so on amount of DAI, and approximately 0.258 ETH. The last exercise is to remove all liquidity from a position. Recall that to actually transfer the tokens out, you'll first need to call the function decrease liquidity and then call the function collect. Both of these functions are inside a non-fungible position manager, and if you need to look at the parameters, you can look at them here. Here's the parameter for the function collect. In this exercise, a position is minted with the token ID assigned to a variable called token ID. The liquidity for this position is stored inside a struct called position. To remove liquidity and transfer the tokens out, you'll need to call the function decrease liquidity on the non-fungible position manager, and then call the function collect on the position manager again. The last exercise for liquidity is to remove all liquidity. To do this, we'll need to decrease the liquidity and then call the function collect to actually transfer the tokens. We wrote the code to decrease liquidity in the last exercise, so let's go copy that and then paste it into here. Inside the test decrease liquidity, I'll copy this part of the code, which calls decrease liquidity on non-fungible position manager. And then I'll paste it here. We won't need the output. So just call decrease liquidity, and the amount of liquidity to decrease will be all of the liquidity for this position identified by the token ID. Next, we'll need to call the function collect to actually transfer the tokens. So over here, call manager.collect. And let's see what structs we need to pass in here to call this function. Again, inside the interface for non-fungible position manager, I'll scroll down and then copy the struct called collect params. Back inside our exercise, I'll paste this struct and then prefix this struct with non-fungible position manager. Token ID will be token ID. Recipient will be this contract, so this will be address this. For amount 0 max, we will pass in the maximum of uint128. So I'll type uint128.max. And the same for amount 1 max, type uint128.max. This will tell the non-fungible position manager to transfer all of the tokens that are owed to this position. And this includes the amount of tokens that are collected from the swap fees and the amount of tokens that are owed for providing liquidity. And that completes exercise 4. Let's try executing this exercise. Note that this exercise is called test collect. Inside my terminal, I'll execute the same command again. And for the last parameter, match test, we only want to execute the function test collect. So we'll pass in test collect and then execute the command. Okay, and our test passed. When liquidity is added in Uniswap V3, the two ticks, the lower tick and the upper tick that define this liquidity position is stored in a mapping called tick bitmap. During a swap, the next tick where liquidity exists is found by calling a function called next initialize tick within one word. In this video and in the next video, I'll explain how this function works to find the next tick. So again, tick bitmap is a mapping that stores the ticks that define a liquidity position. It's a mapping from int16 to uint256. To store a tick into this tick bitmap, the tick is first broken down into two parts. The first 16 bits starting from the left and going right is stored as int16, and the next 8 bits is stored as uint8. For example, let's say that the tick is minus 200,697. Here's the binary representation, and since here we're dealing with int24, this sequence of zeros and ones is 24 bits. In other words, there are 24 ones and zeros. The first 16 bits starting from the left and going right is converted into int16. Inside the code, this is called word position. In this example, when we evaluate this 16 bits as int16, this turns out to be minus 784. The last 8 bit is converted into uint8. And inside the code of Uniswap V3, this is called bit position. In this example, when we evaluate this 8 bits as uint8, this turns out to be 7. Let's look at an example of how this tick is stored into the tick bitmap. We first break this tick into two parts. The first 16-bit is evaluated as int16, and the last 8-bit is evaluated as uint8. In this example, the first 16 bits turns out to be minus 784. We use this number as a key to the tick bitmap. And let's say that the uint256 value that we get back looks something like this. Instead of thinking about this uint256 as a single number, it's helpful to think about this as a sequence of zeros and ones having the length 256. And for this example, let's say at the 7th index, we have a 0 here. Also notice that the bit position, the last 8 bits, is also equal to 7. What we're going to do next is change this 0 at the 7th index to a 1. To do this, we create a mask, 256 bits of zeros, except there's a 1 at the 7th index. Do an exclusive OR with the current value of the tick bitmap at the key minus 784. And this will turn the 0 at the 7th index to a 1, leaving everything else unchanged. This is how a tick is stored into a tick bitmap. And if we wanted to remove this tick from the tick bitmap, let's say that there's a 1 over here. Now, when we do an exclusive OR with a 1 and a 1, here we will get a 0. This is how a tick will be removed from a tick bitmap. To get a tick from a tick bitmap, we will get the 16 bits that represents the key for the tick bitmap and then append 8 bits to this 16 bits. For example, let's say that we have a tick bitmap and we're accessing the key minus 784. This will be the first 16 bits of the tick. The tick bitmap will give us a uint256 value. And again, instead of thinking this uint256 as a number, we think about it as a sequence of 256 bits. For this example, let's say that we wanted to convert this one at the 7th index into a tick. We rewrite this 7 as 8 bits, and then append this 8 bits to the 16 bits that came before. 16 bits from the key of the tick bitmap, and 8 bits from uint256. And this is how a tick is recovered from a tick bitmap. Now that we understand how a tick is stored inside the mapping called tick bitmap, next let's take a look at the function called next initialize tick within one word that will find the next tick during a swap. We'll start with a review of how a tick is broken down into two parts. Let's say that we have an int24 tick equal to minus 200,697. Here's the same number in binary. The first 16-bit is called a word position inside the code of Uniswap V3, and this 16 bits is converted into int16. In this example, when we evaluate this 16 bits as int16, this turns out to be minus 784. The remaining 8 bits is called bit position, and it is evaluated as uint8. In this example, this turns out to be equal to 7. To find the next tick that's 10 or equal to the current tick, we'll need to search right on the tick bitmap. The key for the tick bitmap is int16. For this example, let's say that we access the key minus 784. Again, this key is referred to as the word position inside the code of Uniswap V3. From this key, we get a value of uint256. For this example, I'll be using index 7, and we'll say that it is somewhere around here. And we also say that at index 7, the value that is stored is 0. We're looking for the next tick to be less than or equal to the current tick. Let's say that the current tick is at index 7. If we search for one to the left of index 7, then we're searching for a tick that is greater than or equal to the current tick. So what we need to do here is search for a 1 to the right of index 7. To look for a 1 that is to the right of index 7, we first create a mask. This mask will have a 1 at index 7, and everything to the right of it is also equal to 1. From this uint256 value that is stored inside the tick bitmap, we want to get all 1s to the right of index 7. And to do this, we'll apply this mask. We'll use a bitwise AND with this value. This will give us a uint256 value, where to the left of index 7, all of the numbers are equal to 0. This is because when we do an AND with 0 and 0, it would be equal to 0. When we do a bitwise AND with 0 and 1, it is also equal to 0. At index 7 and to the right of index 7, everything is a 1. So when we do a bitwise AND with 1 and 0, we get a 0. If we do a bitwise AND with 1 and 1, we get a 1. In other words, this operation of creating a mask and then doing a bitwise AND will give us all 1s to the right of index 7. From this value, what we want to find is the leftmost 1. And to do this, what we can do is find the most significant bit of this mask value. In this example, let's say that everything is a 0 over here and our first one is over here. When we find the most significant bit from this mask value, the index in this example will be equal to 1. This is the index where the first one occurs, starting from the left and then searching right. Okay, so now that we know the next bit position, the next step is to calculate the next tick. To find the next tick, we start off with the current tick, and to this, we minus the bit position. This will clear out the last 8 bits, turn them into all zeros. And then next, we add the next bit position. So as an example, let's say that this is our current tick. From this, we minus the bit position. So all of these 1 will turn into zeros. And then we add the next bit position. So remember that the next bit position is the index of the most significant bit of the masked value. In this example, it is equal to 1. In binary, this is equal to 0, 0, 0, 0, 0, 0, 0, and then 1. And this binary turns out to be, we start out with the current tick equal to minus 200,697. In this example, the bit position is equal to 7, so we minus this 7. And then the next bit position is equal to 1, so we add plus 1. And we get that the next tick is equal to minus 200,703. The way to find the next tick that is greater than the current tick is similar to the last example. Instead of searching right on the tick bitmap, in this case, we'll have to search left on the tick bitmap. Again, we'll start with the tick bitmap keys, which is int16, and we'll say that the key that we're accessing is minus 784. This will have a uint256 value. And again, for this example, let's say at the 7th index, we have a 0. From this uint256 value, we need to look for a 1 either to the left of index 7 or to the right of index 7. But which direction should we search for a 1? So let's think about this. If we were to search for a 1 to the right of index 7, then we are looking for a tick that is less than or equal to the current tick. So to find the next tick that is greater than the current tick, we'll need to look for a 1 to the left of index 7. And to do this, we'll first create a mask. This mask will have a 1 at index 7, and to the left of index 7, everything will be 1. To the right of index 7, everything will be 0. We apply a bitwise AND with this mask and the value that is stored in the tick bitmap. The resulting value will have all zeros to the right of index 7. And this is because to the right of index 7, everything is 0. When we do a bitwise AND with zeros, we get a 0 back. At index 7 and to the left of index 7, everything is a 1. So when we do a bitwise AND with a 1, with either a 0 or a 1, we get the value back. If it is a 1 and a 1, then we get a 1. If it is a 1 and 0, we get a 0. What we achieved here is that we got all 1s at and to the left of index 7. Once we found all 1s at index 7 and to the left of index 7, this gives us the ticks that are greater than or equal to the current tick. From all of these ticks that are greater than or equal to the current tick, we need to find the smallest one that is greater than the current tick. And the way we'll do this is by finding the rightmost one. Everything to the right of index 7 is all equal to 0. So if there's any 1s in this value, it will be at index 7 or to the left of index 7. So we'll search for the rightmost one to the left of index 7. In other words, what we're doing here is finding the index of the least significant bit. In this example, let's say that everything over here is a 0 and the least significant bit is over here. The first 0 is index 255. The next one is 254. So this one will be 253. So in this example, the least significant bit will be equal to index 253. Now that we found the next bit position, let's now calculate the next tick. To find the next tick, we start out with the current tick, minus the bit position of the current tick, and then add the next bit position. To make sure that the next tick is greater than the current tick, we add a 1. Let's see what's going on here using binary. Here we have our example tick. From this, we minus the current bit position, and this will turn all of these 1s into 0s. Next, we add the next bit position. The next bit position is equal to 253. When we rewrite this as 8 bits, this turns out to be 11111101. And then lastly, we add this plus 1. We started out with the current tick equal to minus 200,697, minus the current bit position, which is equal to 7, add the next bit position, which is equal to 253, and then plus 1 to make sure that the next tick is greater than the current tick. And this is equal to minus 200,450. Starting from this video, I'll explain how fee for liquidity providers are calculated in Uniswap V3. To begin with, let's start with a simple example. Let's say that the liquidity in a Uniswap V3 pool looks something like this. And from this, let's also say that Alice has S liquidity between these price ranges. The active liquidity, we'll label it as L0, and Bob swaps dy amount of token Y for dx, amount of token X. This will move the current tick over to the right. And let's say that the active liquidity changed from L0 to L1. Fee is collected on token N. In this case, this is token Y. We'll label F0 as the amount of fee that was collected on liquidity L0. And F1 is the fee that was collected on liquidity L1. From this simple example, let's calculate the fees that Alice can collect for providing liquidity. We'll label the total fees earned by Alice as F. And this is equal to, well, fee F0 was collected on liquidity L0. Alice will earn a percentage of this F0. And how much percent can she collect? To answer this question, imagine a simple case. Let's say that Alice provided all of L0. Then the percentage of fee that she can earn from this liquidity will be 100%, or F0. However, in this case, she provided S amount of liquidity out of L0. So the percentage will be, the total amount of liquidity will be L0. And the amount that she provided is S. And S divided by L0 will give the percentage fee of F0 that Alice can collect. Now, this is only one fee that she collected for liquidity L0. But there's also another fee, F1. So we'll need to add this. F1 is the total amount of fee that was collected in liquidity L1. The total amount of liquidity in L1 is, of course, L1. From this, the amount of liquidity that she provided is S. And S divided by L1 will be a percentage. The percentage of F1 that Alice can collect. So in this example, Alice provided S amount of liquidity in a liquidity pool that looks like this. And in a single swap, the active liquidity is swapped from L0 to L1, collecting fees F0 and F1. In this case, the amount of fee that Alice collected in this swap is given by this equation. Let's now consider a case where Alice has S amount of liquidity over some time, and during that time there are multiple swaps, and also the liquidity might change over time. However, the amount of liquidity that Alice provided, S, will remain constant. We assume that Alice's liquidity S is a constant. She provides some liquidity S over some time, and this S remains a constant. She does not further add or remove liquidity. We will label F of I to be the fee on token Y collected at liquidity Li. And we'll say that this I ranges from 0 to some number n. Again, we'll say that F is the total fees of token Y earned by Alice. Now the equation is exactly the same for token X. So for these examples that I'll show you, I'll use token Y. Let's say that the first fee that was collected is F0. Then from the previous equation, then we know that the amount of fee that Alice can collect is the percentage S divided by the liquidity L0. And the same goes for the next fee that was collected. Let's call this F1. Alice can collect the percentage S divided by L1. And we repeat this pattern. until some number n. We can write this equation in a concise way by saying sum from I equals 0 to n s times f of I divided by L of I. In this equation, s is a constant, so we can pull this out. This is an important equation to remember since Uniswap V3 uses a state variable called fee growth, which is based off of this equation. Let's see an example of this equation. Let's say that at time t1 the liquidity pool looks like this. And again, Alice has provided S amount of liquidity. Let's say that there was a swap of token Y for token X. The active liquidity changed from L0 over to the right L1. And the swap collected F0 amount of token Y from liquidity L0 and F1 amount of token Y from liquidity L1. Let's say that some time has passed since t equals 0. Let's call this t equals 1. And notice that the shape of the liquidity has also changed. However, the amount of liquidity that Alice has provided remains the same. Let's say that there was a swap from token X to token Y. The active liquidity started at L2 and it swung over to L5. Remember that in Uniswap V3, fees are collected on token N. So when there was a swap for token X to token Y, there is no fee collected on token Y. So F2, F3, F4, F5 are all equal to 0. Once again, let's say that some time has passed. Let's call this t equals 2. And again, the shape of liquidity has changed. Let's say that there was a swap from token Y to token X. The active liquidity changed from L6 to L8. Along the way, it collected fee F6, F7, and F8. With this in mind, let's now calculate the amount of fee that Alice collected. Again, we'll label this as F. The percentage of fee that she collected from F0 will be S divided by L0. The percentage of fee that she collected on F1 is S divided by L1. We can also say that the percentage of fee that Alice collected for F2 is S divided by L2. But here we know that F2, F3, F4, and F5 are all equal to 0. We continue this until time t equals 2. The last fee that was collected was F8. The percentage of F8 that Alice can receive is S divided by liquidity L8. Previously, we looked at how to calculate fee for a liquidity position, and I also mentioned that this part of the equation is called fee growth, and it is a state variable inside the code of Uniswap V3 that tracks fee for each position. In this video, I'll dig a little bit deeper and explain more about fee growth. We'll begin by explicitly defining what fee growth is. So imagine the case that swap collects fee of f of I of token Y in liquidity L by for I ranging from 0 to some number n. We'll define fee growth f of g to be equal to add up all the liquidity that was collected at a liquidity and then divide by the liquidity. For example, let's say that a fee of f0 was collected and at that time the liquidity was L0. Then we will do f0 divided by L0. We add up all of this from I equal to 0 to I equals to n. We can also write this in a concise way. Starting from I equals to 0, go all the way up to n. And for each I, add the terms f of I divided by L of I. Recall from the previous video that when we multiply this number by the liquidity of a position, then we can calculate the fee that was collected by that liquidity position. Okay, so this is fee growth. Next, let me give you an example of how we can visualize fee growth. I use token Y for this example. The way I think about fee growth is that on the horizontal axis, I think about the ticks, and I map the fee growth on the vertical axis. Let's say that there was a swap of token Y to token X, and it collected fee on token Y. And this is because token Y is token N, and in Uniswap V3, fee is collected on token N. So when there's a swap of token Y to token X, two things will happen on this graph. Fee growth will increase, and the current tick will move right. The current tick will move right because there's a swap, more token Y is coming in and more token X is going out. And the fee growth will increase because we're collecting fee on token Y. We can visualize this as a diagonal line that increases as the tick moves from left to right. The tick moves from left to right because there's a swap, and the fee growth increases because here we're collecting fee on token Y. We do this simultaneously and we get a diagonal line. Okay, what happens when there's a swap from token X to token Y? Here we're just mapping out the fee growth of token Y. When there's a swap from token X to token Y, again fee is collected on token N. In this case, token N is token X, so there's no fee collected on token Y since it is token out. How would we map this on the graph on the left? Well, since there's no fee that is collected, the fee growth will remain the same. However, since there's a swap from token X to token Y, the current tick will move left. On the graph, it will look like a straight line that moves from right to left. It moves from right to left because there was a swap that moved the tick from right to left. And this line is a flat line since there is no fee growth. This pattern repeats every time there's a swap. The tip of this zigzag will represent the current fee growth and the current tick. And this is how I think about fee growth. Now, for this example, I used fee growth on token Y. For token X, it is similar but a little bit different. The difference is when there's a swap of token X to token Y, then the fee growth on token X will increase. On the graph on the left, it will look something like this. The tick will move from right to left, and since the fee growth increases on token X, we'll have a diagonal line that increases as it moves towards left. And similar to what we said about fee growth on token Y, when there's a swap from token X to token Y, no fee is collected on token Y. In the case for fee growth on token X, something similar will happen. If there's a swap from token Y to token X, since token Y is the token that is coming in, fee is collected on token Y, and no fee is collected on token X, so there will be no fee growth. However, the tick will move from left to right. What it will look like on the graph is this fat orange line. As the tick moves from left to right, there's no increase on the fee growth of token X, so it will be a flat line. In the previous video, I provided you with a simple example of how multiplying liquidity by the fee growth will calculate the amount of fee that this liquidity position can collect. However, things are not so simple when we need to also consider that the fee growth will go out of the price ranges. For example, here, let's say that there's a liquidity position between the ticks -3 and +3. This position is highlighted in white lines. And as you can see, sometimes the fee growth will go out of bounds, and other times fee growth are within this liquidity position. So in this case, how do we calculate the fee that is collected by this liquidity position? The basic idea to calculate the fee growth in this case is to calculate the fee growth that is within this liquidity position and then multiply by the liquidity. So in this video, I'll give you a basic idea of how to calculate the fee growth inside the liquidity position. Again, let's start with a simple example of how to calculate the fee growth inside. Imagine a case where there are two ticks, I lower and I upper, which represents a liquidity position. And imagine the simplest case for how to calculate the fee growth between these two ticks. Imagine that the fee growth will always be inside the two ticks, I lower and I upper. And let's ask the question, what is the fee growth inside tick I lower and tick I upper? In this case, the answer is simple. All of the fee growth is inside these two ticks. So the fee growth inside in this case is equal to the fee growth. The height of this fee growth, or you can think about it as the length of this orange line, is equal to the fee growth inside. For the next example, imagine the case where we have a liquidity position again from tick I lower and tick I upper, and the fee growth crosses I lower and then eventually crosses I upper. In this case, what is the fee growth inside these two ticks? This is highlighted as a green rectangle between these two ticks, and we want to calculate the fee growth inside. The fee growth inside in this case is the height of this green rectangle, and we can calculate this by starting off from fee growth and then minusing whatever height of the fee growth that is above tick I upper and the height of fee growth that is below tick I lower. Let's label the height of the fee growth that is below tick I lower as FB, short for fee growth below. And then in the same manner, let's name the fee growth above tick I upper as FA, short for fee growth above. Again, to calculate the fee growth inside, what we're interested is the length of this orange line, or the height of this green rectangle. And to calculate this, we start off with the current fee growth FG. And then from this, we minus this height of this red rectangle, which we labeled it as FB. And finally, we minus the height of this red rectangle called FA. And this will give us the height of this green rectangle, which is equal to the length of this orange line. This is the equation for fee growth inside. Okay, but what if we had a more complex case? For example, here you can see that the fee growth goes below tick I lower, and then later it enters this liquidity position again, and then the same over here. It exits the liquidity position, and then later comes back inside the liquidity position. In this case, how do we calculate the fee growth inside? To calculate the fee growth inside, you will need to sum up all of the height of these green rectangles. This is the part of the fee growth that is inside the two ticks. To calculate the fee growth inside, we take the current fee growth, and from here, we minus the fee growth below and fee growth above. And this will give us the sum of the heights of the green rectangles, which is also equal to the length of this orange line. And again, fee growth inside is equal to the current fee growth minus the height of this fee growth below, and then from here minus the length of this fee growth above. And now we can generalize this idea to come up with an equation for fee growth inside. Let's define a function called f of b of I to be equal to the fee growth below tick I. And we also define the function f of a that takes in a tick as input, and this is defined to be the fee growth above tick I. We also define a function f of r which will take in two inputs, tick lower and tick upper. In the white paper of Uniswap V3, this is also called f of r. R stands for range. What this function is trying to say is the fee growth within the range of tick I lower and tick I upper. And we'll define this function to be the fee growth inside tick I lower and tick I upper. And now we already know how to calculate this function. From the example above, this is equal to the current fee growth minus the fee growth below tick I lower minus the fee growth above tick I upper. So this is a general equation of how to calculate the fee growth inside two ticks, tick I lower and tick I upper. Once we can come up with an explicit formula for fee growth below tick I and fee growth above tick I, then we'll be able to calculate the fee growth inside the two ticks, I lower and I upper. And once we can do that, we multiply it by the liquidity to calculate the amount of fees that can be collected by a liquidity position, even if the fee growth sometimes go out of bounds of tick I lower and I upper. This video is an animated example of fee growth inside. So let's say that we have some liquidity position between two ticks, tick equal to -5 and tick equal to 5. The vertical purple line will represent the current tick. Now let's run the animation to see what fee growth inside will look like for this liquidity position. Okay, so let's say that there was a swap and it swung the current tick over to the left, and at some point the current tick crossed below the lower tick. The fee growth inside is highlighted in green, and the fee growth below is highlighted in red. When this current tick crossed over the lower tick of the liquidity position, the fee growth inside stopped increasing, and the fee growth below started increasing. Next, let's say that there was another swap that brought the current tick from being below the lower tick and into this liquidity position, into the price ranges of the two ticks. Since this example shows the fee growth of token X, when token Y is coming in, the fee growth does not increase. However, since this is a swap from token Y to token X, the tick will move from left to right. Again, let's say that there was another swap from token X to token Y, and in this case we can see that the fee growth increased. After the swap, the current tick still remains inside this liquidity position. Hence, the fee growth inside also increases, and we can see this, that the highlighted green rectangle increased over here. Okay, and after that, let's say that there was a swap that brought the current tick above the upper tick. And now the current tick is above the upper tick. So as long as the current tick is above the upper tick, the fee growth inside will remain the same and fee growth above will increase. And you'll see that this red rectangle, which represents fee growth above, increase. Now the current tick is inside the liquidity position again, and so you see that the fee growth increase again. On the next swap, the current tick remained inside this liquidity position for part of the swap. You can see here that the fee growth inside increased until here, until the current tick went below the lower tick, and then from there fee growth below started to increase. Next, there was another swap from token Y to token X. No fee is collected on token X, so this fee growth remains flat. At this point, the current tick is outside of the liquidity position, and on the next swap, the current tick moved inside the liquidity position. So during the swap, part of the fee growth was above the upper tick, and then the remaining fee growth was inside the liquidity position. I'll play this animation again. I hope this gave you a better intuition for how to visualize fee growth inside. Inside the code of Uniswap V3, there's a state variable called fee growth outside. And this state variable is used to calculate both fee growth above and fee growth below. I'll explain how this works in the next two videos. In this video, I'll explain how fee growth outside is initialized and how it is updated. Let's first start by defining some variables. We'll say f of g is the current fee growth. And we also define the fee growth outside at tick I to be FO of I to be equal to the fee growth outside at tick I. Next, let's take a look at the algorithm, how this fee growth outside is initialized and how it is updated. The state variable fee growth outside is initialized as following. FO of I will be equal to the current fee growth if the tick is less than or equal to the current tick. Otherwise, if this current tick is less than the tick that is associated with the fee growth outside, then it is initialized to 0. It's not so obvious why fee growth outside is initialized in this manner. But over the next 2 videos, when we look at the example of how fee growth outside is used to calculate fee growth above and fee growth below, this will become more obvious. And the way the fee growth outside is updated is the following. When the current fee growth, FOG, crosses tick I, then the fee growth outside at tick I is updated by taking the current fee growth and then taking the minus of the current fee growth outside and then adding it to the current fee growth. Okay, so this is how fee growth outside is initialized and how it is updated. In the next 2 videos, we'll see how this algorithm correctly calculates the fee growth above and fee growth below. Now that we know what fee growth inside is, how it is initialized, and how it is updated, let's now examine how this is used to calculate fee growth below. We will start by defining some variables. Again, FOG will be the fee growth of token Y at current time. We also define something similar. FOG of K will be the fee growth of token Y at time TK. Where this time variable TK has the following property. If we have TK and TK plus 1, then TK plus 1 will be greater than TK, and so on. So what we will have is TK is less than TK plus 1, TK plus 1 is less than TK plus 2, and so on. And finally, we'll define FOB to be equal to the fee growth of token Y below tick I. Hereby created a giant table, and each row will represent a time interval. For example, the first row will represent the time interval from T0 to less than T1. The next row will represent the time interval from T1 to less than T2, and the next one will represent the time interval from T2 and less than T3, and so on. For the first column, we'll fill out what FOB should be equal to at each of these time intervals. And then on the next column, we'll fill out what fee growth inside should be according to this algorithm. And lastly, what we're going to do is we'll rewrite FOB fee growth below in terms of fee growth outside. Okay, so let's begin. For this example, let's say that over time, the fee growth moves something like this. And here we have tick I, and in highlighted in red will be the fee growth below. When we sum up all of the heights of these red rectangles, we'll get fee growth below. So let's begin by filling out what fee growth below should be for each time interval. Let's start with the first one. For time between T0 and less than T1. Let's say that at time T0, fee growth was over here. This is labeled as FOG of 0. And at time T1, it went below the tick. In between these two times, between time T0 and T1, what should be the fee growth below? Well, if you look at the diagram, we can see that the fee growth below should be the height of this red rectangle at the bottom. And the height of this red rectangle is equal to the height of this fee growth at FOG 0. So fee growth below at this time interval will be FOG 0. How about for time between T1 and T2? Well, at time T1, the tick crossed over tick I, and then at time T2, the tick went above this tick I. In between time T1 and T2, fee growth was over here. So what should be the fee growth below? In this case, the fee growth below should be the previous fee growth below, which will be FOG 0, plus the height of this red rectangle. Again, so this will be FOG 0. FOG 0 is the height of this red rectangle at the bottom. And then to this, we add the height of this red rectangle over here. Between time T1 and T2, the current fee growth will be somewhere over here. So the height will be the current fee growth minus the fee growth when it went below this tick. This will be at FOG1. So the height of this red rectangle will be FG minus FOG1. Between time T2 and T3, the fee growth will be over here. So what is fee growth below? Well, in this case, the fee growth below will be the height of this red rectangle plus the height of this red rectangle at the bottom. The height of the red rectangle at the bottom is FOG 0. The height of this red rectangle will be FOG2 minus FOG1. How about at time between T3 and T4? Again, we're going to follow the same pattern that we saw over here. To the previous fee growth below, we're going to add some new height of this red rectangle. The previous heights that represents fee growth below will be f of g2 minus f of g1 plus f of g0. I simply copied and pasted the fee growth below from the previous time interval. And to this, we'll need to add some new height. Between time t3 and t4, the current fee growth will be somewhere over here. And at time t3, the fee growth went below this tick I. So if we take the difference of current fee growth minus f of g3, then we get the height of this red rectangle. So this will be f of g minus f of g3. Okay, and how about for time interval between t4 and t5? At time t4, the current tick crossed over this tick, so the fee growth is no longer below tick I. As long as the fee growth is above this tick I, fee growth below will not increase. At this point, the time between t4 and t5, what is fee growth below? Again, to calculate this fee growth below, what we need to do is add the height of this red rectangle over here between time t4 and t3, and then to this, we add the previous fee growth below. Here is the previous fee growth below. This is the height of this red rectangle and the height of this red rectangle. And to this, we need to add the height of this red rectangle. And the height of this red rectangle will be f of g4 minus f of g3. Okay, how about between time t5 and t6? In this time interval, fee growth will be over here on the left side of tick I. So what we need to do here is add to the previous fee growth below, we need to add the height of this red rectangle. The previous fee growth below, we can just copy it from here and then paste it here. This will represent the height of this red rectangle plus the height of this red rectangle and the height of this red rectangle. To this, we'll need to add the height of this red rectangle. And this is expressed by the current fee growth minus f of g5. And finally, how about for time interval between t6 and t7? At time t6, the current tick crossed above tick I. So to calculate the fee growth below, we need to add the height of this red rectangle and height of the other fee growth below. Here's the previous fee growth below. And to this, we add the height of this red rectangle, which will be f of g6 minus f of g5. Next, using the same example, let's see how fee outside tick I is updated. Let's begin by considering the time for t0 to t1. So if you go back over here, between time t0 and t1, fee growth will be above tick I. So how do we initialize fee outside FO of I? Well, scrolling up, we see here that FO of I is initialized as f of g if current tick IFC is greater than or equal to tick I. So this applies to our case. Back over here, we initialize FO of I to be FG0. Between the time interval t0 and t1, fee growth is above tick I. The current tick is also above tick I. So we initialize FO of I to be FG0. How about for time between t1 and t2? Well, at time t1, notice that fee growth crossed over this tick. And how do we update FO of I when the current tick crosses over this tick? Let's go back to this algorithm. When f of g crosses tick I, we update FO of I to be equal to the fee growth at the time that it crossed over tick I. And then to this, we do minus FO of I. Okay, so going back here. At time t1, the fee growth was equal to FG of 1. This is the time when the fee growth crossed below tick I. And to this, we need to do minus FO of I. The previous FO of I is equal to f of g0. So we get that the new FO of I is equal to f of g1 minus f of g0. Okay, how about for time between t2 and t3? Going back over here, again, notice that at time t2, the fee growth crossed over tick I. So again, we'll need to apply this algorithm on how to update FO of I. The current fee growth at time t2 when it crossed over the tick is f of g2. To this, we need to minus the previous FO of I. The previous FO of I is f of g1 minus f of g0. We flip all the signs, so a plus will become minus and a minus will become plus. And we get minus fg1 plus fg0. At time t3, the current tick again crossed over tick I. So we'll need to apply the algorithm again. The current fee growth at time t3 when it crossed over the tick I is fg3. To this, we need to add the previous terms where all of these terms the signs are flipped. Plus becomes a minus and minus becomes a plus. So the first term will be minus FG2. The next term will be plus FG1 and the last term will be minus FG0. At time t4, again the current fee growth crossed over tick I. So we apply the algorithm again. The current fee growth at time t4 is f of g4. To this we add the previous FO by and flipping all of the signs. And we get minus FG3 plus FG2 minus FG1 plus FG0. We repeat this pattern for the last two terms. At time t5, the current fee growth is FG5. And then to this we add the previous FO by flipping the signs and we get this. And at time t6, the current fee growth is FG6. And then to this, we add the previous FO by flipping the signs. Okay, now that we filled out FO by, next, let's see how this FO by relates to fee growth below. What you can immediately notice is that F of B is equal to FG0. How about FO by? It's also equal to FG0. So, in this case, F of B, when we rewrite it in terms of FO by, is equal to FO by. And the same goes for all of the odd rows. In the third row, we see that F of B is equal to FG2 minus FG1 plus FG0. And this is also equal to FO by on the third row. The same goes for the fifth row and the seventh row. Okay, how about the even rows? How can we rewrite FB in terms of FO by? Let's compare the second row. F of B is equal to FG minus FG1 plus FG0. How about FO by? FO by is equal to FG1 minus FG0. For FB, we have three terms. And for FO by, we have two terms. For F of B, we have a F of G, and then we have minus FG1, and then we have a plus FG0. For FO by, we don't have a FG, but we do have FG of 1. We also have a FG of 1 over here. And we also have a FG0, which we have over here. Also notice that these two terms have the opposite signs. Here we have a minus for FG1, here we have a plus. So to rewrite F of B in terms of FO by, let's first start by putting in the missing term, which is FG. And then to add the last two terms, remember that the last two terms have the opposite signs, so we do minus FO by. The same is true for the fourth row. We have a FG over here, and all of these terms have the opposite signs from all of these terms. And the same is true for the sixth row. F of B will be equal to FG minus FO by. Notice that we have a nice pattern here. F of B is equal to FO by, or it is equal to FG minus FO by. So let's generalize this into an equation. We'll define ILC to be equal to the current tick. And then we'll come up with the formula for F of B in terms of FO by. First, notice that for time interval between T0 and T1, and T2 and T3, T4 and T5, and T6 and T7, we had the term F of B is equal to FO by. And for these time intervals, let's see where the current tick is. For time between T0 and T1, the current tick was above tick I. For time interval between T2 and T3, again the current tick was above tick I. And the same goes for the time interval between T4 and T5, and the time interval between T6 and T7. The current tick was above tick I. So going back to this equation, we can generalize this. When the current tick I of C was greater than or equal to tick I, fee growth below F of B is equal to FO of I. And in the other cases, we can see that the current tick was below tick I. So this will be the time between T1 and T2, T3 and T4, and T5 and T6. Okay, so going back over here, we can say that when the current tick I of C was less than tick I, fee growth below is equal to F of G minus FO of I. And now we have an equation for what fee growth below is in terms of FO of I and the current fee growth FG. In the next video, we'll derive the equation for fee growth above in the same manner that we did over here. In the previous video, we came up with a formula for fee growth below based on fee growth outside. In this video, we'll do the same for fee growth above. We'll derive the equation for fee growth above based on fee growth outside. So let's start with definitions. We'll say that F of G is equal to the fee growth of token Y at current time. And we also define something similar called F of GK. This will be the fee growth of token Y at time tk. And again, this notation for time has a restriction. T of k is less than T of k plus 1, and T of k plus 1 is less than T of k plus 2, and so on. In other words, time is always moving forward. And then we'll define F of A to be the fee growth of token Y above tick I. In this video, we'll look at an example of how to calculate fee growth above, and then we'll relate it to fee growth outside. And again, for the algorithm for fee growth outside, we'll follow this algorithm. You'll say FO of I to be equal to the fee growth outside at tick I. To initialize this fee growth outside, you'll say that fee growth outside is equal to F of G if current tick I of C is greater than or equal to the tick that is associated with this fee growth. Otherwise, when we initialize fee growth outside and the current tick is less than this tick I, then we initialize it to 0. And again, to update it, when the fee growth crosses this tick I, we update this fee growth outside by the following algorithm. FO of I is equal to the current fee growth minus the current FO of I. Okay, so with that said, let's now look at an example of fee growth above. Let's say that we have some tick I, and over time the fee growth went left and right. Sometimes this fee growth was above this tick I, and other time it was below it. And what we're going to do is calculate the fee growth above, F of A. Visually, this fee growth above is a sum of the height of these red rectangles. On the right, what we're going to do is calculate what fee growth above should be for each time interval. And once we calculate the column for fee growth above, next we'll calculate fee growth outside. And this will be based off of this algorithm over here. And lastly, using the fee growth outside, we'll recalculate fee growth above. Okay, so let's start with the first time interval, the time interval between t0 and t1. So let's see where fee growth is for time interval between t0 and t1. At time t0, let's say that the fee growth was over here, and at time t1, the fee growth was over here. In between the time between t0 and t1, fee growth will be somewhere over here. And in this case, what is the fee growth above? Well, to calculate this, what we have to do is sum up all of the heights of the red rectangle that is below FG1. In this case, we don't have any red rectangles below FG1. So in this case, we start out with fee growth above equal to 0. Okay, how about for time between T1 and T2? For time between T1 and T2, the fee growth will be over here. At time T1, fee growth started over here, and at time T2, this fee growth crossed over this tick. And what is fee growth above? Well, between time T1 and less than T2, the fee growth will be somewhere over here. The height of this red rectangle, in this case, will be the current fee growth minus the time that it crossed above tick I, which will be at FG1. So the height of this red rectangle for the time interval between T1 and less than T2 is expressed by FG, the current fee growth, minus FG1. At time T2, the current fee growth crossed over tick I. For time between T2 and T3, we know that the height of the red rectangle is given by this height of the red rectangle. So the fee growth above, in this case, will be FG2 minus FG1. For the time interval between T3 and T4, the fee growth was somewhere over here. So fee growth above will be the height of the previous fee growth above, which will be the height of this red rectangle, plus the height of the red rectangle over here. The height of this red rectangle is given by FG2 minus FG1. And the height of the red rectangle when the fee growth is over here is given by FG minus FG3. FG3 is the base of this red rectangle, and FG over time will travel from starting from here and then keep going up. So the height is given by FG minus FG3. For the time interval between T4 and T5, we know that the fee growth above is the height of this red rectangle plus the height of this red rectangle. So fee growth above is given by FG4 minus FG3. That's the height of this red rectangle, and FG2 minus FG1. That is the height of this rectangle. For the time interval between T5 and T6, the current fee growth will be over here. And fee growth above will be the height of this red rectangle, wherever this fee growth might be, between time T5 and T6, plus the previous fee growth above. Again, the previous fee growth above is given by these terms, which I copied and pasted from the row above. And then the height of this red rectangle will be FG minus FG5. And for this last example, let's look at the time interval between T6 and less than T7. And in this case, the fee growth above will be the sum of this red rectangle plus this red rectangle and this red rectangle. Okay, now that we filled out fee growth above, next let's fill out fee growth outside. To begin with, let's review how Uniswap V3 initializes this fee growth outside. Going above, fee growth outside is initialized as the current fee growth if the current tick I of C is greater than or equal to the tick I associated with the fee growth outside. Otherwise, it is initialized as 0. Okay, so how about in our case? when we initialize fee growth outside, where's the current tick, IFC, and where's the tick associated with this fee growth outside. So going here, let's say that we initialize the fee growth outside over here. Current tick will be over here. And the tick that is associated with this fee growth outside is over here. In this case, we have the current tick less than this tick I. So we will initialize this fee growth outside to be equal to 0. At time t1, we see that the fee growth crosses tick I. For fee growth outside at time t1, we will need to apply this update rule. The new fee growth outside is equal to the fee growth when it crossed over tick I, and then to this we need to add minus the current fee growth outside. The fee growth when it crossed over tick I is FG1. And then from this we need to minus the previous fee growth outside. The previous one is equal to 0. So minus 0, and this is still equal to FG1. Okay, let's move on. At time t2, the current tick again crossed over tick I. So we need to apply the update rule again. The fee growth when it crossed over tick I is given by FG2. And the previous fee growth outside is given by FG1. So we do a minus FG1. Next, at time t3, again the current tick crossed over tick I. So we need to update this fee growth outside again. The fee growth when it crossed over tick I is given by FG3. The previous fee growth outside is given by FG2 minus FG1. And from this, we need to flip all of the signs. So we get minus FG2 plus FG1. The next time the current tick crosses over tick I is at time t4. Fee growth at this time is FG4. To this, we add the minus of the previous fee growth outside. And the pattern repeats for time t equals to 5 and time t equals to 6. Okay, now that we filled out fee growth outside, let's now see how fee growth above relates to fee growth outside. Can we come up with an equation for fee growth above based on fee growth outside? Similar to what we saw in the previous video when we related fee growth below with fee growth outside, here we'll see a similar pattern. For rows 1, 3, 5, and 7, fee growth above and fee growth outside are exactly the same. Here we have a 0, here we have a 0. On row 3, we have FG2 minus FG1. And over here, we also have FG2 minus FG1, and so on. Okay, so how about even rows? How can we get the equation for fee growth above based on fee growth outside? Let's start with the second row. On the second row, notice that for fee growth above, we have FG minus FG1. And for fee growth outside, we only have FG1. Here, we don't have the term FG that is present over here. However, we do have the terms FG1 that is over here and over here. However, the signs are flipped. So to rewrite fee growth above in terms of fee growth outside, let's start by putting in the missing term, which is FG. Okay, so we have FG. And then next, we have the same terms, FG1. However, we have a minus here, and over here, we have a plus. We can easily fix this by putting in a minus FO of I. So what we're doing here is putting a minus over here. So now, F of A is equal to this term. We do the same for the fourth row. We have a FG, we don't have a FG. For F of A, we have the terms FG3, FG2, and FG1. And for FO of I, we also have the same terms. Again, you'll notice that the signs are flipped. So to get fee growth above in terms of fee growth outside, we start with the missing term, F of G, and then we'll need to add fee growth outside and flip the signs. You can check for yourself that row 6 is the same. So now we have a nice pattern for how to calculate fee growth above. Let's generalize this into an equation. We'll rewrite fee growth above in terms of fee growth outside and the current fee growth FG. We'll define IFC to be equal to the current tick. And fee growth above, F of A is equal to, remember that when we started out with fee growth above below tick I. And we can double check this if you go back over here. Fee growth above started below tick I. And at each time, the fee growth crossed over this tick I. So going back over here, we know that for over here, current tick was less than tick I. For the next one, we know that the current tick was above tick I. And for the next one, we know that the current tick was less than tick I. And again, for the next one, we know that the current tick was above tick I. And so on. So let's now generalize this. When the current tick IFC was greater than or equal to tick I, fee growth above is given by FG minus FO of I. On the other hand, when the current tick was less than this tick I, fee growth above was given by FO of I. What we did here was we just summarized these equations. What we accomplished so far is we found out a formula for fee growth below and also for fee growth above. In the next video, we'll use this fee growth above, fee growth below, and fee growth inside to calculate the amount of fees that can be collected from a liquidity position. In the beginning of the video, we defined a function called f(bar) that takes in two inputs, tick I lower and tick I upper, and we defined this to be equal to the fee growth inside tick I lower and tick I upper. We also said that this is equal to the current fee growth minus the fee growth below of tick I lower minus the fee growth above of tick I upper. And now we know what all of these are. The current fee growth is a state variable that is stored inside the contract of Uniswap V3. And we also know how to calculate fee growth below for any tick and fee growth above for any tick as well. So now we know how to calculate fee growth inside between two ticks, tick I lower and tick I upper. Now, while the fee growth is a state variable that was initialized when the smart contract was deployed, a liquidity position can be created and removed at any time. So to calculate the fee growth inside for a position, we need to calculate the fee growth inside when this position is created and also when the fee is collected. Taking the difference of these two fee growths will give us the correct fee growth inside for this liquidity position. So let's say that we created a position at time t0. Then let's say that we claim the fee at time t1. At time t0, we need to calculate the fee growth inside. And then at time t1, when we actually claim the fees, we'll need to recalculate the fee growth inside again. Taking the difference, this will give us the correct fee growth inside for a position. Now, why do we need to take the fee growth inside when a position is created and also when we claim fees? One way to understand this is, let's say that we only take the fee growth inside when we claim the fee. So this will be f1. Loosely speaking, this will mean that we're taking the fee growth inside of tick I lower and tick I upper ever since the contract was deployed. But the time that the liquidity position was created was probably after the contract was deployed. So what we need to do here is sort of like taking a snapshot of the fee growth inside when the liquidity position is created, and then recalculating the fee growth inside to claim the fees. The difference of f1 and f0 will give us the fee growth inside between the times t0 and t1. Okay, so now that we know how to calculate a fee growth inside for a position between time t0 and t1, we're now ready to calculate the fee for this liquidity position. To calculate a fee for a liquidity position, let's say that S is a liquidity for a position between tick I lower and tick I upper. And we'll say that this S remains a constant over time. In this case, the fee that can be collected for this liquidity position is given by the following equation. The liquidity S times the difference of the fee growth inside, F1 minus F0. And again, F0, we denote this as the fee growth inside when this liquidity was created, and F1 will be the fee growth inside when the fee is actually claimed. Taking the difference and then multiplying by the liquidity S. This will give us the fee that can be collected for this liquidity position. In this video, we'll look at the code that are relevant for calculating the fee growth for a liquidity position. The first part that we'll look at is under a contract called tick.sol, and this contract is under the repo V3 core, contracts, library, and the contract is called tick.sol. Inside this tick.sol contract, there's a function called update, and scrolling down, you can see over here. This part of the code contains the logic for how fee growth outside is initialized. And you can see over here that if the tick that is associated with this fee growth outside is less than or equal to the current tick, then this fee growth outside is initialized to be the current fee growth. And the fee growth is tracked both for token 0 and for token 1. Remember a few videos back, we said that the fee growth outside is initialized as the current fee growth when the current tick is greater than or equal to the tick that is associated with this fee growth. And this part of the code is how the fee growth is initialized. Next, let's take a look at what happens when the current tick crosses over the tick and how the fee growth outside is updated. Scrolling down, there's a function called cross. This function will be called when the current tick crosses over a tick. And when it does, the fee growth outside that is associated with this tick is updated by the following. The new fee growth outside is equal to the current fee growth minus the current fee growth outside. And this is true for both token 0 and for token 1. We're still in the same contract. Next, let's take a look at a function that will calculate the fee growth inside. So I'll scroll up, and I am looking for a function called getFeeGrowthInside. Remember the math equation that calculates the fee growth inside. And this is how the code is implemented. The first part of the code calculates the fee growth below. If the current tick is greater than or equal to the lower tick, then the fee growth below is set to be the fee growth outside associated with this lower tick. Otherwise, it is equal to the current fee growth minus the fee growth outside. And similarly, the fee growth above is calculated as following. If the current tick is less than the upper tick, then the fee growth above is equal to the fee growth outside associated with the upper tick. Otherwise, it is equal to the current fee growth minus the fee growth outside. And once fee growth above and fee growth below are calculated, to calculate the fee growth inside, we do take the current fee growth and then minus the fee growth below and the fee growth above. This is how fee growth inside is calculated. To see how a fee that can be collected for a liquidity position is calculated, we need to look at another contract. The contract is called position.sol and it is located under the folder libraries. The function that we need to look at is called update. And inside here, we can see how the fee is calculated. For example, for token 0, we take the current fee growth inside and then minus it with the previous fee growth inside that is associated with this liquidity position. And then we multiply by the liquidity to calculate the amount of token 0 that is owed as fee. And the same goes for token 1. And that is how a fee is calculated for each liquidity position in Uniswap V3. Uniswap V3 allows you to borrow tokens as long as the tokens plus some fee are paid in the same transaction. This is called a flash loan. And to get a flash loan in Uniswap V3, you'll need to call a function called flash on the contract Uniswap V3 pool. It's going to take 4 parameters: recipient, amount 0, amount 1, and data. Recipient is the address that Uniswap V3 will send the tokens to, and amount 0 and amount 1 are amount of tokens to send. And data is an arbitrary bytes data that is sent to the Uniswap V3 flash callback contract. Inside this function, it first calculates the fee, and then next it gets the balance of token 0 and token 1 before the tokens are sent out. After that, token 0 and token 1 are sent to the recipient for the amounts amount 0 and amount 1. And then next, it calls a contract called Uniswap V3 flash callback on message sender. And it calls the function called Uniswap V3 flash callback. For the parameters, it's going to pass in the fees, fee 0 and fee 1. Fee 0 is the fee on token 0 and fee 1 is the fee on token 1. And then the arbitrary data that was passed as input to this function. Notice that it calls the function Uniswap V3 flash callback on message sender. So this means that message sender must be a contract, and this contract must call into the function flash. And then after the function Uniswap V3 flash callback is executed on message sender, it gets the balance of token 0 and token 1 after this function is done executing. So when we get a flash loan, we'll need to write our custom logic inside this function. And then after this function is done executing, it's going to check that the balance of token 0 and token 1 after is greater than or equal to the balance before plus the fees. Next, it calculates the fee to be given to the protocol and the fee that is given to the liquidity provider. And you can see over here that the fee growth global for token 0 and token 1 are updated. And that completes the quick code walkthrough for the function flash. Here's an exercise to get a flash loan from Uniswap V3. Inside this contract, there are several tasks, so let's take a look at them. The first task is inside the function called flash. This function will be called to initiate a flash loan from a Uniswap V3 pool. And the first task is to ABI encode a struct called flash callback data. If we scroll up, you can see what this struct is. Inside the struct, we have 3 parameters. Amount 0, this will be the amount of token 0 to borrow. Amount 1, the amount of token 1 to borrow. And the caller. The caller will be the caller of flash. So inside the function flash, this will be message.sender. Once you ABI encode this struct called flash callback data, the next task is to call the function flash on Uniswap V3 pool. The Uniswap V3 pool and token 0 and token 1 are all initialized inside the constructor. And if you need to know what parameters to pass to call the function flash, you can navigate to where the interface Uniswap V3 pool is defined. Scrolling up, this is where it's defined. Under source, interfaces Uniswap V3 Uniswap V3 pool. If you go here, you'll know what parameters to pass to call the function flash. When the function flash is called on the Uniswap V3 pool, the Uniswap V3 pool will call a callback called Uniswap V3 flash callback. And inside here, the pool will pass 3 parameters: fee 0, fee 1, and the data that will be passed from the caller. So back in task 2, Once you ABI encode the flash callback data, pass this data into the function flash, and you'll be able to get the same data over here. For task 3, check that message.sender is actually the pool contract. And then next, decode this data into flash callback data. This flash callback data, again, encodes these 3 data. And using these, transfer the fees that was requested, fee 0 and fee 1, from the caller. In this case, this will be the account that called into the function flash. Once the fee is paid by this caller, repay the Uniswap V3 pool for the amount borrowed and the fee. Now, if you wanted to add more custom logic, for example, maybe after getting a flash swap, you might want to do an arbitrage, then you will write your custom logic in between either task 4 and 5 or 5 and 6. Next, let's take a look at the test. The test is inside Uniswap V3 exercises Uniswap V3 flash.test.sol. And here's the setup. The pool that we're going to be testing on is the Uniswap V3 DAI ref pool with 0.3% fee. And this test contract is given 1,000,000 DAI. And it approved the Uniswap V3 pool contract to spend an infinite amount of DAI. Inside the test, it will initiate a flash loan by calling the function flash on the Uniswap V3 flash contract that you wrote. And then for simplicity, it will just log the fees that the Uniswap V3 pool requested. Okay, so that is the exercise for Uniswap V3 flash. Let's go over the solutions. The first task is to ABI encode the flash callback data. So let's say bytes memory data is equal to ABI.encode. We'll encode the struct flash callback data, and then we'll fill out the data that we need for this struct. So the data that we need are amount 0, amount 1, and caller. Amount 0, this will come from the input, amount 0, and the same for amount 1. Amount 1 will come from the input. And the caller will be message.sender. The caller of the function flash is message sender. Okay, so that's task 1. Let's move on to task 2. Call Uniswap V3 pool.flash. How do we call this function? Well, let's navigate to this interface, Uniswap V3 pool, and find out how to call this function flash. Inside the interface, Uniswap V3 pool, let's find where the function flash is defined. Okay, here it is. For the parameters, it's easy to remember: recipient, amount 0, amount 1, and data. Going back to our contract, the pool contract is already initialized, so I'll say pool.flash recipient. Who is going to receive the tokens that we want to borrow? In this example, this will be this contract. So this will be address this. Amount 0. We'll just simply pass the amount 0 that's specified over here. Amount 0. And then same for amount 1. And then lastly, data. This is the data that we prepared in task 1. Okay, so that completes task 2. Let's move on. Task 3. Check message sender is pool. We can do this by saying require message.sender is equal to address of the pool. Only the Uniswap V3 pool contract will be able to call this Uniswap V3 flash callback. And for the error message, I'll just say not authorized. The next task is to decode the data from the input into the struct flash callback data. So say flash callback data memory, I'll name this decoded, is equal to ABI.decode the data, and we're going to decode this data into the struct flash callback data. The next task is to transfer fees from flash callback data.caller. This will be the fee that will be repaid to the pool contract, and the fees are specified by the pool, fee 0 and fee 1. So say if fee 0 is greater than 0, then transfer token 0 dot transfer from the decoded data, decoded.caller, and then let's transfer this to this contract, address this, for the amount, fee 0. And we'll do the same for fee 1. If fee 1 is greater than 0, for token 1, transfer from decoded.caller to this contract for the amount, fee 1. Okay, the last task is to repay the pool for amount borrowed plus fee. For token 0, we know that we borrowed some amount if this decoded amount 0 is greater than 0. So say if decoded.amount 0 is greater than 0, then token 0 dot transfer to the pool contract, address pool, for the amount the amount that we borrow, decoded out amount 0, plus the fee that we need to repay, fee 0. And let's do the same for token 1. If decoded.amount 1 is greater than 0, then transfer token 1 for the amount 1, plus fee 1. And that completes task number 6. And again, this was a simple example of flash swap. And if you wanted to add some custom logic, like doing an arbitrage after getting a flash swap, then you will write your custom logic in between task 4 and 5 or 5 and 6. Okay, let's execute the test. Inside my terminal, I'll first set the environment variable for fork URL. Next, we'll execute the test by typing forge test and then fork URL, and then the path to the test, match path test Uniswap V3 exercises Uniswap V3 flash dot test dot sol, and then we'll print out the console logs -bbb. Okay, and our test passed. In Uniswap V2, the time-weighted average price, also called TWAP, is taken by summing up the prices for each second and then dividing it by the duration. Basically, it is taking the arithmetic mean of the prices. However, in Uniswap V3, the time-weighted average price is calculated by the geometric mean. Basically, you multiply the prices for each second, and let's say that there are n prices. Next, you take the nth root of all of these numbers that you just multiplied. This is the geometric mean. To be more precise, let's say that there are numbers a1, a2, a3, all the way up to an. There are n numbers. And now to calculate the geometric mean of all of these numbers, what you would do is multiply all of these numbers from a1, a2, a3, all the way up to an. And since there are n terms, you would take the nth root of this multiplication. This is the geometric mean of the numbers a1, a2, all the way up to an. To calculate the TWAP in Uniswap V3, we would take the geometric mean of the prices that are taken for each second. For example, let's say that we have the prices P of T1 plus 1, P of T1 plus 2, P of T1 plus 3, all the way up to P of T2. Price for each second in the time interval from T1 plus 1 to T2. Then to calculate the TWAP, let's call this P average. And to calculate this, we first multiply all of these prices, and then we'll need to take the nth root of this multiplication. Okay, but how many terms are there between the time intervals from T1 plus 1 to T2? Let's consider the case when there are only two prices, T1 plus 1 and the price at T1 plus 2. In this case, there are two prices, so there are two terms. As another example, how many terms in between T1 plus 1 to T1 plus 3? Well, we can just count them, 1, 2, and 3. We can also come up with a math equation that will tell us how many terms are in between from the time intervals T1 plus 1 to T2. We start out with the last term, T2. And then from this, we minus the first term. This will be T1 plus 1. And then we also need to include this term, so we'll need to add a plus 1. This is the amount of prices that are in between the time intervals T1 plus 1 to T2. And this is equal to T2 minus T1. And to quickly see that this equation is correct, let's say again that there are only two prices, T1 plus 1 and T1 plus 2. When we apply this equation using only two terms, do we get the correct number of terms? So let's say that T2 is equal to T1 plus 2. And for T1 plus 1, we'll keep it the same. So let's say T1 plus 2 minus T1 plus 1. The difference will be 1 plus 1, and that will be 2. So the number of terms between T1 plus 1 and T1 plus 2 will be 2 terms. Let's see another example. Let's say that we want to count the number of terms between T1 plus 1 and T1 plus 3. If we replace T2 with T1 plus 3 and then do this math, what do we get? We have a plus 3, and then we have a minus 1, so that's 2, and then plus 1, so that's 3. So 3 terms. Okay, so it looks like this equation correctly describes the amount of terms in between the time duration T1 plus 1 and T2. And now we need to take the nth root where n is equal to the number of terms that we multiplied. Here we calculated the amount of terms here are T2 minus T1. And this is how the TWAP is calculated in Uniswap V3. Now, of course, inside a smart contract to calculate the time-weighted average price, you wouldn't want to multiply all those prices. It would take too much gas. So, Uniswap V3 uses a clever trick so that we can still calculate the time-weighted average price without multiplying all of the prices for each second. This is done by storing a state variable called a tick cumulative. This tick cumulative is a accumulator of all of the prices ever since the contract was deployed. But before I explain what tick cumulative is, let's first review what price and ticks are. So as a review, let's go over price and tick. Let's say that P is the price. And just like in Uniswap V2, you can think about this price as the ratio of token Y over token X. In other words, the price of token X in terms of token Y. And we'll label T as the tick. The relationship between the price and the tick is given by the following equation. Price is equal to 1.0001 raised to the tick. Next, I'll explain what price accumulator is. Let's first define T of I to be equal to the tick at time I. Then the price accumulator, we'll label this as A of T, is equal to the sum from I equals 0 to I equals T of the tick at time I. So what we're doing here is summing up all of the ticks ever since the contract was deployed for each second. Okay, so with this price accumulator, how will we calculate the time-weighted average price in Uniswap V3? What is the relationship between this equation and the price accumulator? We'll first start with this equation of the time-weighted average price between the time intervals t1 plus 1 to t2. And then we'll work our way down to rewriting this equation in terms of the price accumulator. So first, I'll rewrite this, the inner prices, using the ticks. So the price at time t1 plus 1 can be rewritten as 1.0001 raised to the tick at time t1 plus 1. And the same goes for time at t1 plus 2, t1 plus 3, and all the way up to time t2. Next, I'll rewrite this n through using exponents and a fraction. Also, if you remember your math from high school, you know that if we have the same base and it is multiplied by different exponents, then we can take the same base and then just add up the exponents. So we have 1.0001 raised to the sum of the ticks t of t1 plus 1, t of t1 plus 2, all the way up to t of t2. Next, I'll rewrite this sum using the summation notation. So the summation will go from I equals to t1 plus 1 all the way up to t2. Now notice that we have something that looks like the price accumulator. Going back up, we said that this is the price accumulator. So I'll paste this here. And let's compare this term to this term. For the price accumulator, it starts from I equals to 0. However, in this expression, we have that I starts from t1 plus 1. Is there a way where we can rewrite this in terms of the price accumulator? Well, what we can do is we first need the price accumulator to go up to time t2. So let's rewrite this as A of t2. We take the price accumulator all the way up to time t2. So this will be equal to, just go up to time t2. Okay, let's now compare this term with this term. On the right, I have extra terms that starts from I equals to 0 all the way up to I equals to t1. So if we minus all of the terms from I equals to 0 to I equals to t1, then we will get all the terms that are inside this summation. So what we need to do is take the price accumulator all the way up to t1, and then minus it from the price accumulator at2. This will cancel out all of the terms that start from I equals to 0 to I equals to t1. So this is equal to at2 minus at1 is equal to this term over here. The price accumulator at2 goes all the way up to time t2, but it also has some terms from I equals to 0 to I equals to t1 that are not present in here. So if we minus all of the terms from I equals to 0 to I equals to t1, then this part of the equation is equal to this summation. Okay, so now we can rewrite this as, we'll just replace this summation with the price accumulator. at2 minus at1. And this top part, at2 minus at1, divided by the time interval t2 minus t1, is called a time-weighted average tick. What we showed is that we can rewrite the time-weighted average price of this form using the price accumulator, and then rewrite it as this equation. This is the equation that is used to calculate the time-weighted average price in Uniswap V3. In Uniswap V3, if you know the average price of token X, then you can easily calculate the average price of token Y. You will simply take the reciprocal of the average price of token X. However, this equation does not apply in Uniswap V2. Let's call P of X the spot price of token X in terms of token Y. And if you want to think about in real tokens instead of token X and token Y, an easy way to remember is having token X equal to ETH and token Y equal to some stablecoin like USDC. And we'll label P of Y to be the spot price of token Y in terms of token X. And for the spot price, both in Uniswap V2 and in Uniswap V3, this is true. If we know the spot price of token X, then we can calculate the spot price of token Y to be equal to 1 over the spot price of token X. However, when we take the time-weighted average price of token X and token Y, this is not true in Uniswap V2. So let's label P of X of average to be equal to the TWAP of token X, and P of Y of average is the TWAP of token Y. In Uniswap V2, the time-weighted average price of token Y, P of Y of average, is not equal to 1 over the time-weighted average price of token X. However, in Uniswap V3, this is true. If we know the time-weighted average price of one token, then if we just do 1 over that, then we get the time-weighted average price of the other token. Let's go through an example of calculating the time-weighted average price of both tokens, both in Uniswap V2 and in Uniswap V3. We'll start with Uniswap V2 and see that just because we know the time-weighted average price of one token doesn't mean that if we take the 1 over that, we'll get the time-weighted average price of the other token. Let's calculate the time-weighted average price using a simple example. Let's say that at time 0, the price of token X was equal to 3,000, and that from time 1 all the way up to time 3, the price was at 1,000. To calculate the time-weighted average price of token X in Uniswap V2, all we have to do is take the price at each second, add them all up, and then divide by the duration. From time 0 to 1, we have 3,000. From time 1 to 2, we have 1,000. And then from time 2 to 3, we have 1,000 again. So on the top, we have 3,000 plus 1,000 plus 1,000. And the whole duration is 3 seconds. So we divide the sum of the prices by 3. And we get 5,000 divided by 3. Okay, how about the time-weighted average price of token Y? Now, given that the spot price of token X was 3,000 from time 0 to 1, and then 1,000 from time 1 to 3, the spot price of token Y can be calculated by taking 1 over this price. And we're using this equation over here. The spot price of token Y at each second is calculated by just taking 1 over the price of token X. So the first one will be 1 over 3,000, the next two will be 1 over 1,000. The whole duration is 3 seconds. Simplify this and we get 7 over 9,000. And now let's compare the time-weighted average price of token X with the time-weighted average price of token Y. Let's start with the time-weighted average price of token Y. So we calculated this to be equal to 7 over 9,000. And now we want to compare this with this equation. We want to double check that just because we know the time-weighted average price of token Y doesn't mean that we also know the time-weighted average price of token X. So going back over here, what is 1 over the time-weighted average price of token X? Well, this is equal to, we just flip the denominator and the numerator, and the 5,000 goes to the bottom and the 3 goes to the top. We get 3 over 5,000. And as you can see, these two are not equal. So we just shown that in Uniswap V2, just because we know the time-weighted average price of one token, doesn't mean that we can simply calculate the time-weighted average price of the other token by taking 1 over that time-weighted average price. So this is an example in Uniswap V2. How about in Uniswap V3? So we said earlier that if we know the time-weighted average price of one token, then we can easily calculate the time-weighted average price of the other token. So let's go through a simple example using the same price over the same duration. To calculate the time-weighted average price in Uniswap V3, we first need to calculate the time-weighted average tick. So let's call T of X of average to be equal to the average tick of the price of token X. And let's name T of Y of average to be equal to the average tick of the price of token Y. Once we figure out the average ticks, to calculate the average price, we would take 1.0001 raised to these average ticks. Okay, let's start by calculating the average tick of token X. From the previous example, we had the price equal to 3,000 for the first second and 1,000 for the next 2 seconds. To calculate the tick given the price, we would need to take the log of 1.0001 for each of the prices, and the duration is 3. This turns out to be roughly equal to 72,743. Okay, next let's calculate the time-weighted average tick for token Y. Given that the spot price of token X was 3,000, 1,000, and 1,000, the spot price of token Y will be taking the 1 over the spot price of token X. So this will be 1 over 3,000, 1 over 1,000, and 1 over 1,000 again. And to convert the spot price into ticks, we will again need to take the log of 1.0001. And again, the duration is 3. Now, although these two equations don't look similar, here's the interesting part. This 1 over 3000, we can convert it to minus log of 1.0001 to 3000. And the same for the next two terms. Now, notice that the first term for the time-weighted average tick of token X is equal to the time-weighted average tick of token Y, except we have a minus here. And the same goes for the last two terms. Since the time-weighted average tick of token X, we calculated this to be roughly 72,743. The time-weighted average tick of token Y, the terms are the same except we have a minus sign, so this is roughly equal to minus 72,743. Okay, let's now calculate the time-weighted average price in Uniswap V3. Let's start with the time-weighted average price of token Y. This is given by the equation of 1.0001 raised to the time-weighted average tick of token Y. And we calculated this time-weighted average tick of token Y to be roughly equal to minus 72,743. So this price is roughly equal to 1.0001 raised to the minus 72,743. And this is equal to 1 over 1.0001 raised to the 72,743. But now notice this part. This is roughly equal to 1.0001 raised to the time-weighted average tick of token X that you can see over here. And let's compare the last two terms. 1.0001 raised to the time-weighted average tick of token X is exactly equal to the time-weighted average price of token X in Uniswap V3. So what we've shown here is that in Uniswap V3, if we know the time-weighted average price of one token, then we can easily calculate the time-weighted average price of the other token by taking 1 over that. We've seen an example in Uniswap V3. Next, let's actually go through the math to see why that the time-weighted average price of one token is equal to 1 over the time-weighted average price of the other token. We'll name T of I to be equal to the tick at time I. And let's say that P of X of I is the price of token X at time I, and this is equal to 1.0001 to the T of I. To calculate the spot price of token Y at time I, we would take 1 over the spot price of token X at time I. And from this equation, we can derive a useful equation that we'll use later. The right part of this equation is equal to 1 over 1.0001 raised to the tick of I. Okay, but this is equal to 1.0001 raised to the minus T of I. Okay, so we'll come back to this equation later. Let's say that we wanted to calculate the time-weighted average tick of token X over some time interval where the duration is equal to n. Then the equation is given by this formula. Add all of the ticks from time t1 plus 1 all the way out to t1 plus n, and since there are n terms, divide this by n. Okay, and to calculate the time-weighted average tick of token Y, we'll need to do something similar, except what will be the tick for token Y at time I. Well, we can take a look at this equation to figure out what the tick is for token Y. At time I, the tick is given by minus T of I. So the average tick over the same duration, n, will be equal to the summation from I equals to t1 plus 1 to t1 plus n, and then we sum up all of minus T of I. And then there are n terms, so we divide by n. The difference between the time-weighted average tick of token X and the time-weighted average tick of token Y is that here we have a minus and here we don't have a minus. We can now calculate the time-weighted average price of token Y. This is given by 1.0001 raised to the time-weighted average tick of token Y. And from this equation over here, we said that these two are only different by a negative sign. So rewriting T of Y of average, we can just simply put minus Tx of average. And this is equal to 1 over the time-weighted average price of token X. And this is the mathematical explanation of why the time-weighted average price of one token is equal to 1 over the time-weighted average price of the other token. How would the time-weighted average price in Uniswap V2 and in Uniswap V3 react when the price changes suddenly? To find this answer, I wrote a simple Python script, and in this Python script, it calculates the time-weighted average price both in Uniswap V2 and then in Uniswap V3. And then it will graph the spot price, the time-weighted average price in Uniswap V2 and in Uniswap V3 over time. So for the first simulation, I have the price, where at each second it's equal to 1000, and at some time, the price drops to 1, and then it remains 1 for the rest of the time. This is the spot price. The next part of the code calculates the cumulative price in Uniswap V2 and the cumulative tick in Uniswap V3. And then the code after that calculates the time-weighted average price for Uniswap V2 and in Uniswap V3. And lastly, it plots the graph of the spot price and the time-weighted average price in Uniswap V2 and in Uniswap V3. The spot price is shown in blue, and we can see that the price is at 1,000 and all of a sudden it drops to 1. The time-weighted average price in Uniswap V3 is shown in green, and you can see that it sort of follows the spot price, and when the price drops, it sort of curves and then converges to the spot price. Now take a look at the time-weighted average price in Uniswap V2. It follows the spot price, and then when the price drops, it slowly converges to the spot price of 1. To summarize what's happening here, when the spot price suddenly drops, the time-weighted average price calculated in Uniswap V3 converges to the spot price quicker than the time-weighted average price calculated in Uniswap V2. Okay, so this is a situation when the price suddenly drops. Let's take a look at another situation. Let's see how the time-weighted average prices react when the price suddenly spikes up. So, the price is at 1 for some few seconds, and then all of a sudden, let's say that the price spikes to 1,000, and then it remains at 1,000 for the rest of the time. And then let's run the simulation again. Scroll down, and let's see what the graph looks like. So, let's start with the spot price. The spot price is at 1, and all of a sudden, it jumps up to 1,000. How about the time-weighted average price in Uniswap V3? This is shown in green. The time-weighted average price in Uniswap V3 initially doesn't react to the jump in price. It remains close to the previous spot price, which is equal to 1, and then all of a sudden it catches up to the new spot price. However, the time-weighted average price calculated in Uniswap V2 immediately reacts to the price change going up, and at each second, this time-weighted average price calculated in Uniswap V2 is always greater than or equal to the time-weighted average price calculated by Uniswap V3. To summarize, when the spot price spikes up, the time-weighted average price calculated in Uniswap V2 reacts quicker than the time-weighted average price calculated in Uniswap V3. In the previous video, I explained how Uniswap V3 stores the data that accumulates the ticks for each second. In this video, I'll explain where this cumulative tick is actually stored and how it is updated. So, we'll take a look at 3 contracts: the Oracle, Uniswap V3 pool, and the Oracle library. The first contract, oracle.sol, is inside the repo V3 core libraries oracle.sol. And inside here, we'll first take a look at a struct called observation. This is a struct that stores some tick cumulative at some time block timestamp. Whenever the liquidity inside a Uniswap V3 pool contract changes, or whenever the price changes, this observation struct is stored inside the Uniswap V3 pool contract. Inside the struct, there are 2 other data: seconds per liquidity cumulative x128 and initialized. But we won't cover this in this video. We will mainly focus on tick cumulative, how it is updated, and how we can actually use this to calculate the TWAP. A new observation struct is saved whenever the liquidity changes or the price changes, and this is done by calling a function called write. Let's go to the Uniswap V3 pool and actually see where this function called write is called. First, we can see here that it calls observations.write. This is called inside the function modify position. Again, whenever the liquidity changes, this modify position is called, and inside it, it stores the observation. The other place where observations.write is called is inside the function swap. So whenever there's a swap and the current tick changes, observations.write is called. The next function that I'll explain is called observe inside the Uniswap V3 pool contract. This is a function that you'll call to get the tick cumulatives. For the input, you'll pass in an array of seconds ago from now. For example, 0 will mean 0 seconds ago from the current time, so this will be the current time. And if this array element contains a 1, this means that 1 second ago from the current time. This seconds ago is directly passed to another function, an internal function called observations.observe. And this internal function is fed with more inputs: the current timestamp, the current tick, and the current liquidity. Let's take a look at this function, observations.observe. This function is located inside the Oracle library, and here it is, the function observe. What this function will do is for each seconds ago, it will calculate the tick cumulative at that time. And this is done by calling the function called observe single. Let's take a look at this function. Okay, here's the function observe single. When the seconds ago that is passed from the input is equal to 0, then this means that it's trying to get the current tick cumulative. And there are two cases. If the block.timestamp for the latest observation is not equal to the current time, then it calls another internal function called transform that would transform the last observation, accounting for the current time, and the last time this observation was updated. The simple case is when this block.timestamp for the last observation is equal to the current time. In this case, it would just simply return the tick cumulative and another data that is stored inside the observation called seconds per liquidity cumulative x128. Let's sidetrack and take a look at the function called transform. Remember that tick cumulative is the summation of the tick for each second. However, there's no guarantee that an observation was made for each second. So to calculate the tick cumulative for each second, what we need to do is take the last tick cumulative and then multiply this by the duration of how long this current tick was at the current tick. And this is done by taking the difference between the current timestamp and the last time an observation was made. This is called a delta, and we multiply this delta by the current tick. And this over here says that the current tick was at the current tick for this time interval called delta. And then we add this to the previous tick cumulative. This is how the tick cumulative up to the current block.timestamp is approximated. Going back to the function observe single, we just covered the function transform. And we also covered this part. If the input for seconds ago is not equal to 0, then we move on to this part of the code. The target timestamp will be the current time minus seconds ago. And from this target timestamp, it calls an internal function called getSurroundingObservations. Without looking at the details of how this function works, we can see that it returns two observations. Observation before or at this time, and another observation at or after this time. Next, it compares the two observations that was returned with the target time. If one of the observations that was returned matches the timestamp, then it returns the tick cumulative for that timestamp. If the target timestamp matches before or at observation, then it returns the tick cumulative for before or at. If the target timestamp matches the at or after timestamp, then it returns that tick cumulative. If neither of the two conditions are true, then we move on to this else block. Inside here, we know that the target timestamp is in between the two observations before or at and at or after. What this code inside here will do is draw a line between the two observations of before or at tick cumulative and after or at tick cumulative. And then over here, it does a linear approximation of the tick cumulative between the two tick cumulatives at before or at and after or at. If the target time is closer to the observation at or after, then this linear approximation will be close to the tick cumulative at or after. On the other hand, if the target timestamp is closer to the observation at before or at, then this code will return a tick cumulative that is closer to before or at. Okay, so that's the function observe single. So we covered a library called oracle.sol. This is a library that handles writing observations and fetching observations. But to actually implement a TWAP, I want to show you another contract called oracle-library.sol. Looking at this code will give you some hints on how to write a TWAP price oracle. This contract is located under B3 periphery libraries, and the name of the contract is called Oracle Library. Okay, there are two functions that I want to explain. The first function is called consult. One of the things that this function will do is return the average tick over some time duration, and this is called arithmetic mean tick. For the input, it's going to take in the pool and a number called seconds ago. Seconds ago from the current time. And using this input seconds ago, it's going to initialize an array of uint32, where the first element will be the seconds ago, and the next element will be 0 seconds ago from now. Next, it will call the function observe on the pool contract. Remember that this observe function returns the tick cumulatives for the seconds ago that were requested. And once we had the two tick cumulatives, one for the current time and one for the seconds ago, remember from the math video, we now know how to calculate the average tick over that time duration. And we can see this code over here. The tick cumulative delta is calculated by taking the difference of the two tick cumulatives. The tick cumulative stored at index 1, this will be the tick cumulative from 0 seconds ago. And the other one is tick cumulatives at index 0, and this will be the tick cumulative from seconds ago. And to calculate the average tick, inside this code it is called the arithmetic mean tick. You take this tick cumulative delta and then divide it by the seconds ago. Now, once we have this arithmetic mean tick, we need to call another function to calculate the time weighted average price of a token. And this is done by calling a function called getQuoteAtTick. The function getQuoteAtTick will calculate the amount of token out, given a tick, and amount of token in. Here, think about this base amount as amount of token in, base token will be token in, and quote token will be token out. Given these three inputs, it will calculate the amount of token out. Later, we'll use this function in the exercises, and for the tick, we'll pass in the time weighted average tick. From this tick, it will calculate the square root ratio x96. And then, there are two cases to calculate the amount of token out. Basically, they do the same thing, except that for better precision, the code is split into two parts, and this depends whether this square root ratio x96 is going to overflow or not. We'll look at the case for when this square root ratio x96 does not overflow. In this case, we first multiply the square root ratio x96 by itself to get ratio x192. Remember that this x96 means that this square root ratio is multiplied by a factor of 2 to the 96. We have two of these, so the resulting number will have 2 to the 192. And this will give us the ratio. In other words, first we have square root of p. This is multiplied by 2 to the 96, and we have two of these. And the result of multiplying square root of p times 2 to the 96 by square root of p times 2 to the 96 is, we have a square root of p multiplied by square root of p. So over here, we'll get the p, which represents the price. And then we also have 2 to the 96 multiplied by 2 to the 96. So this will result in 2 to the 196. So this is what this part of the code is doing. The resulting number is the price p multiplied by 2 to the 196. Next, this ratio x192 is either multiplied by the amount of token that's coming in, or 1 over that ratio is multiplied by the amount of token that is coming in. And the way to understand it is, remember that p, we said that is equal to the ratio of token y over token x. And also note that in Uniswap V3, tokens are ordered. So we will have token x is less than token y. This is done by comparing the addresses of the tokens. If this base token is less than quote token, this means that this base amount refers to token x. So we multiply p by some amount of token x, let's call this lowercase x, and we will get the amount of token y. For example, let's say that token y is USDC and token x is WEF. And let's also say that p is equal to 3000 USDC per 1 ETH. And let's also say that amount of token x is equal to 1. So when we do p times x, this is saying 3000 USDC over 1 ETH times 1. If we were to put in 1 ETH, what is the equivalent amount in USDC? And this will give us 3000 USDC. Okay, moving on. If base token is greater than quote token, then we know that this base token refers to token y, since token x is always less than token y. In this case, to calculate the amount of token x that will come out, what we'll need to do is 1 divided by p times the amount of token y. And this is equal to, p is equal to the ratio of y divided by x, so 1 over p will be the ratio x divided by y. And to this, we multiply some amount of token y. And this will give us the amount of token x. Again, for example, let's use this example. Token y is USDC, token x is WEF, and the current price p is 3000 USDC per 1 ETH. So what we need to do is do 1 over p. So this will be 1 ETH over 3000 USDC. Since y is USDC, let's say for y, we do 6000 USDC. 6000 USDC. And what do we get? If we do this math, we get that this is equal to 2 ETH. And what this tells us is that when the price of 1 ETH is 3000 USDC and we put in 6000 USDC, we will get back 2 ETH. Now note that instead of just multiplying and dividing these numbers, it's calling another library called moldib. What this function can do is multiply 2 UN256 and then divide by another UN256 without overflowing the first multiplication. In the first case, we multiply ratio x192, which is equal to the ratio p times 2 to the 196. Multiply this by the amount of token that's coming in, and then afterwards, it still has this extra 2 to the 196, so we'll need to divide by 2 to the 196 to remove this. And this is done by bit shifting 1 by 192. This is equivalent to 2 to the 196. And likewise, in the other case, we need to multiply by 1 over p by the amount of token that's coming in. We have the amount of token that's coming in, and we also have this base, 2 to the 192, multiplied by the base amount, and then divide by the ratio p, which has a 2 to the 196, and this 2 to the 196 will be cancelled out with this 2 to the 196. And that completes the code walkthrough for the function get_@tick. In this exercise, you will create a TWAP using Uniswap V3 pool. The pool contract and token 0 and token 1 are all initialized inside the constructor. And in this exercise, later you'll need to call this function get_@tick to calculate the amount of token out based on the amount of token in. And the exercise is over here. All of the tasks are inside the function get_TWAP_amount_out. For the input, it's going to take in token in, amount in, and the time interval to take the TWAP. And this function should return the amount of token out, calculated from the TWAP and amount in. For the first task, check that token in is either token 0 or token 1. And again, this token 0 and token 1 are initialized inside the constructor. Once you check that token in is token 0 or token 1, next figure out what token out is. Next, the dynamic array of type uint32 is initialized. This will store two elements. For the element at index 0, put in dt. This comes from the input. And for the element at index 1, put in 0. This dynamic array will be passed to the function pool.observe to get the tick cumulatives. Now, if you need a refresher on how to call observe on the pool contract, you can scroll up and then navigate to this interface. And inside the interface of the Uniswap V3 pool, you can see how to call the function observe. Okay, going back to our TWAP contract. Once you get two observations, one from 0 seconds ago and another from dt seconds ago, next you'll need to calculate the tick cumulative delta. This is calculated by taking the difference of the tick cumulative at 0 minus the tick cumulative at dt. After that, the next task is to calculate the average tick. Remember that after we calculate tick cumulative delta, we divide this by dt to calculate the average tick. And the next part of the code handles the logic for rounding down numbers. This works both for positive number and for negative number. Here what it's saying is that if tick cumulative delta is less than 0, and if it does not divide evenly by dt, then round down to negative infinity by doing tick minus minus. And the last task is to call the function get_@tick to return the amount of token out that will come out for amount of token in. Okay, let's go over the solutions. Let's start with the first task. The first task is to require that token in is either token 0 or token 1. I'll type require token in is equal to token 0 or token in is equal to token 1, and with the error message I'll just say invalid token. Okay, moving on to task 2. Assign token out. So at this stage we know that token in is either token 0 or token 1. So how do we figure out what token out is? So this is equal to, we can say if token in is equal to token 0, then we know that token out should be token 1. Otherwise, token in is token 1, so token out will be token 0. Okay, let's move on to the next task. The next task is to fill out time deltas with dt and 0. So say time deltas of 0 is dt, and then time deltas of 1 is equal to 0. Okay, the next task is to call pool.observe. How do we call this function? I'm going to navigate to the interface for Uniswap V3 pool contract and look at how to call this function observe. So to call this function, we pass in a dynamic array of type uint32, and then we'll get back two dynamic arrays. We're only interested in the first dynamic array that is returned. So say pool.observe and then pass in this time deltas, and it's going to return two outputs, but we're only interested in the first output, so we'll ignore the second output. The output type for the first output is a dynamic array of int 56. So here I'll type int 56 memory. I'll call it tick cumulatives. So that's task 4. Let's move on to task number 5. Calculate tick cumulative delta. This is equal to, the latest tick cumulative is stored in tick cumulatives of 0, and this is because when we call the function observe, we passed in a time delta, and the element at the first index tells Uniswap V3 to get the tick cumulative from 0 seconds ago. Say tick cumulatives at 1 minus tick cumulatives at 0. Tick cumulatives of 0 will correspond to the tick cumulative from dt seconds ago. Okay, the next task is to calculate the average tick. Now notice that we have several data types. For tick cumulative, it's int 56, and for dt, what's dt? dt is uint 32. So we need to cast both of these data types into int 24. To calculate the average tick, we'll need to take tick cumulative delta and then divide this by dt. So I'll type tick cumulative delta, divide by dt. Now dt is uint 32 and tick cumulative delta is int 56. So let's first cast dt into int 56 so that we can do a division of int 56. So I'll say int 56, cast dt into int 56, but before we can do this, we first need to cast this into uint 56. Okay, so now this division works, and this data type is int 56. We need to cast this into int 24, so say int 24. Okay, that's task number 6. Task number 7 is to call the function getQuoteAtTick. And how do we call this function? We pass in tick, amount of token in, and the token in, and then token out. Okay, so say return getQuoteAtTick, pass in the tick, this will be the average tick, and then amount in, token in, and token out. Okay, that completes this exercise. Let's try compiling the contract and then running the test. Okay, I'll try to compile the contract by typing forge build. Okay, so there was an error, there was a typo. Change this to getQuoteAtTick. Try compiling again. Okay, and our contract compiles. Let's now execute the test. I'll first set the environment variable for the fork URL, and then we'll execute the test by typing forge test -- fork URL match path test Uniswap V3 TWAP.test.sol and then BBB. Okay, and our test passed. Let's take a look at the test. The test contracts creates a TWAP contract for the Uniswap V3 pool for USDC WEF with 0.05% swap fee. And then it simply calculates the price of WEF in terms of USDC. For token in, we pass in WEF, and amount, we pass in 1 WEF. The TWAP is taken over 3,600 seconds. This is 1 hour. And then it prints out the amount of USDC that we'll get. Back inside our terminal, we can see that the time-weighted average price of WEF over the period of 1 hour is roughly 3,000 USDC. In this video, I'll explain about just-in-time liquidity in Uniswap V3. Let's say that Alice is a liquidity provider, and her position is in the current price. I've highlighted this in purple. Next, Bob swaps tokens. This will move the price from P0 to P1. From this trade, Alice earns some swap fees and she is happy. This is how normally a liquidity provider will earn some fees. Next, let's take a look at how just-in-time liquidity will change how the liquidity providers earn fees. Again, we'll say that Alice is a liquidity provider and her position is in the current price. And again, Bob submits a transaction to swap tokens. Here is where things get different from the first example. Here, Justin sees Bob's transaction in the mempool and then front runs Bob's transaction to add liquidity. Let's say that this is a transaction mempool and inside it there are some pending transactions. Inside here, Bob submits his transaction to swap tokens. Justin sees that Bob has submitted a transaction to swap tokens, and then he submits a transaction to add liquidity. He makes sure that his gas price is higher than Bob's transaction so that his transaction to add liquidity comes before Bob's transaction to swap tokens. Justin's transaction to add liquidity is processed, and then next Bob's transaction to trade tokens is processed. Let's say that this will move the price from P0 to P*1. Let's take a look at what this looks like on a graph. Before Bob submits his transaction, the current price, let's say, is at P0. Justin sees that Bob submitted his transaction and then front runs Bob's transaction. Let's say Justin has a lot of liquidity to a narrow price range, including the current price. This is shown in red. Let's compare the liquidity provided by Alice near the current price and how much Justin has provided. Close to the current price P0, Alice has provided about this much liquidity, whereas in the same price range, Justin provided this much liquidity, a lot more than Alice. So what this means is that when a trade executes between this price range, Justin will earn the majority of the fees. Bob's trade is processed and the price moves from P0 to P*1. Take a note here that the price change from P0 to P*1 is less than the price change from P0 to P1. Here there is less liquidity, so the price moves a lot. Whereas over here, there is a lot of liquidity around the current price range, so the price moves very little. This is called just-in-time liquidity. Justin sees that Bob has submitted a transaction to do a trade, and front runs the transaction to add liquidity so that he can earn a lot of the trading fees. With just-in-time liquidity, Alice earns very little fees, so this is not good news for Alice. On the other hand, Justin earned most of the fees, so he is happy. How about Bob? Well, Bob got a great price for his trade, so he is also happy. Well, why can we say that Bob got a great price? This is because when there is more liquidity, there is less price change. To put this in math, P*1 minus P0, the price change from P0 to P*1 when Justin added liquidity is less than P1 minus P0. This is the price change when Bob traded on this liquidity without just-in-time liquidity. So in summary, just-in-time liquidity is bad news for Alice, good news for Justin, and also good news for the trader Bob. In a constant product AMM, higher liquidity means less price impact. And for a trader, less price impact means they'll get more token out for the token that they put in. In this video, I'll illustrate this example that higher liquidity means lower price impact. In this example, we'll compare to constant product AMM. The constant product AMM on the right has a higher liquidity than the one on the left. We'll put in the same amount of tokens and then compare several things. We'll compare the final price, the amount of tokens that we get, and the execution price. So we have two constant product AMMs, x times y equals L square, where this L square is equal to 20, and we have another constant product AMM, x times y equals L square, where L is equal to 50 over here. The one on the right has a higher liquidity. On the two constant product AMMs that we're comparing, let's say that we initially start with the price equal to 1. And in both cases, we'll put in 20 token X. For the constant product AMM with a lower liquidity, when we put in 20 of token X, we get back 10 token Y. The resulting price after the swap is 0.25. Initially, we started out with price equal to 1, and for putting in 20 tokens and swapping out with 10 token Y, the price will become 0.25. If we were to swap this same amount of token on a constant product curve with higher liquidity, again we put in 20 token X, and this time we get approximately 14 token Y. Again, we started out with price equal to 1, and after the swap, the price is approximately 0.51. Okay, let's compare the numbers. On a constant product with lower liquidity, we put in 20 token and got back out 10 token. On the constant product curve with a higher liquidity, we put in the same exact amount of token, 20 token X, and this time we got approximately 14 token Y. So first thing to notice is that when we swap on the constant product curve with higher liquidity, we get more token out. Here we get approximately 14, but one with the lower liquidity, we get 10 token out. The other thing to notice is that the price after the swap. On the lower liquidity, it changed the price from 1 to 0.25. The difference is 0.75. On the curve with a higher liquidity, we started out with price equal to 1, and the resulting price is approximately 0.51. In this case, the price difference is approximately 0.49. 0.75 over here and 0.49 over here. So in a constant product curve, higher liquidity means less price impact, and the amount of token that you'll get for putting in the same amount of token is greater for a constant product curve with higher liquidity. Let's also compare the execution price. The execution price is simply the amount of token that came out divided by the amount of token that came in. In other words, it is the exchange rate for putting in one of these tokens. The execution price on the constant product curve with a lower liquidity is 0.5. 10 divided by 20 is 0.5. On the curve with a higher liquidity, the execution price is approximately 0.71. Again, we divide dy by dx to get this price. What the execution price tells us is the exchange rate for one of these tokens for one of these tokens. For putting in one of token X, we will get back 0.5 amount of token Y. On the other hand, when we swap on the constant product curve with higher liquidity, for each token X, we get back roughly 0.71 token Y. If you're a trader, would you rather get 0.5 token Y for putting in one token X? Or is it a better deal if for every token X that you put in, you get back 0.71 token Y? Here the better deal is the one with the higher execution price, swapping on the curve with a higher liquidity. So this is how when we swap on a constant product curve with a higher liquidity, we get a better deal for our swap and there's less price impact. And finally, if we increase the liquidity to a higher number, you can see that the execution price increases. So this means that it is even a better deal to swap on, and the price impact becomes less.